Hello, check. All right, people. Finally, we are live. I thank you so much for all of your patience that you've collectively shown here. Vanakkam, everyone. Warm welcome to all of you to Vedantu Master Tamil. And today we are going to focus on organic chemistry for your board examinations, right? So, just a few things before we begin the class. We will be revising organic chemistry for your board examinations. And one more thing, I'm sure Shimon Sir must have told you this already, that the language of instruction for this class will be in English. All right. Because anyway, your board exam is going to be in the English language. You have to write things in the English language. So this is what we will follow today. All right. We'll revise all the chapters of organic chemistry one by one. Now the session duration will be, you can assume 1 hour for every single chapter. You can calculate accordingly. Fine. So the first thing that we will do is we will go towards alkyl halides. Yes. And the very first reaction of alkyl halides, as you guys know, is the free radical halogenation of alkanes. And in the process, we'll be looking at a lot of theory. We'll also be looking at a lot of previous year questions of board examinations. And from theory and from questions both, we'll be learning a lot about organic chemistry. All right. So let's jump right into the first reaction that we have right now. This is the free radical halogenation of alkanes. So what we start with over here is a very simple alkane. Let us take the example of propane. CH3, CH2, CH3. We start with a propane, and what we want to do over here is a reaction with halogen. Now this reaction is best done with chlorine or bromine. I'll tell you why this reaction is very bad with chlorine or iodine. Very interesting ideas. So preferably we will keep any halogen over here. I'll write over here, preferably Cl2 or Br2. And in your NCERT, in your board examinations, mostly questions from Cl2 reaction will be asked. Now, to activate this reaction, what we need over here is energy. Every reaction needs energy to be activated, right? So the way in which we activate this reaction is by providing it ultraviolet light. We provide it UV light. And UV light is also written as H times nu. H is the Planck's constant and nu is the frequency of radiation. Right? So H nu is a symbol for UV light. In some cases, most of the times this will only be written. You will write this and you will get the full marks. Sometimes, instead of providing energy via light, we can also provide energy via heat. Thermal energy can also be provided, so you can also provide heat in this reaction. But in your board examination, write this. You will get good marks. All right. So what can happen over here is that one of the hydrogens will be replaced by one of the halogens. Okay. One of the hydrogens will be replaced by one of the halogens. So the possible products that we can get over here. One product is when we will get chlorine on the outer carbon. One case is when we will get chlorine on the inner carbon. Right? These two mixture of products can be formed over here. Now the interesting thing is that when we do this reaction with chlorine, there is no specific major or minor product. Both of these are formed in decent amounts. That's the thing about chlorine. And in your board examinations, no one going to ask you about the major product. If you studied for JEE, you know that this is a free radical reaction. You go via the most stable free radical generally. But in board examination, you don't need to think too much about that. Chlorine is very reactive. It gives us a mixture of products over here. So we will get a mix of products. And now the interesting thing is that we prefer not to do this reaction in the laboratory. In the laboratory, we prefer not to do this reaction. Why? Because this mix of products is very difficult to separate. All right. It's not easy to separate the mixture because see, These are isomeric halogens. This is propane 1 chloride, this is propane 2 chloride, right? Now the thing is their boiling points are very similar to each other. Because the boiling points are very similar to each other, when you try to do distillation, both of them boil almost at the same temperature. So even after you distill, you will be remaining with a mixture only. Isolation of one of these is not very easily possible, and therefore we prefer not to do this reaction. Bromine will give you a better reaction, by the way. Bromine will give you major product this, minor product this. The 2-degree product over here, bromine will give you this as the major product because bromine reacts a little slower. Bromine reacts a little slower, so it chooses the middle carbon for the more stable free radical. But in board examination, that information is not given to you. Okay, so what we need to remember over here is the reactivity of halogen. In this particular reaction, the highest reactivity comes for fluorine, then for chlorine, then for bromine, and then for iodine. This is the reactivity order. Now, I told you we don't do these reactions with fluorine generally. You know why? Because if you do the reaction with fluorine, the reaction with fluorine is very hard to control. It ends up becoming explosive in nature. Okay? So if you try to do this reaction in the laboratory with fluorine, you might end up blowing something up. Have you seen that cartoon Dexter's Lab? That might happen to your laboratory, so please don't do that. Anyway, sourcing fluorine is not very easy. This itself is not that easy to source in the laboratory. Anyway, and when it comes to iodine, the reaction is extremely slow. Okay, the reaction with iodine is extremely slow. It's so slow that to get the proper product, you might take 2-3 days. So it's so slow that you prefer not to do it. It's better to just do the reaction with chlorine or bromine. Bromine is slightly slower, so gives you a better single product. Chlorine is faster, so gives you a nice mixture of products. Free radical halogenation. And let me show you how this is mentioned in the NCERT, because the questions are going to be asked from the NCERT itself, right? So, if I show you how it is mentioned inside the NCERT, this particular reaction, you will be surprised to see from alkanes free radical halogenation, that's it. That's all the information that's mentioned in the NCERT regarding this particular question. Alright, so you don't expect difficult questions from this reaction at least. Reactions, this reaction is going to be easy. So from the perspective of board examination, this is all. Fine. So now a lot of you must be wondering that, sir, okay, can you tell us what kind of question might come from this reaction? If easy questions will come, what kind of question? Yeah, that might be your question. So before I take you to the question, let me introduce myself. A lot of you are attending my class for the very first time. Some of you are my old students. I can see them in the chat. So my dear friends, my name is Pahul. I am an alumnus of IIT Bombay. I've got a lot of hobbies. I like to travel on my motorcycles. I've been teaching for almost a decade now, and I've done my master's in chemistry. I got a 5-year integrated MSc in chemistry in IIT Bombay. So I cleared my JEE Advanced back in 2011, and then, well, yeah, I'm here. Yes, I recognize you guys from the regular batch. Very good stuff. So this is me on my Ducati Diavel, by the way, for those of you who are curious. So just to show you the kind of question that they might ask from this particular segment, look at the first question over here. Look at the first question over here. This is a previous year question, by the way. This was asked in 2023. And this type of a case. Which isomer of C5H10 gives a single monochloro compound C5H9 in bright sunlight? You need to figure out a compound C5H10 that gives a single monochloro compound C5H9Cl in bright sunlight. Yes. So what do we do? How do we figure that out? First of all, you need to understand that C5H10 C5H10. My dear friends, is this an alkane? This is not a simple alkane, right? Why? Listen. Because the formula for any simple alkane, now this is where I teach you better thought process using a question. If you talk about a simple alkane, what's the formula? CnH2n plus 2. That's the formula for an alkane, right? Now, if I have a 5 carbon alkane, what should be the formula for that? For a 5 carbon alkane, the formula should be C5H12, right? This is missing 2 hydrogens. So, if I have to go from the formula of C5H10 towards C5H12, how many hydrogens do I need over here? How many hydrogens do I need? I need 2 hydrogens, right? I could write that information in this fashion. I need 1 molecule of H2, right? I need 1 molecule of H2. So this 1 molecule of H2, this number 1, this number that we figured out over here, this number is known as the degree of unsaturation. All right. This is known as the degree of unsaturation. The number of hydrogen molecules required to take any formula to the formula of an alkane is known as the degree of unsaturation. So what we've understood just by looking at the formula, my brain says that this has 1 degree of unsaturation. So with 1 degree of unsaturation, what are the type of compounds that I could have? That's the thought process. The type of compounds that we could have, number 1 is we could have an alkene. We could start with an alkene, right? But will an alkene give me a monochloro derivative? Will a 5 carbon alkene give me a monochloro derivative? Think about it. I can put chlorine here or here or here or here or here. There are multiple places in which I can put chlorine. So an alkene for this question does not make sense. So what makes sense? The other thing that can have 1 degree of unsaturation is a cyclic alkane. Yeah. We could have a cyclic alkane because in a cyclic alkane, when you close the ring, you lose 2 hydrogens. If you start with an alkane of 5 carbons, if you close the ring, you will lose 2 hydrogens. That's when it becomes C5H10. So, very simply, and a lot of you got the answer already, I'm just explaining the thought process behind it. If I have simple cyclopentane, if I put a chlorine here, or I put a chlorine here, or I put a chlorine here, etc., it's basically the same product. Yeah. So basically, you're going to get the same product if you monochlorinate cyclopentane in either position. Any position. Right? So in board examinations, now see the thing is, this question can be asked for 1 mark. This question can be asked for 2 marks also. So if this is a 1 mark question, you simply draw the structure, you got the correct answer, very nice. But if this is a 2 mark question or a 3 mark question by chance, then what do? Then in that question, you mention that formula C5H10 has 1 degree of unsaturation. The possible compounds could be this and this. The only compound that suits the condition is cyclopentane. And then draw the structure of cyclopentane and then draw the structure of the final product. Then you will get your good 3 marks also. Alright, so that's how it's going to work in your board examination. Anyway, so that was our reaction of free radical halogenation. Nice. Let's move on to the next reaction now. So the next reaction that we have is addition of HBr on alkene. Yes, this type of a reaction is also known as the reaction of Markovnikov addition. Yes, this is also known as the reaction of Markovnikov addition. So once again, Just for the sake of simplicity, we'll be taking the example of propene over here. Since board examinations, we'll be taking simpler cases. So if we start with propene, what we are going to do is we are going to add an HBr onto it. Now HBr can be thought of as a ionic compound. Even if you think of it as a covalent bond, it's a highly polar covalent bond. So essentially we have H positive and Br negative. So what we do over here is we take the double bond. Okay. Whenever we have a double bond, one bond is sigma, the other bond is pi. So we take the pi bond and polarize this pi bond towards the outer carbon. Then this carbon goes and attacks the proton. Always in chemistry, move your arrows from electrons towards positive charges. In your board exams also, you have to move the arrows from electrons towards positive charges. Okay. So once this particular process happens, can you guys imagine that basically the outside carbon will become CH3, that left side carbon is already CH3, and this carbon over here now will get a positive charge, right? You would get a positive charge over here. So my dear friends, what we have here is a carbocation formation. In this particular reaction, we form a carbocation first. Now this carbocation can be attacked by the Br negative. Okay. Now take this Br negative and attack it onto the carbocation. So eventually, what will we get? We will get CH3, bromine on the middle carbon, and another CH3 over here. So what we have here in this particular case is the more substituted product. Yeah. Bromine goes on the inner carbon, not on the outside carbon. Why? Because we are supposed to form a carbocation over here. And if you remember your GOC times, you know that 2-degree carbocation is better than 1-degree carbocation. If I made a 1-degree carbocation by moving the electrons in the opposite direction, let's say, 1-degree carbocation will not be that stable, but 2-degree carbocation is pretty stable. So, because I need to do a 2-degree carbocation formation, more stable carbocation formation, I get a more substituted product. So, the formation of more substituted product is known as the Markovnikov rule. Whenever more substituted product is formed inside any reaction, it is known as the Markovnikov rule. Alright. Pikachu is asking, is this live or premiere? It's a live session, bro. Alright. So, this is what's mentioned in the NCERT, that if I add HI, HBr, HCl, same reaction, okay? So, if I take an alkene and I add the halo acid onto it, then what I will get is outside product is minor, inside product is major. This is also known as Markovnikov rule. So if in your board you get the question, you can get this for 2-3 marks. What is Markovnikov rule? Illustrate with example. So you will write this reaction, you will write this carbocation, you will write this product, and then write, because we want to make the more stable carbocation, more substituted product is formed, which is known as Markovnikov rule. Coolio. Now Danisha is asking about the H2O2 reaction, the Kharash effect reaction. In NCERT, the Kharash effect is not mentioned. So in board examination, they will not ask you about the Kharash effect. I'll mention that for you later, but you don't need to worry about it at the moment. Yeah. So the next reaction, which is even more simple, is the addition of a full halogen on an alkene. Okay. So if I take an alkene, let's say like this, same propene, just making a quicker structure over here. If I add, let's say, Br2 in the presence of CCl4, this is the NCERT reaction, by the way. Yeah. So what will happen on both sides? We will have the addition of bromine. On both sides of the double bond, we would add a bromine. That's it. So my dear friends, this type of a reaction, okay, this type of a reaction can be used as a test for unsaturation. Can be used as a test for unsaturation. And by unsaturation, I specifically mean either C double bond C or C triple bond C. Because on any pi bond, the halogen can add in this particular fashion. So, can you guys tell me what is the color of bromine? Have you guys seen bromine in the laboratory? Yeah. What's the color of bromine? Gokul, it's okay. We'll talk about Kharash effect also. Yeah. So, bromine's color on its own is this reddish brown color. Have you seen soya sauce in your kitchen? It looks like soya sauce, but it's very harmful. You can't inhale bromine. You'll die. So, bromine, reddish brown color, when it reacts with an alkene, the compound that you get eventually is a colorless compound. So, bromine loses its color on reacting with an alkene. Fine. So, that's how this particular reaction works. Now, you were asking, sir, what if we react it with HBr in the presence of H2O2? Yeah. So, the same type of reaction, this one, if I do it directly with HBr, I will get a Markovnikov product. But if this reaction, HBr, is done in the presence of a peroxide, okay, this peroxide could be H2O2. Could be any other peroxide also, but H2O2 works very well over here. In this particular scenario, the product that you will have is going to be the anti-Markovnikov product. Anti-Markovnikov product is the major product. Alrighty. In the presence of peroxide, anti-Markovnikov product is the major product. Now, this is also known as the Kharash effect. Just a name for it. Maurice Kharash was the scientist who figured this out, and this was done in 1900s, surprisingly. People knew about Markovnikov effect a long time ago, but then in early 1900s, this guy somehow figured out that you can bypass the Markovnikov rule only for HBr, okay? This reaction does not work for HCl or HI. It works only for HBr. For HBr, you can bypass it just by putting a peroxide. Harish, yeah, I will share the PDF with you later, man. All right. So, coolio. Alrighty, very nice. So now, my dear friends, before we move on to the SN1, SN2 type reactions, let's discuss a little bit about what is a chiral carbon. Do you guys understand what's a chiral carbon? Gokul, see, we don't need to go to the mechanism of Kharash effect right now because we are targeting revision for board exams. If I start going to mechanisms, then it will take too long. So I'm mostly doing this from the perspective of your board exam that you have on 27th. All right. Anyway, so what do we mean by a chiral carbon? A chiral carbon is a tetrahedral carbon with all four substituents different from each other. Yeah. So carbon, which looks something like this. Let's say we have substituent A, B, X, and Y. All four substituents are different. So what's going to happen here is if I make a mirror image of this particular substance. If I make a mirror image of this particular substance, what would it look like? It would look something like this. Once I draw, you will be able to see. I can say that's the mirror image, right? So now the thing is, if you try to superimpose these two images on top of each other, they will not be superimposable. These two compounds that we've drawn over here, I'll explain everything, don't worry. These are known as non-superimposable mirror images. Now, my question to you is, do you understand what this statement means? Yeah? Danish, I'll cover them via questions. I will touch upon the physical properties as well, but I'll cover them via questions. And can do it. And Prithvi are asking, can I watch this before learning the chapter? Is this lecture enough? This is primarily for revision, but I'll teach in a manner that you'll be able to learn a lot of things for board exam. So even if you watch this lecture, you'll be able to score very well in board examination if you've not done anything till now. And this is a long marathon type session, so it will take us a good number of hours to complete, but we'll do it. Yeah, so very nice. A lot of you understand that these two do not sit on top of each other. Let's see a few examples and then I can show you these models as well. So, do you understand why these two chairs are different from each other? Chandresh, yes, bro. Yeah. Do you understand how these two chairs are different from each other? If you sit on this chair, you'll be able to write with your right hand. But if you sit on this particular chair, you'll have to use your left hand. Right? They are mirror images, but they are not the same. Mirror images, but they are not the same. Right? Similarly, look at these two scissors. One of these is a right-handed scissor and one of these is a left-handed scissor. Yeah, you can figure out. Exactly. And then, does anyone recognize who this is? Does anyone recognize what band this is from? So this is a guitarist of a very popular band. If you haven't heard their songs, you can, if you are into metal. Avenged Sevenfold. Yeah, that's the band. This is the lead guitarist of that band. And if you can see, the guitars look different, right? This is supposed to be a left-handed guitar. This is supposed to be a right-handed guitar. Both guitars are different. They are mirror images of each other. The Razzling Nerd, very nice. Yeah, there are some metalheads in the chat, very good. So this guy actually is a left-handed guitarist. Usually most people are right-handed guitarists, but this guy is a left-handed guitarist. This is the actual image. So similarly, these two carbons are chiral. They are non-superimposable. They are mirror images, but they are different from each other. So because they are different, they have the same formula, right? But since they are different, my dear friends, these are optical isomers of each other. Isomer because same formula. Optical isomer because these two differ in their symmetry from each other. So these non-superimposable mirror images in the language of chemistry are known as enantiomers. Okay. These are called enantiomers. Alrighty. So that's how it works. And I told you a little bit about chirality as well. Now, can you recognize what this setup is? I have seen some questions in board examinations related to this idea. That's why I thought I would explain this setup to you as well. So what's going on over here is we have a source of light. Light, as we know, is just electromagnetic radiation. So the first image that we have over here represents the fact that the radiation oscillates in all directions. Essentially, when light is traveling towards you, let's say you're looking at a light bulb, light is traveling towards you, but the light that comes from there is an unfiltered type of light. The light from the light bulb oscillates in this direction and in this direction and in this direction and in this direction. It oscillates in all sorts of directions. So what you do over here is you put something called a polarizer. And this isolates one of those directions. Light is oscillating in multiple directions. You isolate one of the directions of the wave. So this, my dear friends, is known as plane polarized light. Okay. This is known as plane polarized light. one of the directions of the oscillation have been isolated over here. Now, the interesting thing is, when you pass this plane polarized light through an optically active compound, or I can say chiral compound, yeah, what happens is, this chiral compound, that molecule, that asymmetric carbon that we saw, that will take this light and rotate it. What happens is, you've got asymmetry. In any chiral carbon, we've got asymmetry. There are asymmetric electric fields over here, right? This has electric field, this has electric field, this has. So these asymmetric electric fields interact with the electric field of light and bend it in a very specific direction. So this optically active compound, or the asymmetric compound, asymmetric means chiral, this chiral compound rotates plane polarized light. This phenomena is called optical activity. The phenomena that is mentioned in this entire diagram is known as optical activity. Alrighty, very nice. Ryan, so that's the fun part, bro. So Louis Pasteur, you guys know Louis Pasteur, pasteurization process. You boil milk and then you drink it. So that same guy used to do all sorts of weird experiments. This experiment was figured out by Louis Pasteur. I don't know what went wrong with him, but he was trying to shine light on organic compounds, and then he realized that some organic compounds rotate that light. Then he figured out why that's happening. That's happening because the compound itself is asymmetric. Asymmetric means the mirror image of that compound does not superimpose on the original compound. Extremely interesting. So yeah, this is the idea of optical activity. So whenever we have two enantiomers, all right, whenever we have two enantiomers, their physical properties are same. They have same physical properties. And if you do the experiment with this, let's say in the laboratory, you put it in the polarimeter, you see how it rotates light. Let's say this rotates light in clockwise direction by 20 degrees. 20 degree clockwise. The enantiomer will rotate light anti-clockwise by 20 degrees. Plus 20 degree rotation, minus 20 degree rotation. Clockwise is referred to with the plus sign or with a small d. Anti-clockwise is referred to with a minus sign or a small l. Okay. D stands for dextro-rotatory. Let me write the spellings of this. D stands for dextro-rotatory, and L stands for levo-rotatory. Alrighty. Dextro-rotatory and levo-rotatory. Alrighty, so that's how the chiral carbon works, and now you know exactly what happens. There's a more labeled diagram that you will get in the PDF later. Fine. Alright. So now it is time for us to move to a certain reaction where this optical activity matters. Let's move to a reaction where the asymmetry of the carbon matters to us, and the reaction that I'm talking about, I'm sure a lot of you have figured out already, is the SN2 reaction. Yeah, this is what I'm going to talk about now, the SN2 reaction. So what happens in an SN2 reaction is we start with an alkyl halide. You can start with any alkyl halide, by the way, but to illustrate this idea, I'm going to start with an asymmetric alkyl halide. So let us say this is the carbon and we have another CH3 on it. We have a hydrogen over here. Just for the sake of it, let's put a CH2, CH3 on this side, and over here On the front, let us put a bromine. So what we've taken is an alkyl halide, haloalkane. We are going to react this with a nucleophile. People, what do we mean by a nucleophile? Nucleophile means something that is attracted towards positive charges, something that wants positive charges. So a good example of a nucleophile could be OH negative, right? This wants a positive charge. Where is the positive charge in this particular structure? Do you realize bromine or a halogen has higher electronegativity? Bromine has higher electronegativity, carbon has lesser electronegativity. So this bond pair, this bond has 2 electrons, right? These 2 electrons will be more towards bromine, isn't it? So this bond that we've got over here has 2 electrons in it, and both the electrons will be more towards bromine. So bromine here carries a negative character on it, and the carbon on the other hand carries a positive character. All right. Because of the electronegativity, bromine carries a negative character, the carbon carries a positive character, and the oxygen is attracted to it. So what we'll do is we'll move the arrows from the negative to the positive direction, and then a reaction will happen. What's the reaction that is going to happen? Oxygen will form a bond with carbon. At the same time, bromine will take both these electrons and leave. You need to make space for the oxygen, right? So bromine leaves, and then only the oxygen will be able to sit there. So this process, this SN2 reaction, happens in a single step. This happens in a single step, one step reaction. Now what we want to make over here is the imagination of how this reaction would happen. We want to make an imagination over here. How would this reaction be happening? Let's think about it. So when the reaction is happening, the bond with bromine is breaking apart. Yeah. And at the same time, the bond with oxygen is getting formed. Yeah. So I can write that this bond is breaking and the blue colored bond is getting formed. What about the remaining bonds on the carbon? The remaining bonds on carbon would look something like this. So this is your CH3, let's say. This is your hydrogen. This is your CH2, CH3. Something like this is going on, where the middle 3 bonds are now in one plane. Bromine is breaking, oxygen is associating itself with carbon, and this, my dear friends, is an imaginary thing that we are putting on paper. This is while the reaction is happening, while the bonds are being broken, while the bonds are being formed. This is known as the transition state. It's undergoing the transition right now. And once the transition is over, then what's going to happen? Once the transition is over, this bromine would have left. You would get Br negative. And notice the image that I'll make for the final product. In the final product, now interestingly, what's going to happen is you will have something like this. Can you notice where the oxygen has come from? The oxygen has attacked from the opposite side of bromine. Yes, I can say that the nucleophile, this guy attacks from the back side. Alrighty. Why did we call it the back side? Because you can't approach it from this side, isn't it? There is an electric field of bromine in this direction. If the oxygen were to come from this direction, bromine's electric field, oxygen's electric field, they will mess up with each other. Repulsion will happen. We don't want that. So the nucleophile comes from the opposite side of the, what do we call bromine in this particular case? We call bromine the leaving group. Okay, bromine over here is known as the leaving group. And what we have made, can you see the structure here and this structure looks like an opposite image of each other? Over here bromine was at the front, over here oxygen is at the back. So my dear friends, this type of a flip that has happened, what you can imagine is, this was your original structure, oxygen came from here, now this structure flipped in the opposite direction. This is where oxygen is now. So this flip that we have, alright, this flip that we have, this is known as Walden inversion. So when the stereochemistry changes, that is known as inversion. What has happened over here is inversion of the chiral carbon. You can also call it inversion of the stereo center. And in your exam, you can be asked to make the entire thing, because this is mentioned in the NCERT very beautifully, by the way. So SN2 reaction is a single step reaction and inversion of configuration takes place. So if we start with a pure enantiomer, the final product will be a pure enantiomer only. If we start with a pure enantiomer, only the opposite enantiomer at the end will be formed, basically. Cool. That's the idea over here. Now people, there are some more points about the SN2 reaction that we will write over here. This is favored by aprotic solvents, or you can also say non-polar solvents. Aprotic means, can anyone explain aprotic? I'll give you some examples of aprotic solvents on the next page. So, favored by aprotic solvents, and nucleophile wants to avoid steric hindrance. Steric hindrance. So if you've studied GOC properly, you know what steric hindrance is. Steric hindrance means crowding. Steric hindrance basically means there's too much electric field already. Nucleophile needs a clear path to approach, right? If the structure itself is bulky, if the structure itself has so many electric fields on it, then oxygen will not be able to approach, because this electric field, there will be repulsion. So you need the minimum amount of steric hindrance. Alright, so when we talk about aprotic versus protic solvent, aprotic means no acidic H positive is present. Alrighty. So what do we mean by that? For example, acetone. These hydrogens are not very acidic in nature. When you throw them in water, you will not get H positive out of this. Why? Because carbon and hydrogen electronegativity is very similar. Okay. Similarly, if you have something like this, carbon disulfide. Okay, this is known as carbon disulfide. One more very interesting structure I'll show you. CH3, C double bond O, single bond, NH2. This is what? This is called as an amide. Yeah, this is an amide type of structure. Now let's modify the amide a little. Let's take both of these acidic hydrogens in the amide, put CH3s, and instead of the CH3 over here, let's simply have hydrogen. This is known as dimethyl formamide. Dimethyl for these two CH3s, form for the hydrogen, amide. This is abbreviated as DMF. So now the interesting thing is you had two acidic hydrogens over here. Those were acidic because nitrogen and hydrogen, the electronegativity difference is quite significant. You removed them, put CH3s. Aprotic solvent. Protic solvents, obviously, water is a protic solvent. Why is water a protic solvent? Because oxygen is quite electronegative. H positive can be removed over here. Ammonia is a protic solvent. CH3, C double bond O single bond OH. Acidic carboxylic acid, protic solvent. So we've observed in the laboratory that aprotic solvents are better for the SN2 reaction. Aprotic solvents are better for the SN2 reaction. Then comes the idea of steric hindrance. The nucleophile wants to avoid steric hindrance. If I ask you about the rate of reaction of SN2 between the given species, I'll give you the examples. Let's say we have CH3Br versus carbon with a bromine that has another CH3 on it. Then you have another carbon which has two CH3s on it. And then let's take a carbon which has three CH3s on it and a bromine. Can you tell me what would be the order for the rate of the SN2 reaction? And the idea that you have to use over here is avoid steric hindrance. Steric hindrance means crowding. Steric hindrance means electric fields repelling with each other. So, what will be the order of the rate of SN2 reaction? Which will give the faster SN2 reaction? This will give the fastest SN2 reaction. Because carbon has only hydrogens and one bromine. OH negative will very easily approach the carbon. Over here, OH negative might get problems because of the CH3. Over here, OH negative will get repelled by two CH3's electric fields. Over here, too many electric fields. OH negative will not be able to approach this carbon. This carbon is very crowded in nature. So, this would be the rate. Methyl halide versus 1 degree halide versus 2 degree halide versus 3 degree halide. SN2 reaction is best done with smaller alkyl halides. Okay. SN2 is best done with smaller alkyl halide. This is the example that they've mentioned in the NCERT. Now you understand this image very well. Yeah. Jaden, this marathon is targeted at the CBSE boards mainly, although this will help some ideas of JEE also, because JEE usually asks questions from the NCERT directly, but this is mainly targeted at board exams. Okay. Sai-Shri is asking what's the difference between an enantiomer and any stereoisomer. See, Sai-Shri, enantiomer is the mirror image. Non-superimposable mirror image is enantiomer. Now, if there are multiple chiral carbons, you can have stereoisomers that are not mirror images of each other. That you do in JEE. For boards, you don't need to worry about that. Alrighty, very nice. Ritik, cool, bro. Alright, so yeah, as you can see, methyl gets 30 times the rate of an ethyl. Isopropyl's rate is only 0.02. 3 degree halides do not give SN2. Okay, so please keep in your mind that 3 degree halides don't give SN2 reaction. Alright, very nice. Now, my dear friends, are you wondering why the name of this reaction is SN2? Why is the name of this reaction SN2? Let me tell you why it is called SN2. S stands for substitution. N stands for nucleophilic, and 2 stands for biomolecular. We've understood nucleophilic, we've understood substitution, because substitution means replacement. We are replacing bromine with oxygen, perfect. What about the 2 over here? What about the 2 over here? How is this reaction? Bimolecular. In the main step of the reaction, there's only one step. In the main step of the reaction, there are 2 molecules that are colliding with each other. Alright, so 2 molecules colliding with each other, bimolecular reaction. And since this is a single step reaction, my dear friends, the rate of this reaction would depend on both the concentration or the activity of the alkyl halide and on the concentration of the nucleophile. Rate of the SN2 reaction depends both on the alkyl halide and nucleophile concentration. So, increase the nucleophile, faster reaction. Increase the alkyl halide, faster reaction. Increase the strength of nucleophile, make this more negatively charged, faster reaction. Alright, so that's how the SN2 reaction works. Now, let's move to a reaction that is sort of the opposite of this one. We're talking about the SN1 type of reaction. Now, what happens in an SN1 type of reaction is very fancy. For SN1, I will take a specific example of this type of a halogen. Do you realize this is the same halogen that we drew on the SN1 on the SN2 page? Drawing it in a slightly different fashion, same thing. Yeah, carbon CH3, CH2, CH3, bromine. Okay. So, my dear friends, in the SN1 reaction, this is a unimolecular reaction. It is a 2-step reaction. So, the first step over here is the loss of leaving group. Alright, the leaving group leaves. And after the first step, what you get over here is a carbocation. Loss of leaving group and a carbocation formation happens over here. Now, in your board examination, rearrangement is not asked, so don't worry about carbocation rearrangement right now. So, once the carbocation formation happens, then you react it with the nucleophile. Now, people, let me tell you something interesting. For the SN1 reaction, we prefer taking a weak nucleophile. Why would we keep a weak nucleophile? Can you imagine? Can you figure out on your own logically why would we keep a weak nucleophile over here? Because if we had a strong nucleophile, it would do SN2 reaction. Right? SN2 reaction is nucleophile comes and attacks. I don't want the nucleophile to attack first. No. I want this structure to break apart on its own when I provided the activation energy, when I provide the little bit of heat to do this reaction. I want this to break apart on its own. Then I want the nucleophile to attack. So first you will have leaving group leaves, then nucleophile will attack. Weak nucleophile means you don't take a negatively charged species. You take a covalently bonded species, something like water can be taken over here. Simply take water. Now people, water can attack this positive charge. And do you realize the attack can happen from any direction now? There is no steric hindrance problem anymore. We have a planar carbocation. So the oxygen can attack from any direction. Both side attack is possible, not only backside attack anymore. Bromine is left. Forget about bromine. You can simply do it like this over here. Minus, Br negative. Bye-bye. So now, ultimately, people, what we will get over here is this type of a product. And you should realize that the carbon that we have here is a chiral carbon. It's a chiral carbon, right? Since oxygen can attack from both sides, both the enantiomers, okay, both enantiomers, are formed in equal amount. Obviously, since both side attack is possible. So when both enantiomers are formed in equal amount, my dear friends, what do we call this? We call this a racemic mixture. The name for this mixture, where both the enantiomers are formed in equal amount, it is called a racemic mixture. So both compounds are formed. The levorotatory is also formed. The dextrorotatory is also formed. Both are formed in equal amount. So the overall mixture over here is known as racemic mixture. All right, racemic mixture. Half of the product is inversion, half of the product is retention. So half product is inversion product, and the remaining half of the product is called the retention product. Inversion we understood from the SN2 reaction, when the stereocenter flips. When the stereocenter doesn't flip, that is called the retention product. Very, very nice. So that's about your SN1 reaction, unimolecular nucleophilic substitution. Yeah. So SN1, why do we call this unimolecular? Because this is the main step of the reaction. Formation of carbocation will be the slow step of the reaction. Slow, which makes it the rate determining step. This step determines how fast the rest of the reaction will go, because this is the slower step of the reaction. So in the slower step of the reaction, only one molecule is breaking apart. Yeah. Only one molecule breaks apart in the main step of the reaction. Therefore, this is a unimolecular reaction. Interestingly, the rate for this reaction is only dependent on the concentration of the alkyl halide and nothing else. All right. So, my dear friends, for alkyl halides, the rate varies in this fashion. Basically, I can say over here that I negative is the best leaving group. I negative is the best leaving group, because when I negative leaves, I negative has very low charge density. The negative charge of iodine is on a huge volume, so it's not very reactive. Coolio. So that's how this works. Alrighty. Chocolate boy Shimon sir is here only. He hasn't gone anywhere. He will come when you have mathematics. Yeah. Alrighty. So that was your SN1 type of reaction. Now that we've understood SN1 and SN2, let me show you some examples, some practical examples of SN1 and SN2 reaction. Look at this reaction. Finkelstein reaction. My dear friends, in the Finkelstein reaction, what we do is we take any alkyl chloride or bromide and we react it with sodium iodide in the presence of acetone. People, what have I taken over here? We've taken a small alkyl halide. Yes. What is this? This is essentially Na positive, I negative. Because you have negative charge on the reacting species, this is a strong nucleophile. The solvent that we've taken over here is an aprotic solvent. The reaction conditions refer to a very nice SN2 reaction. And once the SN2 reaction happens, what would be the product? Your chloride or bromide would be replaced by the iodide and you would get NaCl or NaBr as the side product. So Finkelstein reaction is a typical SN2 reaction for preparation of alkyl iodides. This is what is mentioned in the NCERT. Alrighty. Alkyl iodides are often prepared by the reaction of alkyl chlorides or bromides with sodium iodide in dry acetone. What do we mean by dry? Dry means no water. Acetone itself is a liquid. You don't take powder acetone. No, that does not exist. You take no water acetone. Acetone itself is liquid only. This reaction is known as the Finkelstein reaction. So Rx plus NaI gives Ri plus NaX. Now, NaCl or NaBr that are formed in this reaction are precipitated in the acetone. Sodium iodide is soluble in acetone. But as soon as sodium chloride or bromide is formed, it comes out of the reaction mixture. It precipitates, makes a powder, comes out of acetone. So, if I remove a product from the reaction mixture, the reaction is driven in forward direction. Remember equilibrium from 11th class. If I take one of the products and remove it from the reaction mixture, reaction is driven in the forward direction. That is known as the Le Chatelier's principle. Yeah. So Finkelstein reaction, and Ryan is asking, sir, you can call this a double displacement? Yes, you can. Technically, it is a substitution reaction. Flip it. Now, Akshata is asking, sir, why do we use dry acetone? Why don't we use water? Can you answer? Why don't we use water over here? Because if water is there, then I might have competition with SN1 reaction. So that is why. Alrighty. That's why we prefer not to take water. So water being a protic solvent, carbocations are stabilized by H positive OH negative presence. Basically, I'm talking about a protic solvent. Got it? So just to avoid the happening of SN1 reaction over there, we prefer taking this in dry acetone. That's the first reason. The second reason is sodium chloride and sodium bromide are soluble in water. But at the end, we need them to precipitate out. Only in acetone, these two precipitate out. Right? Now, the razzing nerd is asking, so why are iodoalkanes not prepared directly? Good question. I was waiting for someone to ask this. Yeah. So, the razzing nerd is asking, sir, why can't we create iodides directly? Why do we need the Finkelstein reaction? Because I've already told you one thing interesting. The interesting thing that I have told you is that this reaction to create iodides is extremely slow. So if we can't do this, we would create the chloride first and then convert it to the iodide. So now you understand, because we can't do this reaction with fluorine, we would need a fluoride reaction also. We saw the iodide reaction, we would need a fluoride reaction also, because this is bad for fluorine. So the fluorine counterpart of the SN2 reaction is known as the Schwarz reaction. Nice. So in Schwarz reaction, we take a small halide, chloride or bromide, both work. Take AgF, any fluoride providing reagent, F negative providing species. Alright, and then you get your alkyl fluoride over here. These are different fluoride providing species. Very nice. Acha. Now one more thing I want to ask you is, if I start with an alcohol, let's say, and I react it with an alkyl halide. Let's say I react it with X negative. This is your halide ion. People over here also you could have a substitution, isn't it? This could also do SN1 or SN2 depending on what R is. If this R is small, SN1, if SN2, if this is a 3-degree species, then carbocation formation will happen. Carbocation formation is better for 3-degree species, yeah, 3-degree carbocations are better. So if this alkyl is small, you would have SN2. If this alkyl is big, you will have SN1. Essentially, substitution can happen over here also. Yeah, very nice. So people, when halogens can substitute alcohols, there are some reactions like that. There you go. Kichu, so in that particular procedure, dry acetone turns out to be a better solvent compared to dry ether. In dry ether, your solubilities are different. In acetone, the solubilities match with the requirements of the Finkelstein reaction. Alrighty, so people look at this. ROH being replaced by HCl, you will get RCl plus H2O. People, can you see this reaction creates water, HCl? Generally, this hydrochloric acid is taken inside water only, right? The first reaction over here, my dear friends, this one is an SN1 reaction. SN1 reaction. So for SN1 reaction, your 3-degree halide will be better than 2-degree halide, will be better than 1-degree halide. Because 3-degree carbocation is better compared to 2-degree carbocation compared to 1-degree carbocation. So SN1 reaction. Sarvesh, very nice. So this particular reaction with zinc chloride as the catalyst. Okay. So over here we use zinc chloride as the catalyst. HCl zinc chloride, this reaction is actually known as the Lucas test. And we'll talk about the Lucas test once we begin the chapter of alcohols. Alrighty? Fine. When we replace OH with a bromine in the presence of H2SO4, you get RBr NaHSO4 plus H2O. Fine. So once again, protic solvent is there. This will provide H positive. So this will also tend to be an SN1 type of reaction. The remaining reactions that you see, where we are doing it with PX3. PX3 is basically like PCl3. Okay. So PCl3 is being taken or PCl5 is being taken. Hold on. I'll write this slightly better. Yeah. PCl3, PCl5, red phosphorescent halogen is taken, SOCl2 is taken. All of these other cases are SN2 reactions. All we are doing in all of these reactions is we are replacing the OH groups with halogens. Reagents are different. In one case we take HCl, in one case we take H2SO4 and NaBr. In one case we take PCl3, in one case we take PCl5. In one case we take red phosphorescent halogen, Br2 or I2. And in one case we take SOCl2. Reaction is the same, substitution. Reagents are slightly different from each other. So now that you understand the pattern of these reactions, remembering the reagents will not be that difficult. Alright? Fine. Now, one student over here is asking, why is SOCl2 the most preferred? Very good question. So, this particular reaction over here is the most preferred. This is preferred because alkyl halide is the main product. The side products that we get are both gaseous. Because both side products are gaseous, they leave. They are not a part of the reaction mixture anymore. Reaction is driven forward and you get pure product. So because of the formation of the pure product, this particular is preferred. Very nice. Okay. Sashwin, those metals act as catalysts basically. Whenever you have species that are not a part of the reaction, those are always catalysts. So those catalysts essentially, see, phosphorus and halogen, phosphorus halide, these will act in a very similar fashion. Okay. That's how it's going to work. Very nice. So Finkelstein reaction, Schwartz reaction, that's all done. Main chunk of alkyl halides is over, by the way. Now let's look at the case of beta elimination reaction. Beta elimination reaction. So let's take the example of the same type of alkyl halide once again. And what we are going to do over here is we are going to react it with a base. We are going to react it with a base. The most commonly used situation, the most commonly used reactant for this type of beta elimination is alcoholic, KOH. K positive, OH negative, right? So when we use alcoholic KOH base, essentially what happens in the base is, base has a negative charge, OH negative is a base, has a negative charge. So this base can capture one of these hydrogens. People, this is the halogen. Right next to the halogen is the alpha carbon. Next to the alpha carbon, we have the beta carbon. And the hydrogen on the beta carbon will be called the beta hydrogen. What we want to do over here is, we want to take the base, remove a proton, and we want to take out the leaving group also. Remove proton, take out the leaving group. Fine. What will happen? This carbon will get a positive charge. Bromine takes away electrons, positive charge carbon. Yeah. Can you see me? Yeah. All right. So bromine takes away electrons, positively charged carbons, and proton takes away electrons, negatively charged carbon. Positive, negatives combined together, and the product that we will form over here is an alkene. So if this hydrogen is removed, we will get this alkene. If the outer hydrogen is removed, what will we get? We will get this alkene. Now in beta eliminations, we observe that the more substituted alkenes are the major product. This one is minor product. So this is your more substituted alkene. This is your obviously less substituted alkene. More substituted alkenes are the major product. This rule, my dear friends, is known as the 𝒒𝒐𝒃 rule. 𝒒𝒃 rule, 𝒒𝒃 rule, same name basically, different spellings. The Russian name. So when you translate it to English, you get that jazz. Okay. So beta elimination reaction is happening over here. Generally in beta elimination reactions, heat favors the product. Okay. So heat favors elimination. Okay. And one more thing that a student is asking in the chat. So alcoholic KOH, this is basically used for elimination. And if you have aqueous KOH, this is generally used for substitution. Okay. SN1 or SN2. So alcoholic KOH will give you an elimination reaction. Aqueous KOH will give you a substitution reaction. So if I had aqueous KOH, I would simply remove bromine, put OH over there. All right. Now, are you curious why this happens? I will give this to you as a fact. It's mentioned in the NCERT as a fact. Do you know why this happens? If you want to know why, tell me. I will tell you in some time. There's a nice explanation that we have. But since we are doing a board examination class, not a JEE class, I don't want to go too deep and waste time. I will give you the reason. However, in some time, I will give you the reason. Don't worry. Promise I will give you the reason. First, let's do some more reactions. Grignard reagent, organometallic. You call this Grignard, but it's a French name, so Grignard is a better pronunciation. So what happens if I start with an alkyl halide? I'll give you specific examples also. And if I react it with magnesium in the presence of dry conditions. Dry means we don't want water. So if we have dry conditions, the solvent that works best for this reaction is an ether type of solvent. Okay. Ether type of solvent works best for this particular reaction. So alkyl halide is taken with magnesium in the presence of dry ether. The species that we get out of this looks something like this, RMgX. My dear friends, there is a bond between the carbon and magnesium. Yeah, there is a metal versus carbon bond over here, and therefore we call it an organometallic reagent. Fine. So on the other side, you will have something like Cl or Br. So right side, this particular bond between metal and halogen is an ionic bond. Okay, this particular bond is an ionic bond. But on the left hand side, this particular bond is a covalent bond. Carbon's electronegativity is 2.5, magnesium's electronegativity is 1 point something. So the thing is, metal is less electronegative over here, carbon is more electronegative, and therefore in this covalent bond, carbon has the negative character, magnesium has the positive character. And if something has a negative character, my dear friends, what will happen? This particular area, this guy can act as a base or a nucleophile. This carbon with a negative character can act as a base or it can act as a nucleophile. I will explain to you what a base or a nucleophile is. What's the difference between base and nucleophile? I will explain it to you. So, a certain example that we can take over here for Grignard reagent is, let's say CH3Cl reacts with magnesium in the presence of dry conditions and ether. What will we get out of this? We will get CH3Mg sorry, not Br, Cl. CH3MgCl. Alrighty. If I start with this type of a species, I start with chlorobenzene, or let's start with bromobenzene. I react it with magnesium, again in the presence of dry ether. I would get phenyl magnesium bromide. Phenyl magnesium bromide, and the carbon part in both of these cases can act as a base or it can act as a nucleophile. Alrighty, now let's clarify your doubts. First of all, can you tell me what is the difference between the base and a nucleophile? My dear friends, base means I want to capture a proton. Base means I want to capture a proton. So when OH negative captures H positive, base. When NH2 negative captures H positive, base. When C negative captures H positive, base. Okay. So for example, what if I react CH3 MgBr with an H positive? What will happen over here? What will happen over here is the carbon will simply attack the hydrogen, because positive charge, negative charge, the product that you will get over here is CH4 plus whatever you want to get on the side. Whatever. This is CH4. Alkane, methane is formed. What if I attack as a nucleophile? Yeah. What if I attack as a nucleophile? In a nucleophile, we attack a carbocation or we attack a carbon with a positive character. SN1 reaction, SN2 reaction. So people, you can in fact do this. If I react CH3Mg with, let's say, another CH3Br, you can do this theoretically, this is possible. SN2 type of attack is possible over here. And the product that you will get will be ethane, CH3 bonded to another CH3 plus whatever are the side products. Base versus nucleophile, we understand. Now the thing is, acting as a base is very easy and very fast. Why? Because H positive is this tiny little species. You can easily capture it. But capturing a nucleophile, capturing a carbon, this is going to be difficult. This is going to take time. Easy, difficult. So now can you understand why we keep dry conditions? Why do we keep dry conditions? We keep dry conditions because if by chance, if by chance my Grignard reagent comes into contact with water, this is your phenyl ring, benzene ring. If by chance it comes into contact with water, quickly C negative will capture H positive from here. And you will get PHH is what? Basically, you will get the alkane back again. Useless. Somehow with great difficulty I created PHMgBr, and then once again if I go back to the alkane, what's the point of the reaction? So that is why we do the reactions of Grignard reagents under dry conditions, because as soon as this guy comes in contact with water, it's going to make an alkane and reverse all your effort. Imagine you started with alkane, you did free radical halogenation, you got the chloride, you reacted with magnesium in dry conditions, got something else, then you start this, do more reactions, but someone puts few drops of water, done, back to alkane. So that's why. So why do we choose ether? Why not any other solvent? Because ether over here is an inert solvent. Ether dissolves everything but does not react with anything. In this case, if I take acetone, the Grignard will start reacting with acetone. I will show you that reaction. That is a part of our syllabus only. So ether over here is an inert solvent. So what are the kind of ethers that we use generally? Some common ethers that we can use, my dear friends, are diethyl ether. So this is your diethyl ether. Similarly, you could have dimethyl ether where you have, CH3s on both sides. One more common ether is this one, the cyclic ether. Oxygen with 4 more carbons. So this particular species is known as tetrahydrofuran. Tetrahydrofuran, also abbreviated as THF. So these are some of the ethers that are used as solvents. These are inert solvents. They don't react with anything which is in the reaction. Nice. So Grignard reagent. And now let us look at the uses of Grignard reagent. Let us look at the uses of Grignard reagent. First of all, what we can do is we can prepare alcohols via the Grignard reagent. Okay, so how can we prepare alcohols via Grignard reagents? Let us understand this. We can start with any random Grignard reagent, let's say RMgX, and we can react it with an aldehyde. Let's start and react this with an aldehyde. So simply let us take ethanol. My dear friends, do you realize over here in this particular structure, oxygen will have the negative character, carbon will have the positive character? Why? Because oxygen is more electronegative, carbon is less electronegative. So this carbon has positive character, and we already know that this carbon has negative character. What's going to happen? Negative positive will attract each other. Look at the movement of the electrons. The carbon attacks this positive charactered carbon, but now we need to create space on this carbon. So oxygen can pull this double bond towards itself. After this, what will happen? Oxygen will carry a negative charge on it. This alkyl group that has transferred is sitting over here now. And for the meanwhile, we want to do this reaction in dry ether conditions. Because we can't do it in wet conditions. No, if we do it in wet conditions, then this will react with water directly. So dry conditions, we do this reaction. Oxygen carries a negative charge, alkyl group associated with the carbonyl carbon. Okay, this carbon is known as carbonyl carbon. This CH3 was already there, very nice. For the meanwhile, since the conditions are dry, this remaining MgX, okay, will sit over here. Right now, this is an ionic species. So first step you do in dry conditions, once this is formed, then we can throw this into water. So finally you throw that in water, and then what we get is RCCH3. This already has one hydrogen, which we don't draw in the bond line formula, but it has a hydrogen, and this oxygen will be converted to OH, because this O negative captures a proton from the solvent, water, and on the side you will get MgOH whole twice plus HBr, but all of this will be ionic in nature, so you don't need to worry about the species. You'll have Mg positive inside water, you'll have Br negative inside water only. Sanjay SK is saying, guys, this is pre-recorded. Yes, Sanjay, this is pre-recorded. I recorded this back in the year 1948. 1 year after we got the independence, I recorded this particular class because I knew that in the future, 2025, you will need the class for board exams. So yeah, pre-recorded. Sundar Rajan, we'll come to the HVZ reaction in carboxylic acids chapter. Yeah, Sundar? HVZ reaction in carboxylic acids chapter. All right, anyway. So this was one of the use of Grignard reagent. My dear friends, what kind of alcohol is this? This is a 2-degree alcohol, right? Because the carbon of the alcohol is associated to 2 more carbons. So what if we do this reaction with a ketone? Let's say I take PHMgBr and I reacted with acetone. First of all, in dry ether conditions. So the first thing that's going to happen is the phenyl group will attack this carbon, oxygen will pull electrons toward itself, and we will get PHO negative, and then once you throw it with water, once you quench it with water, you would get this species. This is a 3-degree alcohol. So Grignard with aldehydes can give us a 2-degree alcohol. Grignard with ketones can give us a 3-degree alcohol. Similarly, if I react Grignard with formaldehyde, let's say you react CH3MgCl with formaldehyde. Yeah. What's going to happen over here? Eventually you'll get a 1 degree alcohol, right? So over here you have hydrogen, hydrogen, you got CH3, O negative, put it in water. Final product is CH3, CH2, OH. 1 degree alcohol. Fine. So, my dear friends, depending on the starting material, you can get 1 degree, 2 degree or 3 degree alcohol using Grignard reagent. Okay. Cool. So, these are your reactions with Grignard reagents. One more reaction that we have with Grignard reagent, let's also do that. So, people, what will happen if I react any RMgX with CO2? What's going to happen over here? Again, this alkyl group will attack the carbon, oxygen will pull electrons towards itself, and what you will get here is RCO negative, double bond O, and for the meanwhile you can stabilize it with the MgX. And once you throw this in water, what are we getting, people? Once we throw this in water, the main product that we are getting is RC double bond O, single bond OH. We got a carboxylic acid. So Grignard reagents can be used to synthesize carboxylic acids as well. All right. Very nice. So this is also one use of Grignard reagents, and technically we are in the chapter of haloalkanes, but we already studied about reactions of preparations of alcohols. We studied about reaction of preparation of acid. So don't worry about the speed of the class. Organic chemistry needs attention. I'm going faster than usual only. But if you have patience, we'll be able to cover all of organic. And eventually, we will cover all the chapters. And once we are in the later chapters, we'll increase our speed. Initially, we need to understand the ideas behind base, nucleophile, etc., etc. Once we understand mechanisms and everything, then later it will become much faster. Okay, that's how it's going to work. Now, one more very important reaction where we need to understand mechanism. Two more reactions where mechanism is very important, then things will become even faster. Okay, so let us now look at the reaction of electrophilic aromatic substitution. And those of you who want me to do previous year questions of board exams, I will do that also. Everything will be done. It's a marathon type class. Just need some patience from you guys. All right. All right. So what's about electrophilic aromatic substitution? We start with an aromatic species. Let's say we start with benzene. Now on to benzene, what we want to do is we want to associate an electrophile. Electrophile means something that wants electrons, something that already has a positive charge on it, right? So my dear friends, the mechanism over here is very simple to understand. Take one of these pi bonds and polarize it on one of the carbons, capture the electrophile. What do we get over here, people? We will get a species that looks something like this. Since we've pulled electrons away from this carbon will get a positive charge. This is the reactive intermediate. It's a carbocation intermediate, but since it is a fancier carbocation, not a simple carbocation, we call this an arenium ion. Okay, we call this an arenium ion. Okay, so because this is an arenium ion, and you see that we've lost aromaticity over here, we had aromaticity, we lost aromaticity. How do we regain aromaticity over here? Notice every carbon has a hydrogen. This carbon also has a hydrogen. What you can do simply over here is take these two electrons, put it on carbon, remove the H positive. Okay, so over here you lose the H positive, and once again This carbon will get negative character, this has positive character. You get your benzene back. Electrophilic aromatic substitution. Right? Electrophilic aromatic substitution. My dear friends, do you realize that electron releasing groups will make this reaction faster? Electron releasing groups will make this reaction faster, isn't it? So, my dear friends, electron releasing groups will be called activating groups. What if I have the opposite case? Electron withdrawing group. Why will this make the reaction faster? Electron releasing group will give more electrons to benzene. More electrons with benzene, more attracted is the electrophile. This guy needs electrons, right? If I release electrons in benzene, this will be more attracted. If I take electrons away from benzene, this will not be very attracted. So electron withdrawing group will slow down the reaction. So such a case is known as a deactivating case. Electron releasing groups are activating, electron withdrawing groups are deactivating in nature. Now, this electrophilic aromatic substitution is there in all the chapters. It is there in alkyl halides, phenols, it's there in amines. Every chapter you will have electrophilic aromatic substitution. So, understanding it is important. My dear friends, do you remember that OH group, this OH group is a plus M group? Remember plus M effect, mesomeric effect, do you understand? Yeah. So this one has a plus M effect over here. How does the plus M work? Just a little bit of analysis we'll do so that later on doing these reactions faster is easy for us. So my dear friends, what happens in the plus M effect is that this lone pair is in resonance with the benzene ring. Yeah. So what we will get over here is something that looks like this. We can delocalize this negative charge further, and another structure will look something like this. Negative charge over here, delocalize it even further, you will get the next structure which will look something like this, and eventually if you move this back you will get another structure of the phenol itself, right? These are the resonating structures. My dear friends, do you notice that the negative charge is coming on this carbon right now? Negative charge is coming on this carbon. Negative charge is coming on this carbon. The negative charge is delocalizing only on the ortho and para carbons, right? So ultimately, if I draw the hybrid of this particular case, if you don't know what is hybrid, please revise general organic chemistry once later on. Pi electrons are delocalized. These pi electrons are also delocalized. And we understand that oxygen carries some positive nature on it. The ortho carbons carry some negative nature on them. And the para carbon also carries a negative nature. So people, if an electrophile were to approach this particular species, yeah, if an electrophile were to approach this particular species, where would it go? The electrophile would either be attracted to the ortho positions, it can go that side also, or the para position. Yeah. So people, what we need to understand over here is that plus M groups are going to be ortho-para directing in nature. All the plus M groups on benzene will act as ortho-para directing. Similarly, if I have a minus M group, what's going to happen? Can you tell me? I'm sure a lot of you know this already. In the case of a minus M group, I'll simply make the hybrid for you. Let's say we have NO2, okay, and this is what the hybrid will look like for benzene. This will have negative character, positive character here, positive character here, positive character here. So overall, it has deactivated this ring. Electrophile does not like to come close because there are positive charges on the ring now. But if I force the electrophile to react, electrophile will be attracted to the meta position because ortho-para positions have positive charges on them. So any minus M group that we have will be meta directing. All right. So what are the examples of some plus M groups? OH group, NH2 group, species with single bonds and lone pairs essentially. Minus M groups are like NO2, COOH group, CHO group, C double bond O single bond R or ketone group, C double bond O ketone type of group. On that side, I can also put your ether type of group. Yeah. So in our syllabus, in board examinations, we have electrophilic aromatic substitutions for phenol, for aniline, for anisole esters. We have those type of cases, okay? We have electrophilic aromatic substitution in our chapters for benzoic acid, for benzaldehyde, for acetophenone, etc. So that is why I was revising this entire thing for you, because now that part will become easier. Acha. What about halogens? My dear friends, for halogens, if you remember GOC, their minus I dominates and they have a weak plus M effect. Okay. For halogens specifically, they are electron withdrawing in nature because of the inductive effect. But because of their lone pairs, they have a very weak resonance also. So because of the combination of these two effects, halogens are deactivating in nature. Okay, halogens are deactivating, but they are still ortho-para directing in nature. Because of the combination of effects that halogen has, strong minus I and weak plus M, it is overall a deactivating group for electrophilic substitutions, but at the same time, it is ortho-para directing. Nice. So this was about your electrophilic aromatic substitution. So we'll see multiple cases of electrophilic aromatic substitution. For example, if I start with, let's say, benzene ring and I add to it Cl2 in the presence of any Lewis acid. What's going to happen over here, people? Can you tell me what's going to happen? So a Lewis acid could be something like AlCl3 and this is your Cl2. So what will AlCl3 do? AlCl3 will attract electron pair towards it. This will give you AlCl4 negative and Cl positive. This is your electrophile now. So your benzene and electrophile will combine together to give you chlorobenzene. Formation of haloarine. This is called haloarine. Arine means aromatic species. Alrighty, very nice. This reaction can also be done simply with Br2 in the presence of FeCl3, or this reaction can simply be done in the presence of chlorine and iron, or this reaction can be done in bromine and iron. All these cases will give you halogenation on the benzene ring. Okay. All these cases will generate the halogen as the electrophile. Very nice. So these were your electrophilic aromatic substitutions. Last reaction for the haloalkanes chapter is the nucleophilic aromatic substitution. Okay, you replace a nucleophile with an existing leaving group. Okay, so this is a very tough reaction. This is a very difficult reaction. Very difficult to do. See, chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin. Extremely hot. In fact, at this temperature, this NaOH is basically melted or fused. And you see pressure of 300 atmosphere. 300 atmospheres of pressure. Extreme conditions. So you take chlorobenzene in extreme conditions and then you get phenol. Okay, so first thing that happens over here is, since this reaction is happening at very high temperatures, you will get the phenoxide ion first, O negative, Na positive. This is what happens, and then finally you give it some H positive. So after you give it H positive, you will get your. So replacing this with a nucleophile is very difficult. You see how difficult the conditions are. Can anyone name what this process is? This process, my dear friends, is known as Dawes process. This is known as the Dawes process for creation of phenol. You will see this reaction once again in phenol, part of the NCERT also. Okay. So, Dawes process. How do I make this process easier? The presence of an electron withdrawing group at ortho and para positions increases the reactivity of this. Let's see. Para nitro chlorobenzene, temperature is lesser now. I don't need 623 Kelvin, only 443 Kelvin is okay. Nice. If I put two nitro groups, even lower temperature, I get the reaction. If I put three nitro groups with just warm water, I don't even have to heat it up much, just warm water, you will get the substitution. So these electron withdrawing groups or these minus M groups will make this reaction easier to happen. Okay. The effect is pronounced when NO2 group is introduced at ortho and para positions. However, no effect on reactivity is observed by presence of electron withdrawing group at meta position. Because we saw, right, at meta position, you don't have the effect of resonance. Yeah. Can you see? On meta position, there is no effect of resonance. On meta position, there is no effect of resonance. So what we can keep in our mind is meta, no, meso. Meso stands for mesomeric effect. On meta positions, we don't have any influence of mesomeric effect. Nice. Okay. Robin, I'm trying to cover like 90% of the topics. Okay. So, people, this is how this nucleophilic aromatic substitution works. Now, the mechanism of this is mentioned in the NCERT, so they can ask this to you in board examinations. Let's look at the mechanism once. Let's try to understand the mechanism once. let us take the para-nitro case. This is your chlorine over here. And what we will do is we will try to attack an OH negative on this particular carbon. If OH negative attacks over here, the bond has to be polarized. My dear friends, the first species that you get will look something like this. And you have this OH negative. Now, can you observe this negative charge will be stabilized by the nitro group? This negative charge will be stabilized by the nitro group. Let us understand how. Let's simply try to make a resonating structure. Just one quick resonating structure we'll draw so that we understand how this is stabilized. So negative charge goes over here. This guy goes over here. Oxygen pulls the electrons towards itself. One resonating structure that I can draw is something that looks like this. Yes. Just one mistake that I've done over here. Okay. Observe, people, please. Observe. Because of the presence of a minus M group at the ortho or para positions, the intermediate formed in this reaction is stabilized. This intermediate is also known as the Meisenheimer complex. Okay, it is known as the Meisenheimer complex. Fancy name. If you remember it, great. If you don't, then that's also fine. But because of the presence of these minus M groups at ortho and para positions, the nucleophilic substitution will become easier. Now, from here, all you need to do is lose the Cl negative, remove the Cl negative, and you will get your final product. That is obvious. You remove chlorine, you get this benzene back again. Very nice. Cool. So that's how this particular reaction works. So they can ask you, the question that can be asked is, chlorobenzene reacts with NaOH in extreme conditions to form phenol, but trinitrochlorobenzene reacts with warm water to create phenol. Explain why. Why does the electron withdrawing group make this reaction faster? Explain why. You will explain by making this particular diagram. Alrighty, very nice. So now what we can do is we can move to some questions, some previous year questions. Let's solve some previous year questions, then I will give you a break, don't worry. After 2 hours of the class, I will give you a break. It's fine. Let's do some previous year questions. See, till now we've been doing a lot of reaction. Let's apply those reactions now. Once we apply the reaction, it will be easier for us to realize we are doing something good. Application is important. So let's look at this particular case. Write the main product formed when. This was a 2023 question. Methyl chloride treated with sodium iodide and acetone. Finkelstein reaction. You have done this reaction. CH3Cl plus NaI in the presence of acetone gives you CH3I plus the NaCl that is formed here. Precipitated. Very nice. Finkelstein reaction. 2,4,6 trinitrochlorobenzene is subjected to hydrolysis. Just now we did that, isn't it? So this one is chlorine, NO2, NO2, NO2. We put it inside warm water and very easily, because of the multiple electron withdrawing groups, our chlorine is replaced. by phenol. Nice. Picric acid. Okay. N-butyl chloride is treated with alcoholic KVH. So what is N-butyl chloride? N-butyl chloride means this one. Butyl chloride treated with alcoholic KOH. Beta elimination. Done. Boards. Boards are easy. All you need to do is write neat and clean. Yeah. All we need to do in board examination is write things neat and clean. Look at this. Once again, 2023 board paper question. First of all, we have CH3, CHOH, CH3 with PCl5. My dear friends, what will happen in the first reaction? This is reaction A. We'll do it over here. So we have propanol reacting with PCl5. OH will be replaced by chlorine. Substitution reaction. Now the next reaction is AgCN. This I didn't tell you, maybe you know this already. I will revise that idea for you. AgCN versus KCN. My dear friends, when AgCN reacts with an alkyl halide, the nitrogen acts as the nucleophile. Okay. Nitrogen acts as nucleophile. Why does nitrogen act as nucleophile? Because silver and carbon are strongly bonded via a covalent bond. Okay. Silver and carbon over here are bonded by a covalent bond. So carbon is not free to attack. Nitrogen is free to attack as the nucleophile, and the final main organic product that you get is going to be RNC. This is known as your isocyanide. Okay, it is called isocyanide, also known as isonitrile. So AgCN gives you isocyanides or isonitriles because carbon is not available for nucleophilic attack. Alright. On the other hand, K positive, Cn negative. So we've got alkyl halide, and then carbon has the negative charge. Why? Because this is an ionic species. So carbon attacks the carbon, halogen will leave, you will get RC triple bond N. You will get nitrile, or you can also call this cyanide. Okay. So this is how silver cyanide is different from potassium cyanide. This difference might be asked in the examination. Explain difference between AgCN and KCN. Can be asked like that also. So NC isocyanide. Right? So this is how this works. Very nice. Asha, this first question we've already done. The cyclopentane case. Let's look at the next question in this passage. Arrange the following compounds in increasing order of SN2 reactivity. Can we do that? First we have 2-bromopentane, 1-bromopentane, 2-bromo-2-methyl-butane. So my dear friends, this is a 2-degree species, this is a 1-degree species, and this is a 3-degree species. You know, 1 degree, more than 2 degree, more than 3 degree for SN2 reaction. Nice. Previous year questions. Simple. No rocket science at all. SN2 basically is 1 degree, more than 2 degree, more than 3 degree, because SN2 we want to avoid steric hindrance. Cool. Gokul, I'll come to your question also. Look at this. Gokul, we will do that question in alcohols chapter, bro. Okay. Why para dichlorobenzene has higher melting point than that of ortho and meta? You were asking me about physical property. Let's think about this. Para dichlorobenzene, chlorine and chlorine, has higher melting point compared to the ortho and meta isomers. Chlorine and chlorine. Can anyone tell me what the answer is? Ashish, that's good, man. Yes, people, can you tell me what is the answer? Let me see if you guys know the answer. I will explain, but can you tell me the answer? Very nice. Very nice. Very nice. Sukuti and Nitik have given the answer. Gokul, very good job. Very good job, people. So, this is mentioned in the NCRT directly. Let me show it to you. It says that the symmetry for that para case is very good. So, we'll go to the, you can see. Look at the melting point of this case. When it comes to boiling points, these are very similar boiling points, okay? But when it comes to the melting point, the para position melting point is quite higher compared to these two. Why is that so? Because the symmetry gives us a very good, this one. Here's the statement. Due to the symmetry of para isomer, it fits very well in the crystal lattice. Crystal lattice means solid state structure. Solid state will be a crystal only, no? So in the crystal, the para isomer sits on top of each other very well, has very good crystal lattice, very good packing efficiency, therefore the melting point is higher. Okay? Fine. All right. Roshan, bro, just have a look. The halogen's carbon is connected only to one more carbon, so 1 degree. Halogen's carbon is connected to 2 carbons, so 2 degree. Halogen's carbon is connected to 3 more carbons, so 3 degree. That's how we look at 1 degree and 2 degree and 3 degree. Okay. Do this one, people. Simple Grignard reaction. Identify and be in the following. So first, what we will do? We will simply replace the bromine with MgBr. But what happens when we simply put water into it? Huh? If we simply put water, then what's going to happen, people? Grignard will not react as a nucleophile anymore. Grignard will act as base. And very quickly, get cyclobutane. Great. Very, very good. Racemization occurs in. Racemization means we form a racemic mixture. Where does that happen? Racemic mixture forms in SN1 reaction. Okay. All right. Gokul, think about the dipole moment. Gokul, dipole moment will be the highest in ortho case and therefore the boiling point will be the highest in ortho case. So in boiling point, dipole moment matters. Yeah. In melting point, crystal lattice matters. So for crystal lattice symmetry, for boiling point, you look at the dipole moment. So that's why Gokul, dipole moment is more. Achha. Which of the following is not true about enantiomers? All of these are 2023 board CBSE questions. Some are subjective, some are objective, but all are board questions only. Which of the following is not true about enantiomers? Same density, yeah, physical properties are same. Same boiling point, yeah, physical properties are same. Same specific rotation. They have same chemical reactivity. Do they have same specific rotation? No. One will be clockwise, other will be anti-clockwise. One will be clockwise, other will be anti-clockwise. Yes, they have same chemical reactivity. This statement is only partially correct. Okay, when it comes to chemical reactivity, this statement is partially correct. For board examination, it is correct, but practically it is partially correct because one chiral compound with another chiral compound will react in one manner. This chiral compound with another chiral compound will act in another manner. Okay, so chemical reactivity, technically speaking, is different, but for board examination, you can say it is same. Okay. Gokul, so ortho and meta are basically similarly symmetrical. Yeah, ortho also has a plane of symmetry in the middle, meta also has a plane of symmetry in the middle. So that just comes to experimental evidence. In some compound, the ortho might be higher melting point, in some compound, the meta might be higher melting point. Cool. So that depends on the experimental evidence. So you don't need to worry about the difference between those two. Acha. Let's do this question, people. An alkyl halide A of molecular formula C6H13Cl on treatment with alcoholic KOH gives you two isomeric alkenes B and C of molecular formula C6H12. Both alkenes on hydrogenation give 2,3-dimethylbutane. Write the structure of A, B and C. Try this. What is the ending compound over here? 2,3-dimethylbutane. This is what we have as 2,3-dimethylbutane. So now what it says is an alkyl halide of that molecular formula on treatment with alcoholic KOH gives two isomeric alkenes B and C of molecular formula C6H12. And both of them on hydrogenation give you that particular structure. What could be the original halogens? Let's think about the alkenes first. I can have this alkene. I can also have this alkene. If I hydrogenate this alkene, I will get this structure. If I hydrogenate this alkene, once again, I'll get this structure. Very nice. So now I need to figure out what was my original structure, which after elimination gives me both of these alkenes. What would be the original structure? Original structure could be this particular case. If you eliminate it outside, you get one of the alkenes. If you eliminate it inside, you will get the other alkene. Right? Done, people? So, this over here is your structure A. This is B and this is C. In board examination, just to be careful, just to make sure you get marks, instead of making bond line notation, you can write the structure like this. We're doing bond line notation so that we are faster in our process right now. But for your examination, just to be safe, I would prefer if you draw this. Because board examination teachers are weird. They want you to draw the full structures most of the times. Alrighty. So that's how this particular case works. Let's look at this question now. Let's look at this question. Benzyl chloride is highly reactive towards SN1 reaction. Why? This is a good question. You have to explain the reasons of all of them. Let's look at the first case. My dear friends, benzyl chloride looks like this. In benzyl chloride, you have one more carbon after benzene. So you can draw it this way. CH2Cl. So my dear friends, in the case of SN1 reaction, what happens? In SN1 reaction, my halogen leaves and it gives me a carbocation. Make the carbocation, please. right? Now, this is a stable carbocation, right? This is a resonance stabilized carbocation. So, how will you write the answer in board exam, people? You will write this reaction, and then under this reaction, you will give the reason properly. So, how will you give the reason? You will give the reason that this particular structure, which is benzyl chloride on SN1 reaction gives benzyl carbocation as the intermediate. Okay. And then you keep writing that this carbocation is resonance stabilized, it is delocalized by the benzene ring. That is why, because of stable carbocation formation, it is good for SN1 reaction. You have to write all those statements. So, in board examination, you have to be patient. You have to write things in proper languages, neat and clean. So make sure you write things down carefully in the board examination. Please don't hurry too much. This is not Instagram. This is board examination. Take your time. Okay. Next question says, plus minus butane 2-ol is optically inactive, though it contains a chiral carbon atom. Okay. Butane 2-ol, chiral carbon. How? Look at this plus minus sign. Okay, plus minus sign. What does this mean? Plus minus sign means that this entire thing is a racemic mixture. Plus minus sign means that we have a racemic mixture. So first of all, we will tell the board examination people that racemic mixture is a 50-50 or 1:1 mixture of both enantiomers. Yeah, it's a 50-50 mixture of both enantiomers. One of the enantiomers will rotate light in the clockwise direction, but the other enantiomer will rotate light in the anti-clockwise direction. Since both of their rotations cancel each other out, overall the racemic mixture is optically inactive. Okay, so racemic mixture is overall optically inactive because one enantiomer compensates for the other one's rotation. This phenomena is also known as external compensation of rotation. Okay, this is just a fancy terminology for this phenomena. External compensation of rotation. Right? Sanjit, yeah, that's a good way to write it down. So writing things down is what matters in our board exam. Dopamine detox, because your board examination is going to be in English, bro. Yeah. Alrighty, so that's that. These were some reactions of your alkyl halides, previous year questions. Very good chapter. And with this chapter, we have covered some reactions of alcohols also, some reactions of aldehyde ketone also, some reaction of acids also, and we've understood some very important mechanisms also. So now, once this alkyl halide chapter is done, next we want to move to the chapter of alcohols. And now you will realize how easy it is for us to move forward because basics we have covered. So, My dear friends, up next in this class only is the chapter of alcohols, phenols, and ethers. And because you guys have been studying with me for 2 hours straight, I will give you a 5-minute break. All right. Since you guys have been such good students, I'll give you a 5-minute break. I'm just writing 5 minutes, it'll extend till like 7-10 minutes. So take a little break. I'll also have some tea or coffee, whatever is available in the office. And then I'll come back. We'll start with alcohols, and really you'll realize how easy it is now to do all the rest of the chapters. So, little break. In the meanwhile, let me play a song for you guys if possible. Just a moment, I'll upload that song into the streaming software. Got it. All right, people. What's up? Atif, yeah, that's the plan, bro. Tanwar, yeah, man, this lecture should be pretty good for boards. But apart from this lecture, if you can focus on reading and revising the NCRT, that would be really nice. Yeah. So let's have a little bit of 2 minute chit chat with each other, and then we'll resume and get to the chapter of alcohols, phenols, and ethers. So most of the things, chemical reactions, majority of the chunk we will cover today. We will do alcohols, phenols, ethers, aldehydes, ketones, carboxylic acids, amines, and biomolecules, everything. So it will take time. It's not going to be a quick run and done kind of class. It's a marathon. But this is going to be the longest marathon because organic is the longest of your portion. So physical properties and all we'll discuss here and there. We'll have a look at them. Generally, the idea is more dipole moment, more boiling point, better packing efficiency, better melting point. That's the main idea. And bigger species tend to have higher melting and boiling points. So if you compare, let's say, octane versus methane, methane will have low melting boiling points, octane will have high melting boiling points. That's the basic idea behind any physical property. Wherever specific cases are important, we will discuss those. Cool. Perry, so yeah, physics was a little unexpected this year around. I am hoping chemistry will not be that difficult because chemistry can't be made extremely difficult anyway. But if you're listening to me carefully and if you have read the NCRT or if you will read the NCRT whenever you get the time, then I don't think it should be very difficult for you. The final paper. Cool. Dark side, you never know, man. Kichu, I will reduce the slow mode now because people, the number of students are not as much as they were earlier. So I'll reduce the slow mode, but I will not remove the slow mode because then these beautiful creatures we call spammers will wreak havoc in the chat. Anbu is saying, please teach faster. I'll try to do the best I can. I am limited by the fact that I'm a human. So there's only a certain amount of speed that I can maintain. Although, if you find the live session to be too slow for your liking, then you can watch it later at 2x speed at night. Right. So I'm going to try it the best I can. Ryan, that song is called Diggy, D-I-G-G-Y, by Patrick. That's the artist's name. So that's a copyright-free song that I've been using for a long time in my classes. Yeah. Nico has asked a very good question. Nico is saying, so after this class, what should we do about the organic chemistry portion? NCRT. Read NCRT, solve previous year questions of boards if you want. NCRT is mainly what's important. All right. Yugant, yes, of course, bro. Atif, why would I have it? Gokul will do that towards the end of alcohols, bro. All right. Ethanol to bute 1-ine. Ritvik, that's a very good question, man. I don't have a clear-cut answer to it. It's a long discussion that I need to have with you. But yeah. Kumar Koki is asking, sir, from which state are you? Bro, I'm basically from Punjab, but I was brought up in Himachal Pradesh, studied in IIT Bombay, so Maharashtra, and then I've been in Bengaluru for the last 10 years approximately, so Karnataka. and then I keep visiting Tamil Nadu whenever I want to chill. Yeah, so I keep going to Ooty and Kotagiri. I've been to Ooty and Kotagiri like 20 times, and I've been to a lot of places in Tamil Nadu. So I am a national citizen of this country, not from one specific state. Okay. Anyway, so where did that slide go? Break is over. Let us come to alcohols, phenols, and ethers. So, my dear friends, what are alcohols? Alcohols are essentially species with OH groups. Phenols are aryl species with OH groups. Aryl means aromatic, and ether means you have an oxygen, trapped in the middle of two carbons. So, how do we add H2O on an alkene? Same as HBr addition. Think about it. If we start with a propene and we add H2O on it, this reaction is generally done in the presence of acids, acid catalyzed reaction. So what you can do over here is same thing. Capture the proton, you will form the carbocation, and the OH negative will attack the carbocation. You will get the more substituted alcohol. So this will follow the Markovnikov rule. Can you see how simple this becomes now that we've seen literally the same reaction for HBr? Yeah. Old monk Mano. See, nomenclature questions won't be asked directly, and while we are doing these questions, we'll know about nomenclature also. Like this compound is called propane to oil, right? So you don't need to worry about nomenclature. I'll keep telling you names for specific compounds wherever necessary. Basic nomenclature, I hope you know from 11th class itself. Very nice. So this is known as acid catalyzed hydration. Simple reaction. Let's move forward. So the next reaction is going to be hydroboration oxidation. See, the thing is, in this particular case, I got this as the major product, the more substituted alcohol as the major product, the less substituted alcohol was the minor product, right? What if I want this as my major product? Then what would I do if I want this as the major product? So in that case, the reaction that we use is known as hydroboration oxidation. So we start with BH3, right? So we will take any alkene. Once again, let's take the example of propene. And what you want to do is you want to react it with BH3. I'll discuss a little bit about BH3 in a while. So how BH3 adds onto this double bond is you can imagine it adding like this, BH2H. For steric hindrance reasons, boron adds on the outside, hydrogen adds on the inside. So if you imagine this kind of an addition happening over here, can you see you would essentially get a BH2, this type of a thing, right? Can I call this RBH2? I hope you guys are smart enough to understand that this entire thing can be represented as RBH2. This is the alkyl group, this is the BH2. Now this RBH2 can add on to this propene. This RBH2 can add on to propene once again. How is that going to happen? Propene, you have your BH. Yeah, can you see? Once again, this boron is going to add on to the propene. So after this addition, we will get R2BH. And after another addition of this onto propene, I will get R3B. Can you understand from here to here the idea that this BH3 adds 3 times onto the alkene? Now, once this trialkyl boron species is formed, we will oxidize it. So that triboroalkyl species essentially looks like this. We've got 1, 2, and 3 carbons on all sides of this boron. What we want to do is we want to add H2O2 to oxidize all 3 of the chains. All 3 of these chains have to be oxidized. So how does this H2O2 add? Basically, you can imagine something like this. This oxygen will go over here on this carbon and the other oxygen will go and sit with boron. So when these things combine together, what you will get 3 molecules of this 1 degree alcohol, propane 1-ol, you will get 3 molecules, and you will get BOH whole thrice. This BOH whole thrice can also be written as H3BO3, boric acid. Okay. Sudan, did you join from the beginning or not, bro? Sudan, if you joined late, then this will be difficult for you. Please watch the class from the beginning. Alrighty. So, diborane BH3 whole twice, and I'll talk to you about why we call it diborane, reacts with alkenes to give trialkyl boranes as addition products. This is your trialkyl borane. Now this is oxidized to alcohol by using hydrogen peroxide in the presence of aqueous sodium hydroxide. So this is done in the basic conditions. Under basic conditions, you oxidize this trialkyl borane into your final product. Yeah, this is your anti-Markovnikov product. All right. So that's how this works. Hydroboration, oxidation. So I told you I will talk to you about BH3. My dear friends, do you realize that BH3 is an incomplete octet species? Yeah. It has a vacant p orbital, if you notice carefully. So this BH3 essentially acts as a Lewis acid. All right. BH3 acts as a Lewis acid and it can accept electrons. So there are multiple things that it can do. BH3 can either exist as a dimer which we call diborane, and the structure is a little more complicated. You don't need to worry about the structure of diborane because it's not in the syllabus anymore. So you can exist as a dimer, or you can add an ether like THF onto the boron of BH3. So this particular species is also known as BH3 THF. Yeah. The lone pairs of the oxygen in tetrahydrofuran go and sit in the vacant p orbital of boron. Okay. So these are different ways in which BH3 can exist. So that's why over here, instead of simply writing BH3, they call it diborane. Okay. Yes, it does have a banana bond, but that's not in the syllabus at the moment, so we don't need to worry about it. Very nice. So that's how your hydroboration oxidation works. So we have Markovnikov addition of alcohol and we have anti-Markovnikov addition to create the alcohol. Very nice. Next, if we reduce aldehydes and ketones, we will get alcohols. Let's read this passage and then write the reactions. Aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalysts. Catalytic hydrogenation can work. Usually, your finely divided metals such as nickel, palladium, platinum is used. So what we can do is, if we have R, C double bond O R dash, random ketone, I can hydrogenate it in the presence of metal catalysts, platinum, palladium, or nickel, and the hydrogen will go and add on to the sp2 carbon. So R, C, H, R dash, OH. we get an alcohol. So one of the ways of reducing aldehydes and ketones to alcohols is by doing hydrogenation. This is one of the ways. What's the other way? Other way is it is also prepared by treating aldehydes or ketones with sodium borohydride NaBH4 or lithium aluminium hydride LiLH4. Aldehydes will yield primary alcohols and ketones will give secondary alcohols when treated with LiLH4 and NaBH4. People, what is NaBH4 and LiLH4? These two are hydride providing reagents. Okay, these are hydride providing reagents. How do they provide hydrides to you? Think about it. What we have here is aluminium. Aluminium usually wants to make 3 bonds, but we've made 4 bonds with hydrogen. Now, aluminium's electronegativity is lower than hydrogen, metal hydride. Therefore, the hydrogens over here will carry negative characters on them. And what's the overall charge on this species? The overall charge on this species is a negative charge. But this negative charge has to be stabilized, ionic species, so that is why we take Li positive on this side. What this does overall is one of the hydrogens can be used as H negative. One of the hydrogens can be used as H negative for the reaction. Same with NaBH4, same thing will happen. You will have Na positive, BHHHH negative. Once again, these are hydride ion donors. Now, LiLH4 is very reactive in nature. This one is slightly less reactive. LiLH4 is very reactive, this is slightly less reactive. Also, one more thing about LiLH4, see, lithium is not easy to find. Lithium is a very rare metal. So, this LiLH4 is expensive. So, we try to avoid LiLH4. If you go into the laboratory and say, I want to use LiLH4, first of all, they'll slap you and say, we don't have money. Do hydrogenation normally. If there is no other option, then you use LiLH4. Okay. So, my dear friends, how this reaction works and this mechanism, very simple mechanism, is sort of important for us. And this is the same mechanism that we saw for Grignard reagent, by the way. So, it's not very new for you. So, let's take this aldehyde and react it with, let us say, LiLH4. On paper, we are rich, so we can use LiLH4 on paper. In laboratory, we can't. So what's going to happen? Basically, H negative from here is going to attack this carbon because this carbon has positive character. We saw that a little while back. You will get this type of a species, O negative, R, that hydride has come over here, and this O negative can be stabilized by Li positive for the meanwhile, and on the side I will get AlH3, and this, if I put water into it, I will turn that O negative into OH. So I will basically be getting RCH2OH, alcohol. My dear friends, can you tell me what will be the solvent for this reaction? Can you tell me what will be the solvent for that reaction? Please think about the solvent for this reaction. If I use water, H negative will combine with H positive from water. Yeah. If I use water over here, H negative will combine with H positive from water, create hydrogen gas, leave. We cannot use water over here. For this first reaction, we cannot use water. Same as Grignard reagent, people. Are you listening or not? Same as Grignard reaction. So, we need dry conditions over here, and some of you now got the correct answer. We would use dry ether conditions. Because hydride providing agents, if you give them water, this H negative will combine with H positive, and then reaction is useless. Cool. Got it. So this is how this particular reaction works. You can write it down if you want. So this is how the reaction of NaBH4 or LiLH4 works with aldehydes or ketones. Same as Grignard. Yeah. In Grignard reagent also you put some negatively charged pieces on carbonyl bond. Over here also we put H negative on the carbonyl bond. Same thing. Now let's look at this particular case. How can we reduce carboxylic acids to create alcohols? By reduction of carboxylic acids and esters to create alcohols. So carboxylic acids are reduced to primary alcohols in excellent yields by lithium aluminium hydride. Once again, if I use LiLH4 with an acid, I will get alcohol. However, LiLH4 is expensive and therefore used for preparing special chemicals only. Commercially, acids are reduced to alcohols by converting them to the esters and followed by reduction using hydrogenation. So look at what we are doing. This reaction can be done in the laboratory, but this is very expensive. So a cheaper way to do this reaction is by taking alcohol along with the acid. Alcohol, acid. When alcohol and acid combine together, what will we get? We will get an ester. Now ester, which will look something like this. This is not an acid anymore. This is an ester. So this ester can be hydrogenated, and after hydrogenation, we get RCH2OH plus ROH. Okay. So the alcohol part, I will color that with blue color so that you can see this one over here, and the acid part also gets reduced. So these are the methods of preparation of alcohols starting from carboxylic acid. All right, very nice. Do I need to do this again? I hope not. From Grignard reagents, we know how to prepare alcohols. This is done. If you have joined the class late, please watch it from the beginning. Why am I teaching in English, not in Tamil? Please watch from the beginning. I've told everything. Okay. Reaction of alcohol is done. I mean, preparation of alcohol done. Preparation of phenol. You know this. Yeah. Preparation of phenol. This is also done. Dow's process. No problem. One more creation of phenol process is benzene is sulfonated with oleum and benzene sulfonic acid. Let's understand what that is. People, if I take benzene and I add an electrophile, which I can generate from benzene sulfonic acid, from oleum, you will get benzene sulfonic acid at the end. People, benzene plus H2SO4 and SO3, this is called oleum. Combination of H2SO4 and sulfur trioxide is known as oleum. Okay. Now, in this situation, look at sulfur trioxide. Can you imagine that this sulfur can act as an electrophile? Oxygen has a negative charge because it's more electronegative, so sulfur gets a positive character. Now the benzene can attack that particular sulfur. This sulfur trioxide acts as the electrophile. Benzene plus electrophile, what will you get? Benzene, S double bond O negative. And if you take some water or some H positive, this O negative will be converted to OH. This entire thing can be abbreviated as PHSO3H. My dear friends, this is known as benzene sulfonic acid. Electrophilic aromatic substitution of benzene gives us benzene sulfonic acid, and then this benzene sulfonic acid can be treated with NaOH H positive under high temperature and pressure. Phenol. Do you realize it is very similar to the Dawes process reaction? In the Dawes process, we took chlorobenzene and converted it to phenol under NaOH. Now we take a different derivative of benzene. Very similar reaction. So, same thing, converted to sodium phenoxide on heating with melted sodium hydroxide, acidification gives phenol. Same process, just a slight variation. Great. Then, my dear friends, let's think about the next procedure called diazotization. Okay, so what happens in diazotization is, and this is also there in amines, so let's cover it right now itself. What happens in diazotization is, if I take amine, okay, what amine am I taking? I am taking a 1 degree amine. 1 degree amine can react with NO2. Once this reacts with HNO2, what you get over here is a species that looks like this, Rn triple bond N positive. How does this happen? Let's try to understand a little. So, my dear friends, the interesting thing is that HNO2 or nitrous acid, this species is unstable. Okay. Nitrous acid is not stable at all. It's an unstable species. It's not present inside bottles in the laboratory. So to create HNO2, what we need to do is, we need to do this. NaNO2 plus HCl. Whenever we want to do reaction with HNO2, instead of taking this directly, we freshly prepare it by mixing sodium NO2 and HCl together. So this gives us HNO2 plus NaCl. Now this HNO2, imagine its composition. You can imagine it in this particular fashion, OH and NO. OH negative, NO positive. So my dear friends, this OH negative, NO positive, when you give it a little bit of energy, you don't even need to give it heat, just by stirring it, okay, you will get OH negative separately, NO positive separately. Okay, OH negative separate, NO positive separate. If you give this H positive, it will turn into water. So now, these two nitrogens attract each other and you have the loss of a water molecule from here. Alright, so you get N triple bond N with a positive charge, and on the side you get a water molecule. Fine. Now, my dear friends, for aliphatic amines, aliphatic means non-aromatic. For aliphatic amines, for example, if I have CH3, CH2, NH2, and if I do this reaction, HNO2, and this reaction usually is done at very cold temperature, 0 to 5 degrees Celsius, you stir this a little, at cold temperatures. Quickly, very quickly, your diazonium is formed. This particular species is called a diazonium cation. Quickly, your diazonium cation is formed, and this diazonium cation very quickly leaves also. So you will get your Rn2 positive. This leaves very quickly, and ultimately what you will get over here is CH3, CH2OH plus nitrogen gas is released. Okay. So for non-aromatic amines, when you take an amine, 1 degree amine, if you do this reaction, NaNO2 0 to 5 degrees Celsius, very quickly you convert it to alcohol. Alrighty. Very quickly it gets converted to the alcohol. You don't even realize this process. Very quick. Nitrogen gas is released from here. But, my dear friends, diazotization is a little more stable for aromatic species. If I start with aniline, if I start with NH2 and the same thing I do over here, NaNO2 in the presence of HCl at 0 to 5 degrees Celsius, then what's going to happen over here? N triple bond N positive, Cl negative. This thing can be stabilized for some time. This entire structure is known as a diazonium cation. Okay. And if this diazonium cation is treated with water and a little bit of heat, very small, I mean, this is at 0 degrees Celsius almost, you heat it up to room temperature, you get the formation of phenol at the end. Phenol plus nitrogen gas is released. Obviously, you will get HCl on the side. Nice. So for preparation of phenol, it takes a little longer because this thing can be stabilized and extracted. This is very useful. We will do more reactions with diazonium cations very soon. When we talk about the amines chapter, we'll do more reactions of diazonium cations. But with water, it will give you phenol. Okay. So alcohol with 1 degree amine and phenol with an aromatic 1 degree amine. Okay. Sashwin is asking, are byproducts important? It depends, man. Usually in the case of organic chemistry, they don't ask about byproducts, but some teachers are different. They might ask you about byproducts also. Very nice. So this was about diazotization and how to create phenols via diazotization. So this is the same thing that we've done. This is mentioned in NCERT this way. Okay. Next reaction for preparation of phenol. This is known as the cumene process. All right. So we start with this particular species called cumene. If you want to draw it in bond line notation, this is what you can draw it like. Benzene with an antenna on top. A small antenna on top of benzene. So benzene with this 3-carbon system on top of it is known as cumene. Now cumene can be treated with oxidizing agents. So how does it work? It is oxidized in the presence of air to cumene hydroperoxide. Energy you have to provide. Oxidize this in the presence of air and the species you will get is cumene hydroperoxide. Can you see? This O2 has gone and fit itself in the middle. Fine. So you fit that oxygen over here, basically this position. Cool. Cumene hydroperoxide, and then you put water into it, you will get phenol. and on the side you will get acetone. So in cumene process, you get both phenol and acetone, and you can sell both of these species in the market. You can sell phenol separately, acetone you can sell separately. Bro, cool bro. There's the guy in the chat box called bro. And he's appreciating the lecture, so cool. Nice. So this is how cumene process works, and acetone, a byproduct of this reaction, also obtained in large quantities. Very nice. Okay. Half of the alcohol chapter is already covered. Alcohols as acids. My dear friends, do you realize alcohols can act as acids also? R, C. Let's forget about C for now. Let me directly do this. ROH. What happens when acids react with metals? When acids react with metals, hydrogen gas is liberated. On the side, what will I get? RO negative, Na positive. Balance this reaction by doing this. My dear friends, what have I gotten over here? This OR negative, okay? This is known as the alkoxide ion. Okay, this is known as the alkoxide ion. It is the ion of the alcohol, right? Now, what happens when alcohols are going to be treated with a base? What will happen over here? This hydrogen will be captured by this OH negative. Once again, you will have the formation of RO negative Na positive, and on the side you will have water formation. Acid-base reaction. So alcohols can act as acids, either react with sodium directly to give you the alkoxide ion, or they can react with sodium hydroxide base to give you alkoxide ion and water. Nice. So now people, you only tell me if I take a species like this, if I take phenol, I treat it with NaOH, I will get the phenoxide ion. The rest of the species I haven't written. Now if I react the phenoxide ion with an alkyl halide, let's say methyl bromide, what will happen over here? What's going to happen in this scenario? Do you realize that this negatively charged species can act as a nucleophile? The nucleophile can do a backside attack on carbon, remove the halogen, typical SN2 type reaction. And what will you get at the end? The final product will look something like this. Oxygen, and over here you have the CH3, right? And whatever is remaining, NaBr on the side. Forget about NaBr. We have created an ether. We have created an ether over here. My dear friends, this procedure is known as the Williamson's ether synthesis. Okay, Williamson's ether synthesis is basically when we use an alkoxide ion to attack a simple small alkyl halide. Small alkyl halide, why? Because we want to do SN2 reaction. If we are not doing SN2 reaction, then you will not get a good yield of the product. So for SN2 reaction, we'll take a smaller alkyl halide over here. We can take any ether. Final product. Now this species has a common name. A lot of you mentioned in the chat box also. This is known as anisole. That's just a common name for this species, anisole. You should know this name. All right, so this is known as your Williamson's ether synthesis. All right, so this is what Williamson ether synthesis is mentioned like in the NCERT. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide. Rx plus Ro negative, you will get ROR dash plus NaX on the side. Ethers containing substituted alkyl groups may also be prepared by this method. The reaction involves SN2 attack of an alkoxide on primary alkyl halide. Very nice. Okay, so this is your Williamson's ether synthesis. Now that we understand what is SN2, that's not a very difficult thing. Just a second, there's a little bit of mistyping over here. Yeah. Now let us look at this particular procedure of dehydration of alcohols. Okay. So what happens when we dehydrate alcohols at two different temperatures? It gives you a different reaction. So the first reaction is when you take ROH, you do this dehydration in the presence of H positive. Basically, you take H2SO4. Okay. And you do the reaction at 413 Kelvin. You do this reaction at 413 Kelvin. We have to understand the mechanism over here. The mechanism is mentioned in the NCERT and it has been asked in the previous years. 2023 also they asked this reaction mechanism, so we need to understand. Okay. So the first thing that will happen over here, this ROH will capture the H positive. You will have protonation of the alcohol over here. So after protonation, you will get a species that looks like this, ROH2 positive. Okay. Now, what has happened over here is this OH2 positive, if you remove this, it will become water. So the OH2 positive is a very good leaving group over here. At the same time, you don't have just one molecule of alcohol, right? You have more molecules of alcohol over here. So one more molecule of alcohol can come and attack this carbon. This OH2 leaves as the leaving group. Look carefully what has happened. First of all, we made this a good leaving group by adding this proton. And the second thing is this ROH attacks. So you remove this water molecule, this OH2 you remove, and what is the species that we are getting? R, O, H, R, and oxygen will have a positive charge right now because you have hydrogen, oxygen, R, and new bond with R. So now what you can do is you can lose this H positive from here, remove the H positive minus H positive, and finally you get R, O, R. This is your ether. So notice what has happened over here. In the first step, we capture the proton. In the last step, we remove the proton. Proton is captured, then finally proton is removed. Proton participates in the reaction but gets produced again. So therefore, this proton is basically acting as a catalyst. Okay, this dehydration that we are doing is essentially an acid catalyzed dehydration. Acid catalyzed dehydration. All right. So protonation first, removal of proton at the end. And why is it dehydration? This is why it is dehydration. We are removing a water molecule. Dumping, yeah, this reaction mechanism was asked in 2023 CBSE board. This one. All right. So this is your dehydration of alcohols, and this was at 413 Kelvin. What if now we increase the temperature to 443 Kelvin? Yeah. So the same type of reaction we can do at 443 Kelvin, but 443 Kelvin we need to take a specific type of example over here. H positive, 443 Kelvin. So my dear friends, over here what happens is, first thing is the same. You get the protonation, OH2 positive. But because of this extra heat, what happens is this leaving group leaves on its own. Because of that extra heat that we've provided over here, this OH group, OH2 positive, leaves. So over here itself, you do the elimination of water. Water is gone, bye-bye. And you get a carbocation. Interesting. You have formed a carbocation over here. Now you take one of the hydrogens that are already there in the structure. There are multiple hydrogens or carbons. So you remove this H positive. Remove the H positive. So if H positive is removed, what will happen, people? H positive is removed. So you will get C negative and C positive. You will combine together and you will get this particular species. You have alkene formation over here. So this one at 443 Kelvin is essentially an elimination reaction. Yes. You remove water molecule, but this is basically a beta elimination. Once again, the 𝒤𝒄𝒄𝒆𝒃 is the major product. 𝒤𝒄𝒄𝒃 means more substituted alkene. The outer alkene is not the major product. The inner alkene is the major product. Alright, so that's how it works. We are going to have the 𝒤𝒄 elimination, 𝒤𝒄, whatever spellings you want to use. And at lower temperatures, overall if you think, this reaction is a substitution reaction. Yes. Lower temperature, substitution. Higher temperature, elimination. Coolio. So that's how this particular reaction works. Dehydration of alcohols at lower and higher temperatures. Simple cases. Lucas test, everyone. We have studied this idea already. So Lucas test. Let's take 3 specific examples right now. Let's take a 3-degree alcohol. Let us take a 2-degree alcohol. Let us take 1-degree alcohol. 3-degree alcohol. Can anyone tell me the name for this species? This species, basically there is 1 carbon over here and outside there are 3 CH3s. So this particular species is also known as tertiary butanol. This species is also known as tertiary butanol. So, my dear friends, if I do this reaction with HCl in the presence of zinc chloride as the catalyst, the first species that will get formed out of this is going to be a 3-degree carbocation, which is a very good carbocation. 3-degree carbocations are stable, right? So, this guy gets associated with the chlorine and you get the final chloroproduct. The reaction with the 3-degree species is very fast. The reaction with the 3-degree species is very fast. With the 2-degree species, however, this reaction takes a little bit of time. This reaction takes around 5 to 10 minutes with the 2-degree case. Alright. With the 1-degree case, this reaction does not happen because 1-degree carbocations are very poor. Alright, 1-degree carbocations are very poor. 1-degree carbocation is unstable. So Lucas test gives the final product very quickly. In the 3-degree case, slower in 2-degree, 1-degree, basically no reaction. So the final product that we form over here is like a white colored compound. So our colored clear solution, alcohols are generally clear solutions. Clear solution turns into a white colored solution. That's how it works. All right, people. So that is your Lucas test. It is an SN1 type of reaction. All right. So that's your SN1 type of reaction. Now, people, let's talk about the oxidation of alcohols. Let's think about three different cases over here. Let's talk about the oxidation of primary alcohols. Let's talk about the oxidation of secondary alcohols. Let's also talk about oxidation of tertiary alcohols. So primary alcohols will basically look something like this: RCH2OH. This carbon is connected to only one more carbon. My dear friends, both of these hydrogens on this carbon, both of these hydrogens are oxidizable hydrogens. Okay, these are oxidizable hydrogens. All right, oxidizable hydrogens. So by using suitable oxidizing agents, I can convert this into a species that looks like this: RCOH, OH, H. My dear friends, what is this? This particular species can be called as a geminal diol. Yeah. This particular species can be called a geminal diol. But the problem with geminal diols is that geminal diols are very unstable. Okay. Geminal diols are extremely unstable. What happens is that geminal diols end up losing a water molecule from here. So geminal diols quickly break apart into a species that will look like this: R, C, double bond O, single bond H plus H2 on the side. Hey, what is this? This is an aldehyde. Nice. And my dear friends, the aldehydes can be oxidized further. So the aldehyde can be oxidized further. Take any oxidizing agent. We'll look at the specific oxidizing agents very soon. So when aldehyde is oxidized even further, what's going to happen? R, C double bond O, single bond OH. You will get a carboxylic acid. So primary alcohols can be oxidized. Suitable reagents have to be used, of course. You can oxidize it to aldehydes. You can also oxidize it to carboxylic acids. On the other hand, when we talk about 2-degree alcohols, R, C, OH, and there's another R over here. 2-degree alcohol, right? Because carbon is connected to two more carbons. So it has only one oxidizable hydrogen. So when you oxidize it, this gets converted to RCOH, OH, something like this. And this can lose a water molecule. I will create lines once again to segregate. So this will also lose a water molecule from here. Geminal diols are very unstable. They lose water molecule very quickly. R, C double bond O, single bond R plus H2O. So what will we get over here? We will get a ketone. So 2-degree alcohols can be oxidized to ketones. 1-degree can be oxidized to aldehydes. Stronger oxidizing agents can convert it to carboxylic acids. 3-degree alcohols are C, OH. Can I oxidize them? Can I oxidize 3-degree alcohol? Because there is no oxidizable hydrogen. So people, this can't be oxidized. Can do nothing with it. Not oxidizable at all. So your 3-degree alcohol is not oxidized. What reaction happens with it, I will tell you. It's given in the NCERT. But yeah, this is how oxidation of alcohols works. So, what are the different reagents that we can use for oxidation of alcohols? There are a bunch of reagents that we can use. A few of them are important, few of them are not. So, the first 3 reagents mentioned over here on this page are your strong oxidizing agents. You take a primary alcohol. This is just a 1-degree alcohol. Strong oxidizing agent will convert it to acids. What are the strong oxidizing agents? Have a look. You can have KMnO4. So that KMnO4 over here is not alcoholic. It is alkaline KMnO4. So you can take KMnO4, or you can take K2Cr2O7, potassium dichromate, potassium permanganate. These are strong oxidizing agents. So strong oxidizing agents can oxidize primary alcohols into acids. CrO3, aqueous H2SO4 and acetone. This is a reagent. CrO3 in aqueous acid and acetone. This is known as Jones reagent. This is also strong oxidizing agent. Okay, so these strong oxidizing agents can convert your alcohols to acids. Then there are some milder or weaker oxidizing agents. Okay, what happens in milder or weaker oxidizing agents? As you can see, PCC, PDC, copper and heat, Collins reagent, you will get aldehyde. So these are very common. PCC, pyridinium chlorochromate, PDC, pyridinium dichromate, Collins reagent, that is CrO3 in the presence of dichloromethane and pyridine. So these reagents are pretty common if you want to convert primary alcohols into aldehydes. Have a look at this page, people. Please digest this page carefully. Take some time and digest this page carefully, because we don't want to keep rushing through this idea. All right. So once we are done with this particular page, let me give you some ideas of the structures of PCC, PDC, and we'll notice something very interesting. Okay. So let's look at the structures of PCC and PDC. My dear friends, you know what is pyridine? This is pyridine. Yeah. Now pyridine, if I put H positive on it, this becomes pyridinium. Pyridinium, and PCC means pyridinium chlorochromate. So we've got chromium, double bond O, Cl, okay, and O negative. So this is pyridinium chlorochromate, also known as PCC. All right. Similarly, what would pyridinium dichromate look like? Chromium, double bond O, oxygen, negative charge, oxygen, chromium, double bond O, O negative. This is your Cr2O7, 2 negative dichromate, and this will be stabilized by 2 pyridinium ions. Pyridinium dichromate, PDC, pyridinium chlorochromate, PCC. Can you guys tell me, now listen carefully, this is the interesting part. Can you guys tell me what's the oxidation state of chromium in these? Karamjeet, cool man. All the best for that. What's the oxidation state of chromium? If you notice carefully, oxygen has 6 bonds with more electronegative elements. So in both of these species, we have Cr plus 6. Cr plus 6, as we will study tomorrow in D block, is a good oxidizing agent, because you can't, I mean, you cannot oxidize this anymore. This will get reduced, so it will oxidize something else. It's a good oxidizing agent, Cr plus 6. But notice K2Cr2O7. K2Cr2O7 plus 6 oxidation state for chromium. CrO3 plus 6 oxidation state for chromium. PCC plus 6 oxidation for chromium, plus 6 oxidation for chromium. Even over here, Collins reagent also Cr plus 6 is there. Wait a second. In these cases, Cr plus 6 is a strong oxidizing agent. In these cases, Cr plus 6 is a mild oxidizing agent. What's going on? In these three cases, Cr plus 6, strong oxidizing agent. In these two cases, in these three cases, mild. How? My dear friends, this is the interesting observation. When Cr plus 6 is in aqueous medium, it will be a strong oxidizing agent. Okay, when Cr plus 6 is in aqueous medium, it will act as a strong oxidizing agent. But when Cr plus 6 is in the anhydrous medium, when Cr plus 6 does not have water, okay, that is when it is going to act as a mild oxidizing agent. Got it? Very good stuff, people. So this is the idea for oxidizing agent of different cases for primary alcohols. Let's do this previous year question. Which of the following reactions are feasible? Feasible means possible. Feasible means can be done. Which of these can be done, people? Can you tell me? Emperor, we'll come to aldehydes after the alcohols chapter. Right now we are in the middle of the alcohols chapter, bro. Can you tell me which of these reactions are feasible? Look at these cases. In the first case, what we are doing is we have a 1 degree halide with a big alkoxide ion. If you want to imagine it, this is what it looks like. O negative plus we've got ethyl bromide. The second case, however, is the opposite scenario. In the second case, what is happening? I am taking a smaller phenoxide ion, but I am taking a very huge alkyl halide. In the first situation, what can happen? In the first situation, SN2 is possible. Yeah. In the first situation, SN2 is possible. Why? Because this is a 1 degree halide. So 1 degree halides are good for SN2 reactions. So this guy can come over here, attack from the back side, bromine can leave, and you will get this type of a species. Tert-butyl methyl ether you will get. So this is possible. What about the second case? My dear friends, in the second case, we have a 3 degree halide, and today in the chapter of alkyl halides, we've understood while talking about the SN2 reaction that 3 degree halides are not good for SN2 because of too much steric hindrance. This oxygen will not be able to approach it. So over here, SN2 will not happen. But something else will happen over here. Can you tell what will happen? So this reaction cannot happen. Only the first reaction is possible. Second reaction is not possible. But how does this work? If I were to mix those two things together, then what will happen? So if I mix those two things together, a very interesting case occurs. O negative, you've got this chlorine and this, basically you've got 3 carbons, right? So my dear friends, what can happen here is that this O negative can act as a base, and the base can take one of the protons from here. Chlorine can leave. What we can do using this as a base is a beta elimination. So once the beta elimination happens, what will be the product? Double bond formation over here. Coolio. Very, very nice. So Williamson's ether synthesis works only in certain conditions. And what is the condition for Williamson ether synthesis? The alkyl halide should be small. It should be either a methyl halide or a 1 degree halide. Gokul, yeah, bro. Because the same thing, same syllabus, same questions. Cool. So these are all board 2023 questions, okay? So let's look at the first one. Let's look at the first case. Write hydroboration oxidation reaction with an example. Will you do this? We've done this today, so I hope you are able to write it on your own. Hydroboration oxidation, very nice. Second, write the products of the following reaction. So we've got anisole along with HBr. Let's understand what shall happen in that case. Let's understand what shall happen in this particular case. So we've got OCH3 in the presence of HBr. My dear friends, first thing that will happen is the oxygen gets protonated. After the oxygen gets protonated, we will get this product. Positive. Now, we need to break a bond, right? Because there's a positive charge, we need to break one of the bonds. How do we break that bond? We break that bond via the Br negative. We've got a bromide ion. Use that bromide ion to break one of these bonds. I will ask you which bond should we break. Should we react the bromide ion over here or should we react the bromide ion over here? Is it easier for me to do an SN2 reaction on CH3? Or is it better for me to do an SN2 reaction on a phenyl carbon? This is better, right? Small, no hindrance, nothing. Bromine will come over here, oxygen will leave from the other side. Over here, too much hindrance, too many carbons, too many pi bonds, big problems over here. So, the idea is that your Br negative tries to do a backside attack from this position. And ultimately, one molecule of phenol will be obtained. And on the other side, you will get CH3Br. Alrighty. So that's how opening of these ethers works. Please remember that this phenyl carbon is bad for substitution. Please remember this idea. This phenyl carbon is bad. SN1, SN2, both are bad for this phenyl carbon. Both are bad for this particular phenyl carbon. So since this side over here does SN2, you will get that particular product. Okay. Very nice. So that's how this particular reaction works. Last case, why is para-nitrophenol more acidic than phenol? GOC time, people. General Organic Chemistry. Do you remember? Why is para-nitrophenol more acidic compared to simple phenol? Do you guys remember that electron withdrawing groups increase acidic strength? Yes or no? Electron withdrawing groups increase the acidic strength. Why? You have been asked to explain why. You can't simply write it increases acidity. Why? Why? Because if this acts as an acid, by acting as an acid, it will lose the H positive. So if it acts as an acid, the oxygen will get a negative charge. And this negative charge is stabilized by the minus M effect of the nitro group. Yes. This negative charge is stabilized by the electron withdrawing resonance effect of the nitro group. That is why this is more acidic compared to normal phenol. This is how you will write this particular question in your board examination. Very nice. So this was a board previous year question. Can you try? Just explained this to you. Just 2-3 pages back I explained this particular question. Why does the reaction of CH3ONA with CH3 thrice CBr give 2-methyl propene and not the ether? Yeah, just did it couple of pages back. I'll show you that once again. This one. Because this is not good for SN2 reaction, beta elimination will take place instead. Done. So I hope you understand. That by doing things from the basics initially, we are able to understand the reasons of these easily, right? So basic ideas are important. If you guys have joined the class late, please watch from the beginning of the class. Alrighty. Now, electrophilic aromatic substitution of phenols. People, what will happen on electrophilic aromatic substitution of phenols? Let us try to react it with dilute HNO3. People, when we talk about HNO3, HNO3 can be imagined as OH with NO2, OH negative, NO2 positive. So this NO2 positive is my electrophile. Electrophilic aromatic substitution is there. Okay. Phenol. We already know this is ortho-para directing. Yes or no? This is ortho-para directing. So what should be the major products? The major products over here for this electrophilic aromatic substitution would be ortho product, para product, and a little bit, slight amount of meta product will be formed. Okay, majorly the para product is formed. Okay, this is the major product, around 51-ish%. This is around 47-ish%, and this is the remaining. That's how it works. Okay, so 1 second, I will show this to you in the NCERT also, just to make a point. Anyway, NCERT doesn't mention any percentages, so they will not ask you about the percentage. Simply they give ortho and para isomer. Very nice. Now the interesting and important thing about these ortho and para isomers. Okay. If you think about the ortho isomer, in the ortho isomer, we can observe some intramolecular hydrogen bonding. Yes. In this case, we can observe some intramolecular hydrogen bonding. Whereas in the para case, what I can observe is a lot of intermolecular hydrogen bonding. 1 second. Nitrogen, oxygen, OH. So you would have intermolecular. Intramolecular over here we have intermolecular hydrogen bonding. So can you imagine over here molecules will be better attracted to each other. Over here molecules are not very well attracted to each other. They are busy with their own self. Since more intermolecular hydrogen bonding exists over here, this will have a higher boiling point. And the other scenario with intramolecular, because the molecule itself is done, it's not interacting with any other molecule, this will have a much lower boiling point. So these two cases are easy to distill. With distillation, you can easily separate them. My student asking me when is inorganic class? Tomorrow. We are going to be doing inorganic chemistry tomorrow at 1 p.m. And physical chemistry we'll do on Wednesday at 1 p.m. Okay. Tuesday I have a class on the Hindi channel. So that is where most of my time will go. All right, people. So this is how it works. Electrophilic aromatic substitution of phenol. But if I take concentrated nitric acid, then all the ortho and para positions will be substituted by nitro groups. This is known as picric acid. Now, this picric acid or 2,4,6-trinitrophenol, this gives a very poor yield. Okay, this reaction gives us a very poor yield. Why? Because concentrated HNO3 can actually act as an oxidizing agent. So what we get over here is this side product. This species is formed as a side product over here, where phenol gets oxidized to this species called benzoquinone. Okay, so phenol, when reacted with concentrated HNO3, gives this, but there is a side product formation also. So this is one method of preparation of picric acid, but it's not a very good method. Okay, this is not a very good method. So an alternate method, which they might ask in your board examinations. Okay, this alternate method is important for us to understand. So if we start with a phenol and we react it with H2SO4, what will happen is you will get this type of a species, OH, SO3H, SO3H, 2,4-SO3H. Okay, 2,4-sulfonic acid type phenol is there. And then when you put concentrated HNO3, you get your picric acid. So your SO3H are replaced by the NO2 groups. NO2, and again we've got NO2 over here, and you've got an OH group. So this alternative method is the better way to prepare picric acid. Alright. So this is a bad way to prepare picric acid. This is a perfect way to prepare picric acid. Both of these reactions are asked in board examinations. Yes, this is much more acidic than benzoic acid. It's a very strong acid, in fact, because of the multiple -M groups. All right. So this is how this works. Then there are two more cases of electrophilic aromatic substitution of phenol with bromine, and then after that we will look at some specific reactions of phenols also. This chapter is 15 more minutes. This chapter will also be over. Then we'll move on to the next chapter, right? So if I start with phenol, do you realize that phenol is highly activated in nature? Obviously, we realize phenol is highly activated in nature, good +M group. So if I put it in bromine water, I quickly get tribromophenol. So in the presence of water, I very quickly generate tribromophenol. The color of bromine is lost in this process. What if I want only a monobrominated product? If I want a monobrominated product, I will slow this reaction down by using a non-polar solvent. Okay. So what happens is we use Br2 in the presence of carbon disulfide. I have shown you the structure of carbon disulfide in the beginning of the class when I was talking about aprotic solvents. So carbon disulfide, non-polar solvent, slows down this reaction and you get only the para product as the major product. Okay, so that's how it works. In the case of polar solvent, you will get tribromophenol. In the case of a non-polar solvent like carbon disulfide, you will only get monobromination. Okay, so if you want to balance this reaction, you will put 3Br2 over here, plus you will create 3HBr. Okay. And over here, there's just one Br2 that you're using. On the side, you will create HBr. Okay, please have a look at this reaction also. All right, people. Next reaction that we have is the reaction of Kolbe synthesis. Very interesting reaction. So we have Kolbe synthesis, Riemer-Tiemann reaction. Then we have one or two more small reactions of phenols. Then we'll do previous year questions. Okay, but then we'll do more previous year questions. So, Kolbe synthesis. Can anyone tell me what is Kolbe synthesis? How do we do Kolbe synthesis? We start with phenol and we react it first of all with sodium hydroxide. Second, we react it with carbon dioxide. And third, we quench it with some H positive and H2O. The species that gets formed out of this is this particular species is called salicylic acid. Salicylic acid. Okay. Let me give you an idea of how this is formed. I will not give you full mechanism. I will give you an idea of how this is formed. Okay. In board examination, this much is enough. In NCERT, only this much is mentioned. So what happens over here? The first reaction is when your phenol reacts with a base. Yeah, I'm sure you can imagine. You can lose this water molecule. This part you can lose. And you will get the phenoxide ion. O negative, Na positive. People, do you realize O negative will have a very strong plus M effect? This O negative has a very strong plus M effect. So because of this very strong plus M effect, this species is highly activated. So what this does is, it adds on to carbon dioxide. There is an electrophilic aromatic substitution again. Double bond O, double bond O. So this carbon adds on to this. And what you get out of it is basically this type of a species is formed. Typical electrophilic aromatic substitution, the mechanism that we've studied. So same thing happens over here. Onto an activated benzene, you add an electrophile. This is where the electrophile adds. And when you quench it with H positive, you get your salicylic acid. Alrighty. So now the interesting thing about salicylic acid is that it can create very useful esters for us. Okay. Salicylic acid can create very useful esters for us. So, my dear friends, if I start with this species, C double bond O, single bond OH, and if I react it with, imagine you are reacting with CH3, C double bond O, single bond OH. This is what? Acetic acid. So, acid plus alcohol will give me ester. Acha. One more way of writing this is, instead of using acetic acid, I can use acid chloride. Instead of using acid directly, I can use acid chloride. So what will happen is, this oxygen will go and try to attack this carbon and chlorine will leave. Similar to your SN2 reaction. Okay. So what's the species that gets formed over here? I'll make it on that side itself. C double bond O, single bond CH3, oxygen, C double bond O, CH3. So the alcohol part of the salicylic acid has made an ester with this acid type species. This compound is known as acetyl salicylic acid. And this, my dear friends, is the chemical name, the chemical structure of the very common medicine called aspirin. Okay. So acetyl salicylic acid aspirin, very common medicine that we have. In board examination, they can ask you about structure of aspirin. They can ask you how to create aspirin. So you need to know. Very, very nice. Acetyl salicylic acid. Yes, Kamali, that is possible. In salicylic acid, there is intramolecular hydrogen bonding. All right. Next reaction is Reamer-Tiemann reaction. Next reaction is Reamer-Tiemann reaction. Just a second, I made a small mistake over here. Thanks for the correction. Cool. All right. So now let's look at the Reamer-Tiemann reaction, people. So in the Reamer-Tiemann reaction, once again, we are doing something similar. Once again, we start with the phenol, and number 1 reacted with NaOH, number 2 reacted with CHCl3, that is chloroform, in the presence of more NaOH. Then we reacted with 2 more NaOH, and then finally we put some H positive H2O. Basically, you can simply write NaOH plus chloroform. You don't have to write NaOH so many times. Even if you simply write NaOH plus chloroform and then H positive H2O, you will get a product. I'll make the product for you. Then once again, I will explain how this particular reaction works. So this is called your salicyl aldehyde. This is salicyl aldehyde. Slight difference between Reamer-Tiemann and Kolbe synthesis. Kolbe gives you salicylic acid. This gives you salicyl aldehyde. Okay. This gives you salicyl aldehyde. Arey yaar, sorry. These typos. Now it is fine. Acetyl salicylic acid. Yeah. All right. Come back over here again. Salicyl aldehyde. So people, this is once again an electrophilic aromatic substitution. I hope you understand the first step is going to be pretty much the same. In the first step, you're removing the proton from the phenol to create the phenoxide ion. So we understand that this is our activated benzene. O negative. Okay. But what is the electrophile? What is the electrophile over here? The electrophile is very interesting. Let me show you what the electrophile is. Okay. So, people, when we react chloroform with sodium hydroxide, first what happens is an acid-base reaction. Acid-base reaction. So, you remove this water molecule and what you will get is C negative Cl3 and Na positive. But now in this particular step, something peculiar happens. Something very strange happens over here. Chlorine, chlorine and chlorine. What you do is, you remove one of the chlorines. Cl negative, it can sit with Na positive. Na positive, Cl negative. Now, you have taken away 2 electrons from carbon. Carbon had a negative charge, but you've taken 2 electrons away. Will this have a negative charge anymore? Carbon will not have a negative charge anymore. But carbon will have 2 unpaired electrons. Carbon will have 2 unpaired electrons. That species over there, what we've created, is called dichlorocarbene. And that is what acts as the electrophile. Dichlorocarbene. Okay. So have a look at this page, observe it, then on the next page I'll explain how these two can combine together to form salicylaldehyde. Kirti, so what happens is chloroform and base, acid H positive, base OH negative, water relieves, and your CCl3 and Na can sit like this, carbon negative, Na positive. Now if chlorine takes these two electrons, what is a bond? Bond is two electrons, no? So if these two electrons are taken by chlorine, chlorine becomes negative, Na becomes positive. Carbon was negative, but now you take electrons away from carbon, not negative anymore. So this carbon with two unpaired electrons, octet incomplete, this species is known as dichlorocarbene. Alright. So just to make sure that random chatting is not happening, this is what I'm going to do. If you're here to study, most welcome. If you're here to chat, please create a Telegram group and do something else. Okay. Fine. KS is asking why dry ether is used in Wurtz coupling. Because sodium reacts with water very vigorously. You can't use water. Okay. So if still there are random chats going on in the live chat, then I will turn the slow mode to 1 minute. Okay. Please. Let's focus on what is going on in the class. All right. Now, people, again, since this is just a fancy electrophilic aromatic substitution, and we've done electrophilic aromatic substitution in the beginning of today's class. So please, if you've joined late, join the class from the beginning. Watch it from the beginning. This is where the attack happens. Eventually, you form a species that looks something like this. Eventually, you form a species that looks like this. If you replace these chlorines with OH groups, you will get something like this. And as I told you, geminal diols are not stable. So this can lose a water molecule and ultimately give you your salicylaldehyde. So this is just an idea that I'm giving you how Riemer-Tiemann works. The mechanism for Riemer-Tiemann reaction is not generally asked in board examinations. I don't think it's given in the NCERT either. But for JEE, this idea might be slightly interesting for you. Okay, so that's how it works. Dichlorocarbene reacts with phenol. Dichlorocarbene exists, basically acts as an electrophile. All right. Nithilan, aspirin is used mostly as a painkiller, bro. All right. So chloroform generally has a higher dipole moment than dichloromethane. Kamali, so doesn't matter what type of dichlorocarbene, if it's a singlet carbene or a triplet carbene, it doesn't matter over here to us, because in both cases it can act as an electrophile. Okay. Aldol condensation we'll do in some time, don't worry. Prithvi, physical chemistry is on Wednesday at 1 p.m. So, see, organic chemistry is the longest session, obviously. Physical chemistry and inorganic chemistry, only 2-3 chapters are there, no? So, those will be smaller. So, tomorrow we'll do inorganic chemistry at 1 p.m. That will be like a 4-hour class maximum, 5-hour maximum. And then physical chemistry also on Wednesday we'll do. That is also only take like 3-4 hours. So, today's class is long. Inorganic and physical are not that long. Okay. All right. So this was your Riemer-Tiemann reaction. People, do you know what happens in this scenario? What if I treat phenol with zinc dust? zinc, metal. Metals usually act as reducing agents. Metals usually act as reducing agents. So what happens over here is that the phenol gets reduced to benzene. All right. And on the side, you will get zinc hydroxide. So your zinc has gone from a 0 oxidation state to a +2 oxidation state. So zinc gets oxidized, thereby reducing the phenol. Alrighty. So that's how it works. Anish, wherever the mechanisms are important for board exams, I will tell you those mechanisms. I've already covered SN2 reaction, SN1 reaction, Williamson ether synthesis reaction, dehydration of alcohols mechanism, HBr addition mechanism, etc. So we've already covered those mechanisms, okay? Fine. So lastly, oxidation of phenol. We've already done this reaction as a side product, but let's do it as a major product now. If I treat alcohol with a strong oxidizing agent like Na2Cr2O7 or K2Cr2O7, acidic conditions, then what you get eventually is this species, which is called benzoquinone. Okay, so oxidation of phenol gives us benzoquinone. Very nice. Coolio. So lots of reactions of alcohols, phenols, ethers, everything. Let's do this one. Previous year question, CBSE Board 2023. Can you tell me which of the following alcohols will not undergo oxidation? Easel. Cool, bro. Easel, for such cases, you know what you can do is you can search for the Wikipedia articles of dichloromethane and chloroform, and in that detail you will find all their physical properties, melting point, boiling point, dipole moment, everything is given over there. Yeah. So generally, you know, the 2 chlorines in dichloromethane and 2 hydrogens. On the other side, you have 3 chlorines in chloroform, which add to the dipole moment. AK, we've done that already, bro. Ethanol to ethene, dehydration of alcohol, we've done that already. Please go back and rewind the class and watch it. Which of the following alcohols will not undergo oxidation? Yeah. So, first one is butanol. You can oxidize it. Butane 2-ol. You can oxidize it. This can be oxidized to aldehyde, can be oxidized to acid also. You can oxidize this to a ketone. 2-methyl butane 2-ol. And lastly, we have 3-methyl butane 2-ol. This is again a 2-degree alcohol, but this one is a 3-degree alcohol. So 3-degree alcohol cannot be oxidized. Why? Because it does not have any oxidizable hydrogen. If you've been paying attention, that idea I have told you over here. Yes, we have done that idea already. So 3-degree alcohols cannot be oxidized. All right. Let's do these questions. All of these are good questions. So this is how it will be asked in board exam, okay? 5-mark question. Do either these 3 or do these 2. So because 5-mark question this is, you will have to pay a little more attention explaining these ideas. So let's look at the first case. Why is the CO bond length in phenol less than that in methanol? Let's look at the first question. So CO bond length in phenol versus CH3OH. My dear friends, this is just a single bond. But over here, what is happening is the oxygen's lone pair is in resonance with the benzene ring. So this is not the final structure of phenol. This is just one of the structures. The final structure of phenol will look something like this. Yeah, all the pi electrons are delocalized. So what will you write? You will write that because of resonance. Because of resonance between what? Between lone pair of oxygen and pi bonds of benzene, the CO bond has partial double bond character. Pardon my spellings. Partial double bond character. That is why this bond is smaller compared to that bond. Okay? BMW rider is asking for electrochemistry. That we'll do on Wednesday at 1 p.m. Okay? Anish, we don't, where is minus I, bro? We don't worry about minus I. Resonance is what matters. Prithvi, I already have a class on Tuesday on a different channel, bro, so I can't manage so many things at once. Alright, so this is the case. Sanjay, next lecture tomorrow, inorganic chemistry at 1 p.m, bro. Kamali, so benzoquinone is non-aromatic in nature. It's not anti-aromatic, it's non-aromatic. Does not do that resonance that you're thinking. Alright, arrange the following in order of increasing boiling point. Can you do that? Ethoxyethane, butanol, butanol, N-butane. What is ethoxyethane? This is your diethyl ether. Let's do this particular question. Ethoxyethane is basically diethyl ether. Then you have butanol. Then you have butanol. Just a second. What did I make? This is your butanol. This is your butanol. And then you have your N-butane. Can you arrange them in increasing boiling points? People, the alkane will have the lowest boiling point. Right? Because in alkane, there is no hydrogen bonding. There is no dipole moment. There is a non-polar organic molecule. Lowest boiling point will be for the alkane. Next comes the ether. Okay. So over here, lowest will be the alkane. Okay. Then comes the ether. Because ether has some dipole moment. Yeah. Ether has some dipole moment. How do we compare between ether and aldehyde? Yes, people. How do we compare between ether and aldehyde? Can you tell me? What would be the comparison between ether and aldehyde? Alcohol will be the highest. But how do you compare between the boiling points of ethers versus aldehydes or ethers versus ketones? What do you think? Alcohol will be the highest because of hydrogen bonding. That is correct. I want to understand from you ether versus aldehyde boiling point. C double bond O. More bonding, more electronegativity. Okay. And there's a polar end on one side. This is more polar, this is slightly less polar in nature. So you get aldehydes over here. This is the general trend. Okay, aldehydes are slightly more polar. Lakshan, it doesn't have hydrogen bonding. This hydrogen is not H positive enough to do the hydrogen bonding. This is a hydrogen bonded with carbon. Oxygen and hydrogen. This bond has higher electronegativity difference. This bond does not have that high electronegativity difference. So this will not give you hydrogen bonding. This will give you hydrogen bonding. Okay. But still this is more polar than a simple ether. Alright, anyway. What about the next case? How can phenol be prepared from anisole? Can you tell me? We've done this reaction. Look at the question number 3, people. We've already done this reaction. Can you tell me? Where did we do it? Where did we do that? Satyapriya, please watch the class from the beginning if you joined late. If there is a specific doubt, please ask. How can phenol be prepared from anisole? Yes, we've done this a little while back, people. Let me see where that is. Anisole. Phenol. Simply react it with HBr or HCl or HI. Already done that question. Where are we? This is already done. Okay. So before we do these reactions, listen to me carefully. Of all the students over here, if you are here to chat, please leave. If you are late in the class, please rewind and watch from the beginning. Organic chemistry is like one huge chapter. Segregating it into small chapters does not mean that alcohols chapter is independent from haloalkanes. Does not mean aldehydes is independent from haloalkanes. All these chapters depend on each other. So if you did not join the class from the beginning, you will not understand a lot of things because we've already covered it in the beginning. All right. Fine. So now, if you've been watching consistently from the beginning, and if you're not bothered by the chat box, then let's come to this particular question. Okay. Let's see. Give the mechanism for the following reaction. Anish, we just did that question. Please rewind and see again. Give the mechanism for the first case. People, we've done that. In the class today, I have explained this particular mechanism to you. So this is also done. Next case, illustrate hydroboration oxidation reaction with an example. This is also done. This is a 5-mark question, people. 5-mark question. Both of these cases are already done. Yeah. Very nice. Let's look at this. For the pair phenol and cyclohexanol, answer the following questions. Number 1, why is phenol more acidic than cyclohexanol? Can you tell me, people? Why is phenol more acidic than cyclohexanol? Yeah, we've done this. We've done the explanation of phenol's acidity. Phenol is acidic because the conjugate base of phenol has a resonance stability. So when we react it as an acid, when we remove the H positive, the O negative, this is basically called the conjugate base of phenol. All right. So the conjugate base of phenol is resonance stabilized. Very nice. Now the next case. What is a chemical test to distinguish between these two? And this chemical test, my dear friends, you would have studied for your lab exam. Yeah, chemistry, you have a laboratory exam, no? That YY examination, then you do some chemical reactions also. So what is the test for phenols? Yeah, what is the test for phenol? What's the chemical test for phenol? The chemical test for phenol is neutral FeCl3 test. This FeCl3 and phenol will give you a colored compound. So FeCl3 and phenol will give you a colored compound. Vicky is saying bromine water test. Yes, Vicky, you can do that also. Very good job. So Vicky is saying, sir, we can simply put bromine water over here. This will not react with bromine water because there is no unsaturation. This will react with bromine water because this does the tribromophenol reaction. Perfect. That is also you can use. That's also a reaction that you can use. So you can use both a neutral FeCl3 test, or you can use bromine water also. That is also fine. Good stuff, people. All right. Can we do these? How do we convert phenol to picric acid? We've done both the mechanisms of this. Please go back and revise. Propanone to 2-methyl propane all. Propanone, that is this one, that is acetone. And we want to convert it to 2-methyl propane all. What should I do, people? What should I do? Everything we've done. Yeah. Very good. I can see some people mentioning this idea in the chat. So Grignard reaction we will do. First species that we will get is this one, O negative CH3, and over here you will have your MgBr positive, and then in the second step you would hydrolyze it with water. Grignard reaction. Phenol to anisole, we've done this. As a phenol to anisole is the opposite one. Let's do phenol to anisole. We did anisole to phenol by adding HBr. How do we do this? I want to turn into. So what can we do, people? Anish, were you asking about this one? Is this the reaction you were asking? So we can use the procedure of Williamson's ether synthesis over here, right? So first we reacted with Na, yeah, to create the phenoxide ion. And this can be reacted with CH3Br. So you would do a quick SN2 attack. Remove your NaBr from here. Done. So we could do Williamson's ether synthesis. Friedel-Crafts is done for position of benzene ring. We want to do the reaction on oxygen, so we can't do Friedel-Crafts on oxygen. Yeah? All right. So now the next one is propene to propane 1-ol. Propene to propane 1-ol. People, very simple, right? Hydroboration oxidation. The first thing that we will do is we will put BH3 or diborane, you can say, and then after the diborane's reaction, that trialkyl borane species will be oxidized by OH group. And T-Markovnikov product, hydroboration oxidation. Nice. This is also done. Very good stuff, people. Alcohols is also complete. Lots of reactions are complete for your board examinations. More cases are remaining. As I told you, this was supposed to be a long class. Very good job for those of you who've been staying from the beginning. Okay. So what we can do now, the next thing that we have to do is aldehydes, ketones, and carboxylic acids. We've got some named reactions for aldehyde preparation, some similar reaction for ketone preparation, aldol condensation, Cannizzaro, all of that jazz will come right now. A lot of reactions we've already done. See, aldehyde ketones, let's see what reactions we've already done. We've done the reduction of aldehydes and ketones by NaBH4, LiLH4. We've done reduction of aldehydes ketones by H2, nickel, palladium, platinum. We've done aldehydes plus Grignard reagents already. We have seen how to oxidize alcohols to carboxylic acids and how to create aldehydes also. So oxidation of alcohols to aldehydes ketones is also done. So there are a lot of reactions that we've already done. Some of them we'll now see in a while. So aldehydes, ketones and carboxylic acids, that's next. So what we'll do is we'll take a break for another 5 to 7 minutes. Cool, yeah. So 5 to 7 minutes, we'll take a break and you can freshen up in that break. And when we come back, we will do more reactions of aldehydes, ketones and carboxylic acids. And just a suggestion from my side for those of you who are serious about getting good marks in the board examination, make sure you read the NCERT. If you read the NCERT of organic chemistry, if you remember those ideas mentioned in the NCERT, you will get full marks in organic for sure. Okay. All right. So let me play that same song again for you guys, and then I will go have some coffee, come back. Hello everyone. What's up? We've crossed 1,000 likes on this stream. Thank you so much, people. I'm glad you guys appreciate it. Let's have a tiny chit chat for a little while and then we'll resume the session. Kamli, so for aromaticity or anti-aromaticity, we need cyclic conjugation, right? So in the case of benzoquinone, what is happening is that we don't have only cyclic conjugation. The conjugation extends in these lines. Okay, this part is in conjugation, this part is in conjugation. It's not just the cycle that's in conjugation over here. This is not a circle that we are completing inside. So that's why this is a non-aromatic species. Ashish, that is the plan. That is the plan. Biomolecules is there in the plan, but since the weightage of biomolecules chapter is not that high, I will teach it to you in a slightly different fashion, but I will still teach it to you. Biomolecules will be included. So after this, we'll do amines, and then after amines, we'll do biomolecules. So it will take time, but it will happen. All right. Roshan, we'll do electrochemistry on Wednesday, bro. Ayya. All right, the break is over. Very nice. Let's move towards aldehydes, ketones, and carboxylic acids. So now, let's look at ozonolysis. So ozonolysis, to create aldehydes and ketones, what we need to think of is, we need to think of alkenes. We need to start thinking about ozonolysis of alkenes. So let us take this type of an alkene. Okay, what is this? This is basically carbon CH3, double bond CH3, CH3 and hydrogen, right? Now people, there are two different ways of ozonolysis. One way of ozonolysis is when we react with ozone and then we react it with zinc in the presence of acetone. Or you could do this in the presence of acetic acid, CH3COOH. I think this is what's mentioned in the NCERT also, right? So ozone and zinc in the presence of acetic acid. So my dear friends, this overall procedure that we've written over here, this thing is known as the case of reductive ozonolysis. All right. This is known as the case of reductive ozonolysis. So all you simply do is break the bond from the middle, and wherever you've broken the bond, you add an oxygen over there. CH3, hydrogen. Wherever you've broken the bond, you add an oxygen. That's it. So after reductive ozonolysis, what we obtain is an aldehyde, and on the side we also obtain a ketone. All right. Now similarly, instead of doing reductive ozonolysis from the same species, I could do a different thing also. Slightly different reagent if I take. So what are the reagents that I'm going to take over here? First, we react it with ozone as usual. Second, we can react it with H2O2. So H2O2 over here acts as a mild oxidizing agent, and this particular case is known as oxidative ozonolysis. Okay, this is known as oxidative ozonolysis. So now after oxidative ozonolysis, what are we going to do? Again, the bond will be broken from the middle. The double bond will be broken from the middle. You get C, double bond O, CH3. On the other side, you get C double bond O, CH3, another CH3. The only difference is that since we are using a mild oxidizing agent, this hydrogen will also get oxidized. this hydrogen will also get oxidized. So what are we getting out of it? We are getting a carboxylic acid and ketone on the side. So this is how ozonolysis works. In reductive ozonolysis, we use a metal in the second step. In oxidative ozonolysis, we use H2O2 in the second step. All right. So that was one of the reactions of preparation of aldehydes and ketones starting from alkenes. Then we have the reaction of alkyne plus HgSO4. So over here, just to illustrate this idea, let us take propine. Okay, let's take propine. So my dear friends, what happens over here is in the presence of Hg2 positive, this is Hg2 positive, SO4 2 negative, and H2SO4. You take a small amount of HgSO4, H2SO4. This basically is the Markovnikov addition of Markovnikov addition of water on the pi bond. So you've got two pi bonds over here. Take one of the pi bonds and add water in a Markovnikov fashion. Remember adding water to the double bond? OH went on the middle carbon, right? You do the same thing over here. So what we will do is we will convert it into this type of a species. The OH goes on the middle carbon. But I'm sure you realize from your general organic chemistry days that this is the enol form, isn't it? Right? This, my dear friends, is an enol form. Enol. Enol form will very quickly equilibrate to form your ketone. And you would get a double bond O in the middle. So what has happened overall? Overall, if you see this propine, on the middle carbon, we've added a C double bond O instead. Okay. So this happens when alkynes add on to Hg2 positive in the presence of strong acid. Okay. So now people, let's talk a little bit about, we know what aldehydes are, we know what ketones are. Let's talk a little bit about what are carboxylic acids and what are the different derivatives of carboxylic acids. Okay. So this is a little bit of carboxylic acids part also. So my dear friends, what is a carboxylic acid? RC double bond O, single bond OH. This is a carboxylic acid, right? Now all the species where I can exchange this oxygen and put something else, all those species are known as carboxylic acid derivatives. So for example, if I have any carboxylic acid with a chlorine instead of the OH group, okay, this is known as the acid chloride. Okay, also known as acyl chloride. Fine. So this is an acid derivative. Then if I have RC double bond O, single bond OR dash, which means I have the acid with some other alcohol bonded together. This, as we know, is known as the ester. Right? What if I take two molecules of acid and try to react them together? I've got two molecules of acid. What if I try to react them together? We can have the loss of a water molecule from here. Once this loss of water molecule happens, you get a dehydrated product which will look something like this. Or let's just put R only. What is this called? This is called an acid anhydride. Cool. So, carboxylic acid chloride, carboxylic acids ester, carboxylic acids anhydride, one more species, RC double bond O, single bond NH2. If you replace the OH group with the NH2 group, this is known as an amide. All right. This is known as an amide. Cool. So, people, this is a bunch of acids and acid derivatives. And the interesting thing that we need to know over here, is whenever we take acid, just a second, whenever we take any acid derivative, if I add water in an acid derivative, any acid derivative, you put water, you will get your acid back again, plus your side product. So, for example, if we start with RC double bond O single bond Cl and add water over here, what will we get? We will get the acid back again, plus you will get HCl. Nice. What if I take RC double bond O single bond OR dash and add water in this? We will get RC double bond O single bond OH, plus at the same time we will get R dash OH. Yes, interesting. If we have RC double bond O single bond NH2 and we react this with water, we'll get RC double bond O single bond OH plus ammonia, etc. Any acid derivative you take, if you add water to that acid derivative, you will get your acid back again. Fine. So this is the idea behind acid derivatives. Now, let me tell you about an acid derivative that you don't think about acid derivatives. There's an acid derivative that doesn't look like an acid derivative. Whenever we think about acid derivatives, we don't think about this compound, but let me make you think about it. R C triple bond N, cyanide. Cyanides can act as acid derivatives. Let me tell you how. So cyanides can act as acid derivatives, and let me tell you how these can act as acid derivatives. Okay. So people, let's take R C triple bond N, and what I'll do is I'll add water onto it. What happens is this oxygen can go towards this carbon, this nitrogen pulls electrons towards itself, and you can put the H positive on the nitrogen. So the first species that you will get will look something like this. Okay. Now, this species can once again be reacted with water. Oxygen goes here, nitrogen goes, pulls the electrons again. You can again react it with water. Multiple times when you do this reaction with water, this nitrogen will leave. Okay. So ultimately, after multiple steps, you will get RC double bond O single bond OH plus NH3. So your cyanides can also hydrolyze to give you carboxylic acids. So cyanides are also considered as acid derivatives. All right. So that's how it works. Acid derivatives when added to water will give you acid and a side product, and even cyanides are considered as acid derivatives. Nice. So now people, what I want to ask you is, imagine what will happen if I take an acid derivative and treat it with LiAlH4. What will happen if I treat it with LiAlH4? Think about it carefully. The first thing that will happen is you will get H negative from LiLH4. Yeah, that H negative and go attack this carbon and the chlorine leaves. So after the first attack, the species that you will get looks something like this. This is an aldehyde. Now the problem with LiLH4 is that LiLH4 is very reactive. So it doesn't just stop here. LiLH4 will react with it once again. Okay, LiLH4 will react with it once again. And you know the reaction. Yes. LiLH4 when reacts with aldehyde once again, what will happen is we will get RC double bond O, sorry, not double bond O. You will get RCO negative, H and H, and then once you quench it with water, you will get your RCH2OH. So, think carefully. Any acid derivative, when it undergoes one step of reduction, it gives you aldehyde. When it goes another step of reduction, it gives you alcohol. So, acids or acid derivatives, if I can control their reduction, I can get aldehyde. Now let us come to some very specific reactions of preparations of aldehydes where we control our reduction process. So the first case that we've got is known as Rosenmund's reduction. Rosenmund reduction. So what happens in Rosenmund reduction? We take our acid chloride, we react it with hydrogen. What is the catalyst we use generally? Palladium, platinum, etc. But if I directly react with hydrogen in the presence of palladium, platinum, you will have multiple reduction happening over here. Two-step reduction will happen. What if I want to control it? If I want to control it, I would use palladium in the presence of barium sulfate. Yeah. So this basically slows down the reaction. This barium sulfate is known as a poison to the catalyst. So what it does is it slows the activity of the palladium catalyst, and over here we can control this reduction process to reach till the aldehyde. Controlled reduction of acid chlorides with palladium and barium sulfate is known as Rosenmund's reduction. So barium sulfate is generally a powder, and in that powder we mix a little bit of platinum. So less surface area of platinum gives you a slower and controlled reaction. That's why we use barium sulfate. All right. So that's what's given in the NCERT. The same thing is given in the NCERT. Benzoyl chloride taken with hydrogen and palladium barium sulfate. Very nice. Okay. Then we've got Stevens reaction. So Stevens reaction is once again a same kind of reaction. We are doing controlled reduction of an acid derivative to reach the aldehyde. Have a look. What we've done over here, just to take a specific example, let's take CH3, C triple bond N, and we've used a metal catalyst over here, SnCl2 in the presence of HCl. Metal reducing agent is used over here. And after this, what we will do is, this is reduced by one step, so CH3, C double bond O, and you get this. Sorry, hydrogen. So once again, an acid derivative controlled reduction gives me aldehyde. This is the complete procedure. Controlled reduction, you get the species C double bond N species. This is known as the imine type of species, and imine when hydrolyzed will give you the aldehyde. Just have a look. Just have a look. This is also the similar type of reaction of reduction of an acid derivative. Stephen reaction. So Stephen reaction is specifically used to reduce alkyl cyanides. Then we have another species, another reagent known as diol H. Diol H stands for diisobutyl aluminium hydride. This is what it is called, diisobutyl aluminium hydride. So now let us understand what is isobutyl, how is it associated to aluminium, and what's the use of this particular species. So aluminium, of course, hydride, so hydrogen, of course. Now it has two molecules of isobutyl on it. People, what is isobutyl? This type of a species is known as isobutyl. 1, 2, 3 and 4 carbons, isobutyl. Okay. In that particular fashion, isobutyl. So let me make this over here in an even clearer fashion. This is your isobutyl. So the aluminium right now has two of these isobutyl groups. Diisobutyl aluminium hydride. Now the interesting thing about this is that it is a very mild hydride providing reagent. Very mild hydride providing reagent. So with this very mild hydride providing reagent, what we can do is we can do a controlled reduction. We can control the reduction process. So my dear friends, this diisobutyl aluminium hydride works specifically well for cyanides. Okay. So if I put diol H and then put water. So first we reduce with diol H, then we quench with water. So you will get R C double bond O single bond H aldehyde. Controlled oxidation, single step reduction of acid derivatives. Again, one more acid derivative that works very well with diol H is an ester. So you've got either nitriles. Nitriles work very well with diol H. Esters also work very well with diol H. So ester, when treated with diisobutyl aluminium hydride and then quenched with water eventually, this will also give you R C double bond O single bond H. Plus this alcohol will be created on the site. Coolio. So diol H, diisobutyl aluminium hydride, will work with nitriles and esters. Fine. So that's the reaction for diol H. Then we have something called the 𝒉𝒨 reaction. And in the 𝒉𝒨 reaction, we start with toluene and oxidize the carbon of the toluene to turn into benzaldehyde. So the species that we use over here to do this conversion is this. Can you name what this species is? This species, my dear friends, is known as chromyl chloride. And chromyl chloride, if you remember from your laboratory times, This is also brownish reddish in color. Okay. So chromyl chloride reacts with toluene to create benzaldehyde. This is the chromium complex that gets formed in the middle. Let me show you what that complex looks like. Just to give you an idea of what this complex looks like essentially. So you've got the benzene ring, you've got this carbon that has one hydrogen, but now two of oxygens have associated on it. Okay, so this is the kind of species that you get out of it. Hold on. Yep. Cool. So you get this complex where chromyl chloride has added onto the two hydrogens of this carbon. Those hydrogens you can put over there. There we go. So the hydrogen that were on the carbon have gone towards the oxygens. This is the complex that we form, and this complex, when treated with water, gives you benzaldehyde again. So this is your Itard reaction. Toluene when treated with chromyl chloride. Now there is a variation of the Itard reaction. Instead of treating with chromyl chloride, we treat with CrO3 and acetic anhydride. So this is your CrO3 and this is your acetic anhydride, the same species we drew a couple of pages back. Alright, so toluene, CrO3, this jazz. Again a similar complex that we saw on the previous page. Similar complex. Can you draw this? Try to draw this. Benzene ring, CH, oxygen, oxygen, and both these oxygens are basically the anhydride type. Basically make esters, double ester kind of thing. And then you hydrolyze it to get the benzaldehyde back again. So this is just a slight variation of the Itard reaction. Okay, Nitish, you would understand things if you joined from the very beginning of the session. Everyone who's over here, who's joined late, you will not understand any word that I'm saying unless you've joined from the beginning. Okay. Kamali, we'll look at the reaction mechanism of esterification in some time, then I'll tell you. When we come to the esters part, I'll tell you the reaction mechanism. Alright, so this is your Itard reactions variation. Now people, before I come to this Gattermann-Koch synthesis, people, can you tell me what this reaction is? If you've studied hydrocarbons properly in 11th, you'll know. Otherwise, now you will know what is this reaction. So let us say we reacted with RC double bond O single bond Cl in the presence of AlCl3. What is this reaction? This reaction essentially is chlorine captures the electrons, goes towards aluminium, and we've created an electrophile over here. This is the electrophile RC double bond O positive. And what will happen? One of the benzene's carbons will attack on the electrophile. So people, the name for this particular reaction is, let me make the product for you first. Just put it on this carbon, let's say, double bond O. Very nice. So those of you who are paying attention, this is known as the reaction of Friedel-Crafts. Pardon my spelling. Friedel-Crafts. Hey yo, what am I doing? My hands are tired, I think. Friedel-Crafts acylation reaction. This is known as your Friedel-Crafts acylation reaction. This group that we are associating over here is known as the acyl group. Can you see we've made a ketone? We've made a ketone over here. So creating an electrophile out of an acyl chloride, we do this reaction, Friedel-Crafts acylation. Okay. So now people, let me ask you what will happen if I take benzene and react it with a very specific type of acid chloride. HC double bond OCl. This is your formyl chloride, yes? Formic acid, HC double bond O single bond OH. Out of that, we create HC double bond O single bond Cl, formyl chloride. Once again reacted with AlCl3. Do you realize it's essentially the same reaction? Chlorine will go over here, that will become the electrophile, get associated onto benzene. And once it goes on to benzene, we will get benzaldehyde. The problem with this reaction is that formyl chloride is not available in the laboratory. This particular species that we formed over here is an unstable species. So this can't be stored in bottles. We have to synthesize it when we do the reaction. Like nitrous acid, we have to synthesize this when we do the reaction. So how do we synthesize this? We simply use carbon monoxide plus HCl. And when we use carbon monoxide and HCl to create this and do the same reaction, it is known as the Gattermann-Koch synthesis reaction. Yeah. So reaction is basically the same electrophilic aromatic substitution, but the way we are doing it is we are using carbon monoxide and HCl along with benzene and AlCl3. Nice. So that's your Gattermann-Koch synthesis. Then people, one more process of preparation of aldehyde, benzaldehyde in this case, is if we start with toluene and we treat it with chlorine in the presence of light, we take two of these hydrogens and convert it into Cl2. Yeah. So what have we created over here? We have just simply done free radical halogenation 2 times to create this type of a species. Now if I treat this with water, what can happen is that the chlorines can be replaced by the OH groups. So you've got carbon, hydrogen, OH and OH. And as we know that your geminal diols are unstable, what is going to happen? You lose a water molecule from here, get your benzaldehyde. Nice. So once again, slight variations of very similar type of reaction. Yeah, let's have a look at these reactions once again that we've seen quickly. Rosenmund reduction, take the acid chloride, H2PD BSO4, get the aldehyde. Stephen reaction, take the nitrile, use tin chloride as the reducing agent, get aldehyde. Diol H, you can use nitriles and esters to convert them to aldehydes. Etard reaction, you've got toluene and chromyl chloride. Variation was you use CrO3 in the presence of acetic anhydride. And then you do the Friedel-Crafts acylation via COHCl to form benzaldehyde via Gattermann-Koch synthesis. And this toluene, first you do chlorination and then you replace the chlorines with OH groups and one of the OH groups leaves, leaving you with benzaldehyde once again. Very similar reactions. Okay. Very similar reactions. Okay. So now people, let us move. Kamalia, that variation where we reduce the activity of palladium is known as the Lindlar's catalyst. That's absolutely fine. Coolio. All right. So what's next now? Let's talk about what is dialkyl cadmium. What do we mean by dialkyl cadmium? Do you recognize this species? This is your Grignard reagent. Good old Grignard reagent. What is this? This is your cadmium dichloride. And in cadmium dichloride, we've got cadmium in the +2 oxidation state. When we react these together, the alkyl group gets bonded to cadmium. What does this look like? This looks something like this: cadmium and 2 CH3s on it, let's say. Organometallic species once again. Now, cadmium has a positive character, carbon has the negative character. This dialkyl cadmium is once again a mild organometallic reagent. It is not as strong as Grignard. Grignard is very reactive, right? This is a mild organometallic reagent. So what you can do is, once again, you start with your acid chloride. You start with your acid chloride and you attack it with dialkyl cadmium. The chlorine gets replaced by the alkyl group. And what you get is a ketone. If we had Grignard reagent, listen to me carefully, please. If we had Grignard reagent, Grignard would again attack on ketone, right? So with your Grignard reagent, you would have multiple attack and you would get the reduction till the alcohol. But over here, alcohol will not be formed. Only ketone will be formed because dialkyl cadmium is milder. Yeah. Very nice. So this is your dialkyl cadmium. Very nice. Acha, those of you who have been following the ideas till now, can you understand how this would work? Emperor Nobilius, we have a class for that tomorrow at 1 p.m. Gokul, my bro, we will do that. Don't worry. People, can you understand what's happening in this particular process? So, if you take a nitrile RC triple bond N along with a Grignard reagent, let's say R-MgX, yeah, what's going to happen is this guy will attack over here, nitrogen will pull electrons, first species will look something like this, RC double bond N negative, R dash, this negative can sit with Mgx for the time being, but if you quickly hydrolyze it, you don't allow the Grignard to react anymore. You quickly hydrolyze it. So if you quickly hydrolyze it over here, what will you get? You will get RC double bond O, single bond R dash, plus NH3 on the side. Okay, so very similar patterns repeating again and again and again. That's all organic chemistry is. Similar patterns repeating again and again with different reagents. Now, one of our students over here is asking, that sir, how do we remember so many things? It's not easy to remember so many ideas. See, first of all, we are doing a one-shot class just 3 days before board exam. Are we supposed to study these only 3 days before the exam? Definitely not. These are supposed to be done throughout the year and this is supposed to be a revision class. That's number one. This is not a class where you're supposed to remember everything. This is a revision class. Okay. Number two, the more practice you do, the more previous year questions you solve, the more you read the NCERT, the more repetitions you go through for these reactions, the better you will understand. Okay. So, multiple iterations of the same thing, multiple times you practice these ideas, the better they will sit inside your brain. Alrighty? Yes, this is a nucleophilic attack. Grignard acts as a nucleophile and attacks the carbon over there. Anish will come to the Schiff base also eventually. So, Friedel-Crafts acylation, this is done. We've already seen this in the Gatterman-Koch synthesis, so we know how to create ketone from Friedel-Crafts acylation. Okay, now let's come to some characteristic reactions of carbonyl compounds. So to explain all the reactions of carbonyl compounds, it's very easy. This is your typical carbonyl compound, and in a carbonyl compound what happens is carbon has a positive character, oxygen has a negative character, and a nucleophile can go and attack this carbon. Oxygen pulls the electrons towards itself, and the species that you get out of it looks something like this. We've been doing this again and again, right? The same procedure we've done 224 times till now. Right. Yeah. So the same thing will happen for almost all the reactions of aldehydes and ketones. Look at this. Addition of HCN onto aldehydes or ketones. Shall we do this? Let's take a specific example. Let's take ketone acetone for this case. And what I'm going to do is, I'm going to add HCN. So we've got H positive, CN negative. This is a covalent bond only, but highly polar covalent bond. So the first thing that can happen is oxygen can get protonated, making this species even more reactive than it is. Now this has become even more reactive, no? Because it wants to pull electrons towards itself. So the CN negative will go and attack. What gets formed? We will get CH3, COH, CH3, and over here we have a C triple bond N. Nice. Now this C triple bond N, as we know, is very useful to us. Why? Because C triple bond N, if we put it in even more water, if we put H positive H2 over there, this will get converted to carboxylic acid. So you will get COH, CH3, CH3, and C double bond O single bond OH. So the species that we formed over here is known as a cyanohydrin. So cyanohydrin formation is a typical reaction for aldehydes and ketones. It's a very typical, very characteristic reaction for aldehydes and ketones. Yeah. Just a moment, please. My pen's cap is not working properly. Yeah. Actually, the pen, this is falling apart. So I stuffed it with some paper. Addition of HCN. Now, the next reaction that we have is very similar. This is the reaction of sodium bisulfite. My dear friends, what do we mean by sodium bisulfite? Sodium bisulfite, as mentioned over here, is Na positive. You can imagine like this. Something like this. Okay. NaHSO3. So out of these two hydrogens, you take and put a sodium over here. NaHSO3. So instead of doing OH, O negative, H positive over here, you can simply write it like this also. This is your sodium bisulfite. Now I am sure you realize that the sodium bisulfite's oxygen can act as a nucleophile. Same thing once again, just the nucleophile is slightly different. So this oxygen can act as a nucleophile, and this oxygen can react with, yeah, so it goes and attacks over here. So the nucleophilic addition of ketones or aldehydes with sodium bisulfite can give you this particular reaction. So you have this addition product, yeah, and in this addition product, basically the carbonyl carbons O negative. Now this O negative can capture this proton, and sodium can go and sit with the sulfur side. So this particular species that we formed is a crystalline compound. This species that we formed is a crystalline compound, and my dear friends over here, this reaction happens better with aldehydes. Okay, aldehydes are smaller, there is less steric hindrance in aldehyde. So nucleophilic reactions happen very fast on aldehydes. Ketones are slower in reaction because they have more steric hindrance. Cool. So because we form a crystalline compound at the end, this is a clear liquid and we form a crystalline compound at the end. This is also known as the sodium bisulfite test of aldehydes and ketones. Sodium bisulfite test for aldehydes, ketones. Nice. Addition of sodium bisulfite, characteristic reaction for aldehydes and ketones. Now people, let's come to the addition of alcohols and these reactions, by the way, the cyanohydrin reaction, the sodium bisulfite reaction, the addition of alcohols reaction. These are very important for biomolecules also. So these reactions are very important for biomolecules also. So let's have a look. Addition of alcohols, how does this work onto carbonyl species? So let's simply take any aldehyde over here. And what I want to do is, for the sake of simplicity, I want to add CH3OH. Now this reaction works very well in the presence of dry HCl. In water, this reaction doesn't happen because in water, you will break apart into ketone and alcohol separate. If you want the alcohol and ketone to react or alcohol and aldehyde to react, you need dry conditions once again. HCl helps catalyze this particular reaction. So what happens here, people? Let me show you the pattern. This guy goes here. Same thing. Same nucleophilic attack happens. So you will get RCOH. Hydrogen was already there and now this OCH3 adds over here. So on this carbon you have one OH group, you have one OCH3 group. This type of a species, my dear friends, is known as an acetal. This is known as acetal. And if I add one more molecule of CH3OH, one more molecule of CH3OH, what will happen? This guy comes and attacks over here, this guy leaves. Remove that OH group. So finally, the species that we form will look something like this. It will have two OCH3s on top of it. This is known as, this one is called a hemiacetal. This first species is hemiacetal. The last species is called the acetal. So first alcohol, this is what it looks like. Second alcohol, this is what it looks like. First you form a hemiacetal, then you form the final acetal. Alright. Now, if I start with a ketone, let's say I do this reaction with acetone, people. If I add ethanol in the presence of dry HCl, what will happen? First species will look something like this. This ET is what? This ethyl group is also written as ET. Yeah? ETOH. Same thing. So OHOET, another molecule of ethanol adds to it. So once we add another molecule of ethanol, what's going to happen eventually? You will get this type of a species, OET and OET. Wow. So in the case of ketones, this species is called a hemiketal, and the final species is known as a ketal. So for aldehydes, we call it, just let me write this, aldehydes. So for aldehydes, we have hemiacetal and acetal. For ketones, we have hemiketal and ketal. All right. Ma Toma is asking, will the PDF be shared? Yes, it will be shared. Absolutely, it will be shared. So this is what happens when we add alcohols. This has to be done in the presence of dry HCl. So one very interesting example, people. Let's say we have PH, C double bond OH. Let's randomly take benzaldehyde and let's add ethylene glycol over here. Have you seen what is ethylene glycol? Can anyone tell me what are the uses of this compound? This compound known as ethylene glycol. What is ethylene glycol? Do you have any idea? Have you ever heard of this compound? So since this has two alcohols in the same structure, when you use dry HCl, when these two combine together, you know what forms? Very interesting species gets formed. It looks something like this. Yes, it is used as antifreeze. It is used as a coolant also. So in cars and motorcycles, you have the coolant in the radiator, right? This is what we use in the coolant also. Used as antifreeze also. Julio. Very nice. Now let's come to the addition of ammonia and the derivatives of ammonia. Harinarayan Singh, used in Wolff-Kishner reaction? Yes, that is correct. It is used as a solvent in Wolff-Kishner reaction. We'll come to that also. It's very entertaining to read your chat. Out of all the live viewers, I think only 10-20% are actually following the class. Remaining people are worried about something else only. Sir, how long will class go? Where is Shimon sir? People are just turning YouTube chat into Tinder. Very, very interesting, people. Shows me your priorities in life are very sorted. Our country is going in the right direction. Oh Lord. So what happens when we add ammonia or a derivative of ammonia to a carbonyl compound? Alrighty. So what is ammonia? Everyone knows what ammonia is. If we have, let's say, a carbonyl species and this adds on to ammonia, just notice how I'm drawing ammonia. Ammonia is what? NH3. I'm drawing it in this type of a fashion, right? So when these combine together, I will get double bond NH plus a water molecule. Yeah, can you see the water molecule formation over there? So this species that we formed over here, this is your ammonia derivative. This is your ammonia derivative of the C double bond of, okay. This is the reaction when it happens directly with ammonia. Now there are other ammonia-like species also. So what are the other ammonia-like species? For example, you have NH2 and you have any group over here. Okay. This group could be anything. This group could be, let's say, NH2 and CH3, a carbon chain. This could be NH2 and an OH group. This species is known as hydroxylamine. This species is known as hydroxylamine. So this is another ammonia derivative only. Another ammonia derivative that is very common, which you guys have seen in Wolff-Kishner reduction, is this one. What's this called? Hydrazine. So hydroxylamine, hydrazine, etc. These different types of ammonia derivatives are known as ammonia derivatives. They are known as ammonia derivatives. Okay. So if these react with a carbonyl species, let's say NH2 and a group, the water molecule goes away, and finally the species that we get is something that looks like this. So there's a carbon with a double bond nitrogen, and nitrogen has something on it. Nitrogen has something on it, right? So if you get this type of a species, C double bond N single bond H, this type of a species is called an imine. Amine is single bonded species, imine is C double bond N type of species. Okay, so if I create this type of species, people, double bond N single bond OH, what is this called? This is called oxime. What if I create this type of a species, C double bond N CH3? Yeah, this is known as a substituted amine. Okay, this is known as substituted imine, sorry. Also called Schiff's base. This is what is called the Schiff's base. Nandu is asking, sir, are you alive? No, bro. Teaching this from the afterlife. All right. So let's see all the different ammonia derivatives that we have and what are the products that we can form out of them. So these are all your ammonia derivatives. So on ammonia, all the different groups that you can have are mentioned over there. So ammonia, if it has hydrogen, called ammonia. If it has R, amine, hydroxylamine, hydrazine, we saw those cases. So in all of those cases, this is the final product that we form, the carbonyl derivative. Okay, this one, this final product, that is your carbonyl derivative. So the names of those are given over here. Imine we saw on the previous page, substituted amine saw on the previous page, oxime saw. This one is known as hydrazone. Okay. Hydrazine gives you hydrazone. Phenylhydrazine. Normal NH2 is hydrazine. NH2 with NH and benzene ring. Phenylhydrazine, product is called phenylhydrazone. This is called 2,4-dinitrophenylhydrazine because on 2 and 4 position you have nitro groups. So 2,4-dinitrophenylhydrazine, product will be called 2,4-dinitrophenylhydrazone. Yeah. NH, C double bond O NH2, 𝒚𝒐𝒖𝒓, 𝒚carbazone. Yeah, this is the final product. Just have a look at this. Observe this page carefully. It's important. Board examinations, they ask you these questions. In JEE as well, they ask you a bunch of these questions. Please. Vishwa, thank you so much, man. Appreciate your appreciation. Emperor, it's okay, man. Ramamurthy, thank you so much again. Kraken, the PDF will be shared in the description box later. Since today is a Sunday and we are already pretty late, the PDF will be updated by tomorrow, but it will come in the description box. Abhishek on the Hindi channel, Vedantu JEE, my same type of session is there on Tuesday. So literally the same things. If you want to study in Hindi, on Tuesday I have a session. Okay. Nice. Coolio. Thank you so much for appreciation, everyone. I hope you've observed this particular page. And all of this is mentioned in the NCERT. Yeah. So this is very important over here. This is known as the 2,4-DNP test. Okay. So 2,4-dinitrophenyl derivatives, also known as the 2,4-DNP test. So this is your 2,4-dinitrophenyl hydrazine. If you have a, just a second, okay. Let me draw that for you properly. What does it look like? So if you have the NH2 over there, not able to write NH2 over there, but you understand NH2. Yeah, NH2, NH, whatever. This is 2,4-dinitrophenyl hydrazine. When this reacts with any carbonyl compound, this is what gets formed. This is called 2,4-dinitrophenyl hydrazone, and this compound is a colored compound. So depending on different aldehydes and ketones, you might get yellow, orange or red colored compounds, and that helps you understand in the laboratory that yes, I got an aldehyde. Yes, I got a ketone. Perfect. So this is the reaction with 2,4-dinitrophenyl hydrazine. Then we come to reduction of carbonyl compounds. Okay. Kamali, I don't think that is separately in the NCERT, and if it's there, it's already been covered in the Viva examination. So that's why I'm not taking those for board exam class. So shift test is different, shift base is different, shift test is different. Shift test is your para-rosanilene hydride something derivative. Yeah. So shift test is different. That is a para-rosanilene chloride compound that reacts with aldehyde to give pink color. That is different. This one is different. Fine. Okay, Sanjay is asking a very good question. In 𝒚𝒐𝒖𝒓, which NH2's water is removed? Good one, bro. So if you look at the 𝒚𝒐𝒖𝒓, this is what the entire structure looks like. NH2, NH, C double bond O, NH2. So, bro, realize that this particular NH2 is a part of the amide. The reaction that we are doing is of ammonia derivative. So this is the amide nitrogen. This is the ammonia nitrogen. So the ammonia nitrogen reacts, not the amide nitrogen. Yeah. So that's how this works. Very, very nice. Now let's talk about reduction of carbonyl compounds. Hey, we've done this already, no? Do you realize we've covered this? Hydrogenation we know how to put LiLH4, we know how to put NaBH4, we know how to put Grignard reagent for reduction, we know how to reduce all those weird cases to benzaldehyde, etc. Reduction of carbonyl compounds, we already know this. Nice. We've covered that in different cases already. Now, two more cases of reduction that are important for us are these cases. See, till now we've been reducing aldehydes and ketones to alcohols. Now let us look at two cases with which we reduce aldehydes or ketones to simple alkanes. Eventually alkane. Yeah, so I'm sure you guys remember these reactions from your hydrocarbons chapter also in 11th class. One of the cases is known as Clemmensen reduction. Clemmensen reduction is the acidic reaction. We use HCl over here. What is this called? ZnHg, this is known as zinc amalgam. Yeah, ZnHg is known as zinc amalgam. It's just a mixture of zinc in mercury. It's just a solution of zinc in mercury. So zinc amalgam reacts with HCl, gives you alkane plus water. Very nice. And then the other scenario that we have is, first of all, we react it with NH2NH2. Yes. Hydrazine gives you hydrazone, and hydrazone is taken in either QH or it is taken in ethylene glycol. We know what is ethylene glycol, CH2CH2OH, and heat it up, and that gets reduced to alkane plus nitrogen, Wolff-Kishner reduction. So this Wolff-Kishner reduction is essentially happening in basic environment. This is acidic, this is basic. Sundar, yes, tomorrow 1 p.m. we have inorganic chemistry. Priya, I agree, I feel a little tired because I've been continuously teaching for so many hours, but it's okay. Board examination comes only once in 1 year. It's okay, I can manage. All right, so this is your Clemmensen reduction and Wolff-Kishner reduction. Oxidation of carbonyl compounds. How do we oxidize carbonyl compounds, people? Yeah, same oxidizing agents that are there. Okay, so oxidation of carbonyl compounds, if we take, let's say, an aldehyde, if I treat it with KMNO4 or K2Cr2O7 or Jones reagent, what will happen? I will get RC double bond O, single bond OH. Oxidizing agent once again. Acha. The interesting thing happens when I try to oxidize a ketone. What happens in this scenario? What if I try to oxidize a ketone? First of all, it's a very difficult thing to do. First of all, it is very difficult to do. And what you need to do over here is you need to use extremely strong oxidizing agents. Generally, we do this reaction with KMNO4. Generally, this reaction is done with KMNO4. So what happens is that if you think about the enol form of the ketone, this is the major enol form. En would be on the middle side. This is the enol form of this ketone. So you take this enol form and you break it from the middle. Similar to oxidative ozonolysis. So once you break apart this enol form from the middle, that is when you get two different acid molecules. So ketones are broken apart into smaller acids via their enol form using strong oxidizing agent. So from here to there, your process is similar to oxidative ozonolysis. Right. That's how it works. Oxidation of carbonyl compounds. This is your aldehydes oxidation, this is your ketones oxidation in vigorous cases, but then there are certain cases which you have done in the laboratory. People, do you remember this test for aldehydes? Do you know the names for these tests? You've got your very famous Tollens test. Yeah, you've got your Felling's test, and these are the only two tests that are mentioned in the NCERT. But you also have something known as the Benedict's test. And Benedict's test and Felling's test are basically the same ideas. Yeah. So these I'm sure you have done in your chemistry laboratories, but let me revise these ideas for you because they are asked in board examinations, okay? So test for aldehydes. First of all, you start with aldehyde. You react it with Tollens reagent. It will give you the acid. Yeah. You will get the carboxylic acid. Essentially, your aldehyde is oxidized. Felling solution, Benedict solution, both case, oxidation happens. What are the side products? In Tollens reagent, you have silver mirror as the side product. Silver mirror test. You've done this in the laboratory if you've been to the laboratory. Yeah. Cu2O, brick red precipitate, is formed in both these cases. So if you want to know a little more about the reagents, let me show you. Tollens reagent is ammoniacal silver nitrate. Essentially, that is AgNO3 plus ammonia water. Okay, so AgNO3 and ammonia water. Are you able to hear me, people? I hope you are. Yeah. Okay. So this microphone wire keeps entangling in my feet. Hope I don't fall and break the mic or I break myself. So ammoniacal silver nitrate gives us this diamine silver complex. Okay. Now this diamine silver complex is a little reactive in nature. It's not as stable as silver nitrate itself. So this diamine silver complex essentially has silver in its +1 oxidation state. So the silver +1 gets reduced to silver 0 oxidation state and the aldehyde gets oxidized to the carboxylate ion. Okay, so silver mirror, this is where it is formed. So Tollens reagent is selective, it does not attack the olefinic double bond. Basically, if you have a C double bond C, that will not be affected by Tollens reagent. Only the aldehyde's hydrogen will be oxidized by Tollens reagent. The Tollens reagent is a very specific, very mild oxidizing agent. Okay, so this is what it looks like. Villain esports. Please watch the class from the beginning. Yeah. If you come to a movie after the interval, will you be able to understand the movie? Definitely not. If you're able to understand that movie, then that movie is so if it's a good movie, you won't be able to understand it after the interval. If you joined late, I'm sorry. You have to join from the beginning, right? So, people asking, do I know Tamil? No, I do not know Tamil. I'm sorry. That's why I've been teaching in English. Yeah. So, silver mirror test. This is how the silver gets deposited on the sides of the test tube. Very nice reaction. Then the next reaction, which is the Felling reaction, uses this particular species, CuSO4.5H2O, called blue vitriol. Okay, CuSO4.5H2O, this is blue in color, therefore it is called blue vitriol. Very nice. So when blue vitriol is reacted with Rochelle's salt, that is sodium potassium tartarate. This is the salt of tartaric acid. People, what is tartaric acid? Just a second. Double bond O, single bond OH. So this particular species that we've made over here is known as tartaric acid. All right. So tartaric acid, when it is treated with sodium, potassium or both, gives you this type of a salt called Rochelle's salt. So what happens is that Cu2 positive makes a reactive complex with this. Cu2 positive makes a reactive complex with this, so copper's reactivity increases, right? And we've got the aldehyde over here. We've got the copper 2 positive. Copper 2 positive gets reduced to copper 1 positive. This is a reddish brown precipitate. I'll show you the image, and your aldehyde gets oxidized. Aromatic aldehydes do not respond to this test. Nice. Do you want to see the color of Cu2? This is what it looks like. This is what your Cu2O, brick red precipitate. This is what it looks like. Nice. Okay. And once again, if you look at the Benedict test, it's the same. CuSO4.5H2O, blue vitriol is taken in sodium citrate. So you take the citric acid salt. Once again, these two create a reactive complex, and Cu2 positive is reduced to Cu2O. Same thing is formed in Benedict test also, and Benedict test is not in NCERT, so don't worry about it for board exams. So aromatic aldehydes do not react with Felling test. Aromatic aldehydes do not react with Benedict test either. Coolio? All right. So these were some interesting reactions of test of aldehydes in the laboratory. Now the next reaction that we have is the halofoam reaction. The next reaction that we've got is the halofoam reaction. This is extremely important, people. This is one of the most popular reactions that are there in your syllabus, and we need to understand this properly. Okay. So what about the halofoam reaction? What about the halofoam reaction? My dear friends, this reaction is very specific. Okay, this reaction is given by methyl ketones or methyl aldehydes. Very specific reaction, okay? Methyl ketone or methyl aldehyde are the only species that can give this reaction. For example, you take R, C, double bond O, single bond CH3, methyl ketone. So what we are going to do with this methyl ketone is we are going to react it with NaOH and Cl2. How this reaction works is also important. They can ask you the mechanism. So the first thing that we will do over here, just to draw this in a better format, hydrogen, hydrogen, hydrogen. Your OH negative can capture one of the protons from here. And you can get a species that looks like this, RC double bond O, single bond CH2 negative. My dear friends, please listen carefully. This is known as the enolate ion. Okay, this species is known as the enolate ion. You've seen this in ketonol tautomerism back in GOC days. Okay. So now the C negative can attack one of the chlorines over here. One of the chlorines can be attacked, and the species that you get out of this is RC double bond O, single bond CH2 Cl, and this Cl negative can sit with the Na positive. So you can make your NaCl. Fine. Understood till this point? Hydrogen abstracted by the OH negative to get C negative, and then again chlorine is put on the outside carbon. Do you understand that if this is our functional group, this is the alpha carbon, and these are my alpha hydrogens, and on alpha hydrogens I've removed to put a chlorine. So this can be called an alpha substitution. Right? This is an alpha substitution type reaction. If I substitute all three hydrogens, I have just substituted one hydrogen right now, but what if I substitute all three hydrogens? So if I do this reaction further, what I can get is a species that looks like this, R, C double bond O, single bond C, Cl3. Yes. So start with a methyl ketone or a methyl aldehyde and try substitute it with a chlorine or bromine or iodine. All right. Now that particular species, R C double bond O single bond C Cl3, this reacts with another molecule of Na positive OH negative. Another molecule of base. So 3 molecules of base we've already used. Now we need another molecule of base. So this goes and attacks on the carbon, nucleophilic attack, and this CCl3 leaves. R C double bond O single bond OH, and we've created our Na positive CCl3 negative on the side. Nice. People, this is a carboxylic acid and this species is a carbanion. Do you realize that the acid is acidic and the carbanion is basic in nature? So over here there is a quick proton transfer that takes place. So after the quick proton transfer, we get our final products over here. O negative, Na positive, and you get your CCl3. That, my dear friends, is your chloroform. And this over here is our carboxylate ion. So what happened overall? What happened overall? Overall, if you notice, your methyl ketone has reacted with 4 moles of base, 3 moles of halogen to ultimately provide you with a carboxylate ion and chloroform on the side. One part of this guy gets oxidized, the other part gets converted to chloroform. You can do the same reaction with bromine to get bromoform, same reaction with iodine to get iodoform. Iodoform is yellow in color, so iodoform is preferred because you can see when the reaction gets completed. Yeah. So that's how this works, the haloform reaction. You get oxidation and haloform at the same time, starting from a methyl ketone or a methyl aldehyde. Viswa, so the thing is that with formaldehyde and tolerance test, you will get only tolerance test, but you will not, the tolerance test is applicable for an aldehyde, but not for a ketone. So tolerance test will tell you that this is an aldehyde. This particular reaction, the haloform reaction, can happen for ketones and aldehyde both. Yeah, methyl aldehyde and methyl ketones both can give you this product. So you will not be able to distinguish between ketones and aldehydes with this reaction. Okay. Kevin, bro, you are 5 hours late for your doubt. In the beginning of the session, the second, third reaction that we did was SN1, SN2. So please go back and watch that. Okay. All right, people, aldol condensation next. You want break? I'll sit and talk to you. That will do. I don't want to do big break anymore. I'll just sit here and talk to you. I'll just write small break over here. Because we've got aldol, Cannizzaro, aldol and Cannizzaro, and then we move to carboxylic acid. So aldehyde ketone chapter is almost done, and carboxylic acids will not take much time. Very quick that will happen. Alrighty, what's up, people? It's a small break, 2, 3, 4, 5 minutes. So You can relax. Emperor, it's okay, man. Teenagers are supposed to act like teenagers. That's absolutely fine. It's just that teenagers should act like teenagers where they are supposed to act like teenagers. So that is the slight gripe that I might have, but it's okay. Kamali is asking, why does formic acid give tolerance test? So the thing about formic acid is that this guy can be oxidized very easily. Essentially, what is Tollens reagent and Fellings reagent? They are oxidizing agents, mild oxidizing agents. So this guy can get oxidized very quickly to CO2 plus H2O. So since that gets oxidized, the reagents get reduced and give you a positive test. Gobish, yes, I will solve previous year questions also, bro. I have done previous year questions of aldehydes, ketones, the alkyl halides chapter and alcohols chapter. We'll do aldehyde ketones previous year questions also, then amines also, and biomolecules also. Abhishek, the thing is that at higher altitudes, the pressure of oxygen is lesser. So your body is not used to low pressure. That's why it's difficult. Shalini, Shimon Sir is absolutely fine, but Shimon Sir wanted the best for you. And since I have been teaching chemistry dedicatedly for so many years, and Shimon Sir and I both have that IIT connection. He's from IIT Madras, I'm from IIT Bombay. So he was like, Pahul bro, why don't you do this? I was like, sure bro. That's the reason. Matoma, cool man. Anime Fame is saying 10-year previous year questions enough. For JEE Main, for sure they are enough, bro. Terror bro is asking what were your JEE marks. Bro, I gave my JEE in 2011 and at that time we did not have JEE Main, JEE Advanced separately. We could straight away give JEE Main, JEE Advanced. Just needed to have 75% in boards. So JEE Advanced, I got All India rank 3410. That was my JEE Advanced rank. Gokul, so isopropyl alcohol, you oxidize it to acetone and then do the iodoform test. Can we solve Chem Board previous year questions in this week? Yes, definitely you should. Ritik, if you say so, bro. Kaushik structure of carbonyl group. Arey bhai, this C double bond O. Sorry, I'm writing with my left hand. Arey, bro, the carbonyl carbon is aldehyde carbon or ketone carbon. The C double bond O is known as carbonyl carbon. Adishivan, oh, I'll try to make it easy for you, bro. Rayoman is asking, what about conversions, organic chemistry? See, in board examination, they won't ask you difficult conversions anyway. They're pretty easy. Uncommon, diabyl H is used to reduce nitriles and esters. We've already done that. Joshit, yo, what's up, man? Atif, I'm not sure about GOC classes separately on this channel. We'll see and have a discussion with the team on that. But in case you guys want to study GOC from me in English, there is a series that I've made called Epic GOC. And if you watch Epic GOC series, you will become an expert at general organic chemistry for sure. It's in English. It's on Vedantu JEE channel. 4-year-old series, but too good. You can check it out. Yeah. All right. So we'll chat with each other furthermore. We'll have more discussions. I like talking to my students quite a lot. So let's do some more chemistry. Then we'll do some more chit chat. Okay. Fine. All right. Ready? Methane, so moist Ag2O basically provides you with a steady stream of OH negative, mildly reactive OH negative is what it provides you. So Ag2O, when it reacts with water, gives you AgOH plus OH negative. So it gives you slowly reacting OH negative. So you can do substitution with that OH negative. If you take heat with moist Ag2O, you can do elimination also. Okay, aldol condensation. One of the most favorite reactions ever. And trust me, if you pay attention to the way I draw things for aldol condensation, this will become the easiest mechanism for you. Ready? So let us start with this very simple case of acetone. What we want to do is, we want to react it with a 10% solution of sodium hydroxide. So what's going to happen in aldol condensation is that one of these alpha hydrogens, very similar to what happened in alpha substitution, same thing will happen over here. Oxygen will capture this, and the first species you get will be called the enolate ion. Yes. So the first species that we obtain out of this is known as the enolate ion. Now, as we know, this can act as a good nucleophile. Negative charged species can act as a good nucleophile, no? So what we will do is, we will react it with one more molecule of the reactant. Alpha acid H positive is removed. This basically acts as acid to create the species enolate ion. Now enolate ion can act as nucleophile to attack the original reactant once again. Simple. Try to make the product out of this. Double bond O. Now there's a new bond between this carbon and this carbon, right? So this is the new bond. On this particular carbon, what will we have? On this particular carbon, we already have two carbons. One carbon at the top, one at the bottom. And we have one O negative now. Yeah, one O negative now. And people, if I put H positive and water over here, O negative can capture the H positive, and the final product will look something like this. Okay, this particular species, this carbonyl is the main group, ketone is the main group, this is the alpha carbon, this is the beta carbon. So I can call this species a beta hydroxy ketone. This species is known as a beta hydroxy ketone. Now, if I heat it up, it undergoes a spontaneous elimination reaction. So if I heat it up, what can happen over here is, look at the alpha carbon. If I have a proton over here, this OH and this proton can leave if I heat it up. It undergoes a very quick beta elimination reaction. So once you remove that, the final product you will get is looking something like this. Double bond O. This was your bond where you have two carbons. But now on this side, you will also get a double bond. Alpha beta has a double bond. So this species is known as an alpha beta unsaturated ketone. Have a look. Just have a look once, then I will repeat the procedure for you. If you've been attending the class from the beginning, this would be very easy for you. Otherwise, I don't know. So first step is removal of an alpha hydrogen to create the enolate ion. Then this enolate ion will attack the carbon, oxygen will pull the electrons towards itself to create this particular species, which when hydrolyzed gives you the beta hydroxy ketone. Now beta hydroxy ketone when heated can give us spontaneous beta elimination and provides you with this alpha beta unsaturated ketone eventually. Nice. So first you remove the H positive, then use this enolate ion to act as a nucleophile on the original species. So what we've done on this page is known as a self-aldol condensation. What we've done over here is a self-aldol condensation. This thing reacts on its own self. Let us now try to look at a case of cross-aldol condensation. Shall we? Saran, that is absolutely correct, bro. That is absolutely correct. Now, cross-aldol condensation, we will take two different species. So, for this example, let us take acetone and let us take acetaldehyde in the presence of 10% NaOH. Can you tell me how many products will be formed? Sanjay, because two things are merging into one thing. So you can imagine like condensation, condense. Condense means to reduce things into smaller, to reduce more numbers into less numbers. Vishwa, yes bro, that is exactly the mechanism. It's not a trick. Very nice. So you guys are saying that there will be 4 products over here. Good stuff. Why 4 products? One self product, another self product, one cross product when this guy attacks over here, one cross product when this guy attacks over here. Okay, so how shall we make the products, people? Let's try to make the 4 products over here. I hope this is enough space. One product is this one only, no? The same product. One product we already know. Let's not worry about it. Acha. What will happen when the enolate ion of this guy reacts with the aldehyde? So do this attack, move this over here. Imagine we've put the water at the end. So we will get hydrogen over here, OH. Yeah, so just there's a hydrogen over here. In the previous case, there was a CH3 over here. Fine. If I heat it up, what will happen? There will be an elimination over here. So after the elimination, what will we have? That's it. And for bond line notation, you don't need to draw the hydrogen. You can draw it like this. Perfect. Let's do the opposite case now. What if I react this enolate ion with the ketone? Double bond O. This is the new bond. This carbon has 2 carbons on it and 1 OH group will be there. Do the heat, do the elimination. And what's the product you will get out of this? Double bond O, double bond, and you've got 2 CH3s on that side. Show clips. Good question. So show clips is asking, sir, if they ask us in the board exam, are we supposed to do bond line notation? You can do this in rough work so that you come to the correct answer. Then in fair work, you can make those carbon hydrogen structures. All right. Madhu is asking how much time will this class go on? I have got no idea. I had estimated 6 hours, but we've already crossed 6 hours and we have a bunch of things remaining. So I don't know, 9 hours maybe. Let's see. I'm not in a hurry, but Yeah, we'll complete organic chemistry today. Imagine I have to do all of this again on Tuesday on the Hindi channel. We'll manage. Anyway, so the ketone product we already know. So one product we've already done on the previous page. Let's do the self product of acetaldehyde with its own self. Goes and attacks over here. Double bond O. New bond. CH3. O negative, which you can convert to the OH, and then you heat it up, and finally we get this type of a species. Done. 1, 2, 3, and 4 products in the cross aldol condensation. Very nice. Do you realize how simple it is? 2 times you will draw it on your own, the 3rd time you will get the idea. It's not very difficult. It's just about understanding the pattern and writing things on your own. If you write things on your own, it's a very simple. Yeah. Now, people, do you realize that in aldol condensation, we need an alpha hydrogen? Alpha hydrogen is necessary. Yes, because the first step is to take out the alpha hydrogen. This is one alpha hydrogen. What if I don't have an alpha hydrogen? What if I do not have an alpha hydrogen? So, one Italian scientist was crazy enough to try that. One Italian scientist called Cannizzaro. This guy was crazy enough to try this reaction. So, what he said is, I want to do a reaction of benzaldehyde with NaOH. And he tried so hard, this reaction didn't happen with 10% NaOH, 20%, 30%, 40% NaOH. This reaction didn't happen. This reaction happened when he took 50% concentration of NaOH. It's quite concentrated. This is very risky to do, by the way. Concentrated NaOH. So, people, what happened is that when this guy took 50% concentration of NaOH, what happened is the OH negative from the NaOH now attacks the carbonyl carbon as a nucleophile. Is there anything new in this attack? OH negative attacks this carbon. This oxygen will pull electrons toward itself. Same thing once again. CO negative hydrogen, and you've got another OH group over here. The next step is the most peculiar step in chemistry till now. In chemistry till now, the next step that I'm going to show you is the weirdest, the strangest step. What happens next? To understand what happens next, I will make another molecule of the original compound over here. What happens next is that this O negative says that I want to come back. This O negative says I want to come back. So if that O negative comes back, I have to break one of these bonds. If I break this bond with OH, my reaction goes back. I don't want to do a reverse reaction over here. So what I do here is I take this particular bond with hydrogen and move it towards hydrogen. Just imagine what is happening. Have a look. Just have a look at what is happening over there. Can you see an H negative will leave? Yeah, people. can you see an H negative will leave from here? And this H negative can go and attack this particular carbon. This is a hydride movement. H negative moves out and goes over here. So H negative goes over here. Oxygen will pull electrons towards itself. Notice what will happen to the two species. First, we are getting this C double bond O, single bond OH. And what's happening at the other side? This carbon had one hydrogen already. Now another hydrogen has gotten stuck to it, and you will get O negative. So this is a hydride shift. This is a hydride arrangement. It's unexpected. That's why it happens at high concentration of base. Needs a lot of energy for this to happen. So now, in this step, do you realize that the first species is an acid and the other species is an alkoxide ion? So what happens over here is the O negative wants to capture the proton from the acid because acid is the acid, right? So there is an acid base reaction that happens over here. There is a quick acid base reaction, and finally you get the species that you want. Finally what you get over here is this C double bond O, single bond O negative plus CH2OH. So if I start with 1 mole of benzaldehyde, I will get half mole of this, half mole of this. Half of this is formed, half of this is formed. Now, if you notice carefully, this particular reaction is a reduction process. Benzaldehyde gets reduced to benzyl alcohol. The other half of this reaction is an oxidation process. Yeah. Same reactant undergoes reduction and oxidation at the same time. What do we call this? Oxidation and reduction of the same species at the same time. This is known as a disproportionation reaction. So Cannizzaro reaction is a disproportionation reaction. Nanatsu was asking, why is 50% NaOH risky? You know what happens when you add strong acid to water, right? Explosive type reaction. Same. Strong base and water also very corrosive, very explosive, very harmful for the body. If it falls on your body, things will break apart. So that's the problem. NaOH and water. Strong base and water. Okay, Cannizzaro reaction is done. Lok Pradeep is saying, will they ask the mechanism in the exam? They might. They might. Very, not probable, but they might. Okay. How to prepare carboxylic acids now? People, do you realize you already know everything about carboxylic acids? Just take a deep breath and realize we already know how to prepare carboxylic acids from all sorts of species now. Yeah. You take alcohol, you put K2Cr2O7. You take aldehyde, you put K2Cr2O7. You take aldehyde, you put Tollens reagent or Felling's test. Yeah. You take KMNO4 with ketone and force it to break apart into smaller acids. You can do oxidative ozonolysis to create carboxylic acids. You can take any acid derivative, hydrolyze that derivative to create carboxylic acid. You can do Cannizzaro reaction to get half carboxylic acid, half alcohol. You can do halofoam reaction on a methyl ketone to get carboxylic acid and halofoam. You know everything that is there for preparation of carboxylic acids. That's why I say organic chemistry is one huge chapter. We already know this. Yeah, so carboxylic acid, half chapter is over. Half chapter is over, people. Carboxylic acid. Okay, what next? This is something new for us. Okay, this particular reaction is new for us. Let me explain this particular reaction to you. So, whenever we have aromatic alkanes, okay, whenever we have aromatic alkanes, let us say something like this. Whatever this carbon might have, what do we call this hydrogen? Benzene ring. Carbon, hydrogen on this carbon, this is known as the benzylic hydrogen. Alright, this particular hydrogen is known as the benzylic hydrogen. Okay, now this benzylic hydrogen is oxidizable. If I take a species with one benzylic hydrogen, okay, even if I have one benzylic hydrogen, this species, when treated with KMnO4, okay, if I treat this with KMnO4, I will simply get carboxylic acid plus side products that no one will ask you about. On vigorous oxidation of such species where you have a benzylic hydrogen, you will get benzoic acid plus some side products will be formed. So, just to give you some examples, let us take toluene, CH3, and you do this in the presence of potassium permanganate. What's going to happen? Benzoic acid. Another example will do. Let's take this guy, CH2, CH2, hydrogen, CH3, I don't know, something random. You have one benzylic hydrogen, put KMnO4, you will get benzoic acid. Even if you have one benzyl hydrogen, this will get converted to benzoic acid. But if I have a system where we don't have benzylic hydrogen, can you see there is no benzylic hydrogen? No hydrogen on this carbon? No benzylic hydrogen equals no reaction. This reaction will not happen. Okay? That reaction is not going to happen with the benzylic, in the absence of the benzylic hydrogen. All right. So this is what is written in the NCERT. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic alkaline potassium permanganate. Yeah, same thing. The entire side chain is oxidized to the carboxyl group irrespective of the length of the side chain. So whatever is on the side doesn't matter. The only thing that matters over here is the hydrogen. Benzylic hydrogen should be there. Coolio. This is how it works with alkyl benzenes. Nice. People, you know this reaction? Hey, now we are in the easy part. We know most reactions. Yeah, look at this formation of anhydride. We already know this. Remember, we took 2 molecules of acid, and from 2 molecules of acid, what we need to do is we remove 1 water molecule. How do we remove water molecules? The only thing to do to remove water molecules is to heat things up. When you heat it up, water leaves. Now this reaction can be done in the presence of acid. So you can do this reaction in the presence of H2SO4. Okay. Or you can do this reaction in the presence of H3PO2 also. Or you can do this reaction in the presence of P2O5. You can also write this as P4O10 because generally it exists as a dimer. All of these essentially act as dehydrating agents. Alrighty. So these act as dehydrating agents. Fine. So this is how you create acid anhydrides. And we already know what anhydrides are, yes? For those of you who might have joined the class late, I would love to tell you that we have already seen what are acid derivatives. We've already seen what are acid derivatives. We've already seen the mechanism of formation of acid anhydride. This is just a recap now. Yeah. So if you joined the session late, thank you so much for joining in. Please watch it from the beginning if you can. Esterification. Everyone knows esterification. Acid plus alcohol gives ester. This was the first reaction of organic chemistry that you ever studied. 9th, 10th class, I think. So now one of our students was asking, sir, which oxygen attacks where? Right? So let me do a very beautiful color coded mechanism for you guys. R, C double bond O, single bond OH. This guy reacts with an alcohol which has R dash instead of R, okay? R dash OH. So the mechanism over here is very peculiar. See, this is an acid. An acid behaves as an acid. But the alcohol can behave as a nucleophile, can behave as a base, can behave as an acid. Alcohol is very versatile over here. So what we observe for the esterification process is I put it in concentrated acid. As you can see, H2SO4 or HCl. So what this concentrated acid does is, carboxylic acid is weak acid, concentrated acid is strong acid. Look at this very weird species. The carboxylic acid acts as a base. Yeah, the carboxylic acid acts as a base over here. Why? Because we've taken an even stronger acid. So if this is Don, this is Big Don. I don't know. Alright. Now do you realize this has become a good leaving group? And if this has become a good leaving group, what can happen is the oxygen of the alcohol can go here and the OH2 can leave. So notice R, C double bond O, and the oxygen of the alcohol gets associated over here. You can lose this H positive. You took H positive, you lose H positive, catalysis, ester. So my dear friends, this particular oxygen comes from the alcohol. Because alcohol can act as a nucleophile, and that's what it's doing. It's acting as a nucleophile in this particular step. So that comes from the alcohol, this oxygen. This mechanism, by the way, if you are interested in science, is known as the Fischer-Spear esterification. names of the two scientists that figured this mechanism out. Esterification process is done. Reaction with PCl5, PCl3, SOCl2. Look at this. You know this already. What are we doing overall? Let me show you and then you read it, okay? RC double bond O single bond OH. If this reacts with a halide providing reagent, chlorine comes, OH leaves. We will get the formation of acid chlorides. Substitution reaction, nothing new. The first thing that we did in today's class was substitution. You saw the same reagents for substitution of alcohols, remember? I will show you that just as a recap. I'll come back to that page, even though I'll forget what page number that was. Ayyo, there it is. Same reagents, people. Same thing once again. Yeah. So, there we are. PCl5, PCl3, SOCl2. Once again, this method is preferred because we get gaseous formation in the last mechanism. So we get the pure product out of this. That's mentioned over here also. Read it, please. Vishwa, yeah, that's the same guy, bro. Vishwa, sure. It's called a callback. Have you heard of the basics of presentation and how to make things interesting? So one of the things that stand-up comics use quite a lot to make things interesting for their audience is called a callback, where they've said something in the beginning and towards the end they say that thing again and it turns into something fancy. Callback. In the language of Instagram, we call it throwback time. So yeah, callback. So now we know how to create acid chlorides also, starting from acids. What will happen with ammonia? This is also a very simple reaction. Now you know everything. People, what happens when an acid reacts with ammonia? Do you realize we can do an acid-base reaction over here? Acid-base. So, RC double bond O, single bond O negative and NH4 positive. But if we heat it up, what happens when we put heat? Water leaves. Typical. What happens when we heat things up? Water says bye-bye. So once water says bye-bye over here, you will get RC double bond O, single bond NH2. And this is your water that says bye-bye. Amide. Nice. So we know how to create esters, we know how to create anhydrides, we know how to create acyl chlorides, we know how to create amides. Same thing is mentioned over here from the NCERT. You've already done all the reactions of acid derivatives also. Yeah, very good. People, do you remember this reaction? People who are asking for a break, let's finish the carboxylic acids part. Okay, there are just a few handful of reactions that are remaining. Once we do the carboxylic acids part completely, then we will take a break. Okay, so after the carboxylic acid reactions, we'll take a break, 5-minute break. Then we'll do previous year questions of this chapter and then we'll move to amines. Okay, so let's do carboxylic acids. Decarboxylation. 11th class you had done this particular reaction. So let me remind you if I take, say, any carboxylic acid of this manner, OH, and I add it to NaOH and calcium oxide. This reaction, basically, you realize, will be an acid-base reaction. So you will waste some OH negative, Na, this carboxylic acid, etc. So what if we start directly with a carboxylate ion over here? Okay. We start directly with a carboxylate ion over here. So let me tell you what happens, just giving you a pattern of this reaction. Just a second. Notice what I have drawn inside this particular red colored box. There is carbon dioxide, and then there are two sodiums and another oxygen. Do you realize out of that box we can create Na2CO3? The carboxylate part goes away with sodium. The carboxylate part goes away with sodium. That's why we call it a decarboxylation, because the remaining part, which I'll highlight with the green colored dotted line, will create your CH4. Done. Sodium carbonate, alkane. What is calcium oxide doing over here? Calcium oxide is used only to absorb moisture. Okay? Because water starts reacting with this, then that's a problem. If water starts reacting with this to create the acid again, that's a problem. So in order to absorb water, so that water does not disturb this reaction, we take calcium oxide. Great stuff. Decarboxylation reaction. Beautiful. Last reaction of carboxylic acids. Last reaction of carboxylic acids. After this, yeah, we'll do a break. Okay. So, people, imagine we've got a carboxylic acid, something like this. Can you understand that this is an alpha carbon? This is an alpha carbon, isn't it? Yes. If I put, let's maintain the color coding. If I put a halogen on this alpha carbon, let's say we put a bromine, can I call this an alpha substitution reaction? Alpha substitution. And this looks very similar to the first step of haloform reaction. Looks very similar to the first step of haloform reaction, right? Over there also we took a ketone and we did an alpha substitution. So this is an alpha substitution reaction for carboxylic acid. The reagent that we use over here is Br2 in the presence of phosphorus. Carboxylic acids having an alpha hydrogen are halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amounts of red phosphorus to give alpha halocarboxylic acids. This reaction is known as the Hell-Vollard-Zielinski reaction, also called the HVZ reaction. Three different scientists, Vollard and Zielinski, worked exclusively on this reaction, by the way. Hell did not work on this reaction, but other earlier research papers that Hell had published were used to figure out this process. So Vollard and Zielinski decided to keep Hell's name also. Hell-Vollard-Zielinski reaction. Perfect. So this is your alpha halogenation reaction. Nice. Hell-Vollard-Zielinski. People, tomorrow at 1 p.m. we have inorganic chemistry session, and Wednesday at 1 p.m. we have our physical chemistry session. Cool. So this is your Hell-Vollard-Zielinski reaction, which is nothing but the alpha halogenation reaction of carboxylic acids. So people, up next is number 1, the previous year questions of this chapter. And the second thing that we're going to do is the chapter of amines. So there are a few reactions of amines, but it will be easier for us to understand now that we've done 80% of chemistry, organic chemistry. So once this is done, then we'll move on to biomolecules. And for biomolecules, I'll take a slightly different approach to teaching. Biomolecules is a different type of chapter. So for biomolecules, the approach will be slightly different. So we'll come to biomolecules after we do these two things. So at the moment, let's take a 5-minute break. Coolio. Kamali, since you already know Kolbe electrolysis, good. And what I can suggest is you can quickly search for it on Google and revise it. In NCERT also, there's just one line that says Kolbe electrolysis, and that's just a coupling reaction, as you know, of 2 carboxylic acid. Cool. So yeah, we'll do this. Hello, check. All right. We're back. I had two biscuits and a protein shake. That was my meal. What else, people? Ah, enjoying the class, I hope. Vimal, not regularly. Sometimes I do. Vishwa Singh, sir, your favorite destination you want to visit and have visited? I have been to Ladakh on my motorcycle, Vishwa. From Bangalore, I went to Ladakh and stayed there for a month in 2022. But my regular favorite destinations have to be Goa and Kotagiri. If I go to Goa and Kotagiri, I feel really nice. Kotagiri is very close, hardly like 300 kilometers. And then Ladakh is too far, so I've been there only once. Goa, once a year is what I do. Nitish, I'm sorry, I don't, bro. That's why we're doing this class in English. Ritvik, yeah, man, tried a different style. I thought, why not? Bhuvan, it's okay, man. You can take some rest. Oh, Lord. Classes for JEE April attempt. You can request Shimon Sir for that, and I will also have a word with him. Then we'll organize it. If your demand reaches him directly, I think we'll be able to organize it better. Yeah. Raghavan, the class started around 4 p.m. Sashwin. Sashwin, so scooter seats are not meant for long duration anyway. The posture on a touring motorcycle is as such that you can do longer hours, and harder seats are better for long duration. Soft seats don't give you support. Gobish is asking how long you're growing your beard. This is natural, bro. Joshit, yes. My name is Pahul. Okay. 5-minute break is over. Let's do 2023 boards questions. Okay. What happens when propanone is treated with CH3 and then hydrolyzed? Now it looks childish, isn't it? Propanone, CH3 O negative, H2O, IO. We've done this reaction, the same reaction we did a little while back. What happens when ethanol is treated with excess ethanol and acid? Ethanol. And you've got ethanol and you treat it with H positive. People, what should happen over here? What should happen over here? It's an interesting reaction if you think about it. What can happen over here, my dear friends, is that this guy can get protonated. After protonation, we will have this type of a species. OH. And then this alcohol can add on to the carbonyl compound. Alcohol plus carbonyl. What will happen over here? First species that we'll get is a hemiacetal. And then the next species that we will get after more addition of ethanol will be the ketal. Or since we are starting with an aldehyde over here, hydrogen, this is acetal. acetal formation. Okay, alcohol added on to aldehyde is acetal formation. What happens when methanol undergoes Cannizzaro reaction? Let's look at the last case over here. What happens when methanol undergoes Cannizzaro reaction? So what is methanol? If it undergoes Cannizzaro reaction under 50% NaOH conditions, then you would get HC double bond O, single bond O negative, and HCOH. So we will get the carboxylate ion, methanoate ion. This is from methanoic acid, right? So we will call this methanoate ion, and this is your methanol. Oxidation and reduction of this carbon both at the same time. Very nice. Write the main product for the following reaction: 2CH3COCl plus dialkyl cadmium. What will this give us, people? We've done this reaction. Mild reduction. Grignard will force it till the alcohol. This will only continue till the ketone part, yes. So, chlorine leaves, and what we will get over here is the ketone. And they've asked you only to write the main product. So, you don't even need to worry about the side products. Cool. Very nice. Okay. What about the next reaction? CH3, CH2, CHO, zinc, amalgam, concentrated HCl. This is your Clemenson's reduction, yes. So if I have an aldehyde and I reacted with zinc Hg in the presence of HCl, you would get reduction. 2 carbons, you would get ethane. This is your Clemenson reduction. Perfect. Achha, there are 3 carbons over here. So we will get propane. Nice. Okay, what's the last one? Decarboxylation. People, will you be able to do this on your own? Decarboxylation is simple. Just remove this entire thing. You will get cyclohexane. So we will get cyclohexane as the product. Done. Very nice. Simple questions. Which of the following acids would be stronger? FCH2COH or CH3COH? So we've done this idea earlier also, that electron withdrawing groups make our species more acidic. Why? Because the electron withdrawing group stabilizes the conjugate base. Therefore, this is more acidic. The fluoride part is more acidic, okay? Because fluoride is a minus I group, right? So this minus I effect of the fluoride will stabilize the COO negative that is formed. That negative charge will be stabilized by the electron pulling nature of fluorine. So that's why that is going to be the stronger acid. Okay. Then arrange the following compounds in increasing order of their boiling points. Once again, we have alcohol, we have aldehyde, and we have carboxylic acid. So we'll have the most amount of hydrogen bonding where? You can do this. Very nice. Try it on your own, okay? Alcohol has hydrogen bonding, aldehyde has hydrogen bonding, but acid has lots of hydrogen bonding. So, acid more than alcohol, more than aldehyde. Give simple chemical test to distinguish between benzaldehyde and acetophenone. Acetophenone means you have C double bond O CH3. Acetophenone. Acetyl, phenyl, ketone. Acetophenone. So how do we distinguish between aldehyde and ketone? Simple. Let's do tolerance test. Can I use Felling's test over here? The razzling nerd. You've been in the class from the beginning. Good stuff, man. But what do you think? Will Felling's test be possible over here? No, because you should remember that Felling's test is weak. Okay? What just happened? Felling test does not work with aromatic aldehydes. Okay? So Felling's test does not work with aromatic aldehyde. Cool. So you can do tolerance test. Tolerance test will work. Felling will not work. So that was the idea. But you guys are telling me that you can also do haloform test. That is also fine. Haloform test is also fine because this will give you the haloform test. This will not give you the haloform test. So tolerance test can be used, or you can also use haloform test. Good stuff. All right. Conversions. You guys love conversions, don't you? Let's try this out. Benzoic acid to benzaldehyde. Benzoic acid needs to be converted to benzaldehyde. People, how would you do this? Think it's a very good question, and I'm sure you know. Vishwa, so since it is a subjective type examination, if the person who's checking your paper knows chemistry, they will choose either answer as correct. We want to do reduction, very nice, but can you tell me the reagents that we will use to do this reduction? I want to reduce the acid only till the aldehyde part. There are multiple cases we saw, right? See, if I use LiAlH4, this will get reduced till the alcohol. LiAlH4 will reduce it till the alcohol. So what's the better thing to do? Think about it, okay? Think, how did we take all the acid derivatives till aldehydes? How did we take all the acid derivatives till aldehydes? We did mild reduction. Yeah, we did mild reduction. So how do we do mild reduction over here? What is the better method of doing mild reduction? Raghavan, very nice. So what we should be doing in the first reaction, okay, listen carefully now. It's basically about memory. The more you remember these reactions, the better you'll be at converting them. So it's more of a memory based type question. First of all, let's convert this to the acid chloride. Now this acid chloride, there is a very specific, very standard reaction to convert it into benzaldehyde, and that is when I react it with H2 in the presence of pelletized barium sulfate. Rosenmund's reduction. So first you turn the acid into a suitable derivative, and then the derivative can be reduced mildly, in this case by Rosenmund reduction, to create this. Another thing you could have done is, you take this, you convert it into ester. Ester can be converted to the benzaldehyde via diol H, diisobutyl aluminium hydride. So just about memorizing the reactions carefully, and now that you've applied the reaction, now you will be able to remember it better. Application means memorization. More you apply, better you will get at it. So first part is done. Let's look at the second part. Propane 1-ol to 2-bromopropanoic acid. So in the second case, I want to start from propanol. I want to convert it to 2-bromopropanoic acid. Okay. Yes, people, can you imagine? You've seen this, no? Alpha bromination of acid. Just convert this to acid and do alpha bromination. So, first of all, let's convert this to acid by using Jones reagent. What was Jones reagent? CrO3, aqueous H2SO4 and acetic acid. So, you take Jones reagent, you convert it to the acid, and then you simply do the alpha bromination by taking Br2 in red phosphorus and Hi. You don't even need to take Hi वैसे. Br2 in red phosphorus. Number 1 and 2, just put some H positive. Done. HVZ reaction. Cool. Zoom homeopathy is asking, do we have to write reaction intermediates? Not really. This is good enough. Cool. Second part is also done. What about the third case? Acetaldehyde to but2-enol. Acetaldehyde to but2-enol. Okay. One more reagent I'm telling you, okay, for aldol condensation might come in boards. 10% NaOH or barium hydroxide is also used. So barium hydroxide is also used for aldol condensation. Just keep that in your mind if you can. So 10% NaOH and then you heat it up. First you will have aldol condensation, then you will have elimination. Sarvesh, it's okay, man. To each their own. Alright, so this procedure is also completed. This is the third one. Nice. Okay. Nice question. All explanations are given in the NCERT. This is a homework question for you guys. Class is not over. Just giving you a homework question. You will get it in the PDF. If you want a screenshot, you can take a screenshot. Reasons are all mentioned in the NCERT. One more question is there. A couple of questions. I have taken a bunch of questions, by the way. So, let's do this one. Next two questions I'll give you as homework. Then we'll move to amines chapter. Okay. All right. Chalo. So, an organic compound A having the molecular formula, error, yes, it does. So, that's why we quench it eventually with H positive. Chalo. An organic compound A having the molecular formula C3H8O on treatment with copper at 573 Kelvin gives B. B does not reduce Fehling solution but gives a yellow precipitate of compound C with I2NaOH. Reduce the structure of A, B and C. My dear friends, you have first of all C3H8O. So your compound A should be an alcohol. What are the two possible alcohols for C3H8O? Either it would be propane 1-ol or it would be propane 2-ol. Now, if I put copper at 573 Kelvin, this is one of the oxidizing agents. This will get oxidized to aldehyde. This will get oxidized to ketone. Now the thing is, this does not reduce Fehling solution. So, cannot be the aldehyde. Has to be the 2-degree alcohol. And what happens when it reacts with NaOH and I2? Iodoform is yellow. Very nice. Done. Simple questions, board exams. You can try this. First of all, it says write the reaction involved in Cannizzaro. You know that. Why are boiling points of aldehydes and ketones lower than that of carboxylic acids? Because carboxylic acids have hydrogen bonding. An organic compound A with molecular formula C5H8O2 is reduced to N-pentane. This is a very good question, by the way. Want to try this? After this question, let's do the amines chapter. An organic compound A with molecular formula C5H8O2 is reduced to N-pentane with hydrazine followed by heating with NaOH and glycol. Wolff-Kishner reduction gives you N-pentane. So this C5H8O is a straight chain structure. You have to basically put two double bond O's on this. Now A forms a dioxime with hydroxylamine. Basically it adds two molecules of hydroxylamine. So it has two double bond O. It has 2 times C double bond O. So that's why it is creating your 2 times hydroxylamine. And it gives a positive iodoform test and also tolerance test. It means positive iodoform test means you will have a methyl ketone. Positive tolerance test means you will have an aldehyde. Done. This is your methyl ketone part which will give you iodoform. This is your aldehyde part which will give you tolerance test. Nice. So, with that, my dear friends, there is another question over here that I've kept. You do it as your homework. Let us move towards amines. Are we ready? Shall we go towards amines? Now life will become even simpler. We can rush through this chapter because we know the basics. We know what is oxidizing agent, we know what is reducing agent, we know what is nitro, we know what is amine. Let's quickly get through this one. Reduction of nitro compounds. Nitro compounds can be reduced to amines by passing hydrogen gas in the presence of finely divided nickel, palladium, palladium. Same thing. Tin HCl. Similar to your Clemmensen reduction, zinc HCl was there over here, tin HCl. Similar to Stephen reduction, SnCl2 and HCl, same. FeHCl, all of these metals with acid are reducing agents. So, nitro compounds can be reduced to amines by either hydrogenation or by treating it with metal and acid. Okay. Either of these species can be used over here. Tin generally gives us better results. Okay. Tin generally gives us better results with lower side products. Needs the least amount of energy. So it gives us a good yield available easily in the laboratory. Those are some few reasons. Alright. Ammonolysis of alkyl halides. My dear friends, this is just a fancy SN2 type of reaction. Okay. So what we will do over here is, let us take ammonia. Let us react it with CH3Cl. Okay. So SN2 reaction, backside attack on carbon, chlorine will leave. The first species that you will get over here is CH3, let me draw it like this, CH3NH2, and you will get HCl on the side. So from ammonia, I have created a 1 degree amine. Now, what if this 1 degree amine attacks on the same species again? Yeah. What if this 1 degree amine reacts with CH3Cl again? Again, you do an SN2 reaction. What will you get? You would get NH CH3 CH3, and you would get another HCl on the side. So ammonia 1 degree amine, then you've created a 2 degree amine. Now if this 2 degree amine reacts another time with CH3Cl, what's going to happen? You will get one nitrogen with 3 CH3s on it. CH3, CH3, another CH3. 3 degree amine. Okay, what if it reacts one more time? What if it reacts one more time with CH3Cl? Finally, the species you will get looks a little different. It has nitrogen with 4 carbons on it. Positive charge and stabilized with a negative charge. This particular species is known as a quaternary ammonium salt. Quaternary ammonium salt. Have a look. SN2, 1 degree amine, another SN2, 2 degree amine, another SN2, 3 degree amine, another SN2, quaternary ammonium salt. Kamali, since there are no 4 different groups, these will not be optically active over here. Jebin is asking which one of these is the most basic. See, the quaternary case, Jebin, is already, associated with 4 carbons, has a positive charge, so it does not need any more H positive. Out of these 3, which one is more basic? We will discuss that in some time. There's an exceptional case over there. Okay. There's an exceptional case over here. So those of you who are confused about the optical activity, please have a look at the original case. In a tetrahedral species, if all 4 substituents are different, then we have optical activity. Okay, so if you have CH3, C2H5, hydrogen, something else, then it will be optically active in nature. All right. Reduction of nitriles, people, same thing once again. Can you see? I am reducing a C triple bond N to RCH2NH2. What are the reducing agents that I can use? I can use hydrogenation, or I can use sodium amalgam in ethanol. Slightly different reaction. Sodium, again, metal reducing agent in the presence of ethanol. Okay. So nitriles can be reduced to RCH2NH2 by treating with sodium amalgam in the presence of ethanol. Okay. RPK, that question that you are asking, we have already done that in the alcohol chapter. Please rewind and see. Reduction of amides. R C double bond O NH2. This is an amide. Amide can be reduced by LiLH4 in the presence of water to once again create a 1 degree amine. Yeah. Adishivan, we are already in the amines chapter, bro. Cool. So, for preparation of amines, we can reduce nitro groups. We can take ammonia and do substitutions. We can reduce nitriles. We can reduce amides also. Yeah. So, now we will do a very interesting reaction called the Gabriel's phthalimide synthesis. Gabriel's phthalimide synthesis. We will fill the full page with some structures. So, please pay attention. Okay. Please pay some attention over here. My dear friends, do you know the name of this particular species? C double bond O single bond OH bonded with another C double bond O single bond OH. Do you know what's the name of this species? This species can be called the phthalic acid. Okay, this species can be called phthalic acid. Okay, now if I react phthalic acid with ammonia and put heat onto it, what will happen? Both sides of the phthalic acid will be converted to the amide. C double bond O, single bond NH2, C double bond O, single bond NH2. Right? Now, if I heat it up even further, I get a very interesting species. So if I heat it up even further, the interesting species that I get over here, there is a loss of an ammonia molecule over here. C double bond O, single bond NH, C double bond O. That species over here, my dear friends, is known as phthalimide. So we start from phthalic acid and we end up at phthalimide. Okay. Who says it's recorded? Yeah, whoever is saying that this session is recorded, yes, this session was recorded back in the year 1901. We were still under the British rule. That's why I'm speaking in English. Just kidding, people. This is a live session and I don't know how to speak Tamil, so I'm sorry. That's why I'm teaching in English. Why did they choose me to teach you chemistry? Because I have experience in chemistry and they wanted you to have a good chemistry teacher before board exams. Anyway, not that I'm saying all teachers are, I'm the only good teacher. That's not the case. They told me you have to take session, so I took session. Simple. So those of you who are appreciating the session, thank you so much. And those of you who are bored with the session or not interested in the session, that's absolutely fine. This is YouTube. No one's forcing you to stay here. So please write this down. Give me a moment. All right. Thank you for waiting. So after the phthalimide, what we do is we treat our phthalimide with something that looks like this. So people, treat your phthalimide with a base. Yeah. What happens when you treat your phthalimide with base? OH negative will capture the proton, and what you will get is a negatively charged species. C double bond O, N, C double bond O, negative charge on the nitrogen and K positive next to it. N negative, K positive. People, now that we've created a negative charge over here, this can act as a nucleophile, isn't it? Yeah. So if that acts as a nucleophile, once again I have to draw the entire phthalimide over here. It's okay. C double bond O, N negative, C double bond O, N negative, right? So now this N negative that is stabilized by K positive for the meanwhile can attack a small alkyl halide. So let us take some RBr type of species. This is essentially a small alkyl halide. And what I want to do here using a small alkyl halide is I want to do an SN2 attack. So after the SN2 attack is done, what do I form? C double bond O, C double bond O, N, and you have your alkyl over here, plus your KBr will be formed on the side. Last step of the reaction. All you need to now do is put water into it, and as soon as you put water, the left side will convert into the original species, which is your phthalic acid. And the right side will get converted to NH2 with this alkyl group. 2 hydrogens on nitrogen, nitrogen only with 1 more carbon. People, this is a 1 degree amine, a primary amine. So your Gabriel's phthalimide synthesis is the reaction for preparation of primary amines. Gabriel's phthalimide synthesis, preparation of primary amines. All right. So you can have a look. You take your phthalimide, you put a base into it to create the nucleophile, and the nucleophile then attacks on the alkyl halide, eventually hydrolyzed to give you the 1 degree amine. Perfect. So that's your Gabriel's phthalimide synthesis. Next reaction that we have is known as the Hofmann's bromoamide degradation reaction. So people, what we do over here is RC double bond O, single bond NH2 is taken with NaOH, Br2. That's all basically. Okay, that's all basically that you have to do. You take sodium hydroxide or potassium hydroxide, cool. Now what is this? Why is this reaction called a bromoamide reaction or a bromamide reaction? You might call it anything, bromoamide, bromamide, whatever. So let me tell you, the name for this reaction comes from this particular case. So first of all, this oxygen captures one of the protons. This gets converted to RC double bond O, single bond NH negative, and this guy captures one of the bromines. So the species that will form over here, RC double bond O, single bond NHBr. This species, my dear friends, is known as the bromoamide or bromamide. Bromoamide, bromamide, same thing. So eventually, when you heat this up, this undergoes some rearrangement, and what you get at the end, the final product is very simple. You get RNH2. This R, this NH2 get combined together with each other, and on the side you also get CO2 gas evolution. From here, this CO2 gas is evolved. So what you have to remember over here is very simple. Amide NaOH-Br2 gives amine. That's all. Hofmann bromamide degradation reaction. This is what's mentioned in the NCERT. Cool. Amine, your CO2, if you combine it with sodium, it becomes sodium carbonate, NaBrH2O. So this is the reaction mentioned in the NCERT. Perfect. So the mechanism over here, I've just done a quick mechanism. You don't need to remember the mechanism as such, but the long mechanism is very long, so we'll not go into it right now. Okay, so now people, let's come to the basic character of amines. There is a certain exception that we will have to look at over here. So quickly let me explain the two ideas behind this, then we'll look at the exception. So people, when we are comparing basic character of these specific amines, let's say, first of all we take ammonia, then we take CH3NH2, then we take NCH3, CH3H, and then finally we take our 3-degree amine. Right? People, over here, how does the nitrogen act as a base? The nitrogen acts as a base by capturing a proton, right? So if this captures a proton, this will become NH4 positive, this will become NH3CH3, this will become NH2CH3CH3, and this will become NCH3CH3CH3 hydrogen positive. Fine. This is what they will become after acting as a base. Now, can I say that this particular structure, because of 3 methyl groups, has the most amount of plus I effect? Can I say it has the most amount of plus I effect? And this has the least plus I effect. What will plus I do? Plus I will make this lone pair even more reactive, right? This lone pair is a pair of electrons. CH3 is pushing more electron density towards it. So this should become more reactive. So according to inductive effect, hopefully you're listening to me carefully. According to inductive effect, this should be the most basic. But at the same time, if I do this reaction inside water, then people, the final ions that I've created will also undergo solvation. What is solvation? Solvation is the process where the water molecules come close to ions because of dipole moment. Yeah. So positive charge will be attracted to the negative side of water. Oxygen has the negative charge. So this will be surrounded by a lot of water molecules like this. Lot of water molecules will surround it. This will have water molecules, but since there is a CH3, lesser water molecules, because water will not be able to approach from this direction, steric hindrance. So water will approach only from this direction, not from this direction. This has more steric hindrance, so it will have less solvation. And this one over here, it has a lot of steric hindrance over here. It will have just a little bit of solvation. So according to solvation, according to hydration, this guy will be the most solvated. According to inductive effect, this is most basic. Most basic via inductive effect. This guy, this small ammonia, is giving you the most stable conjugate acid. See, simple idea is whenever we do a reaction and we make a stable species, that reaction happens very quickly. Yes, if I'm getting a stable species, this reaction should happen quickly. So the thing is, according to solvation, this should be the most basic, because this is giving a stable species. Solvation means stable. More solvated ion, more stable it is. So this should be, right over here, this should be most basic by solvation. So the thing is, there are two ideas working opposite to each other. We cannot predict their basic strength. We cannot think about their basic strength on paper. We need to do an experiment in the laboratory. So when we do the experiment in the laboratory, damn, I think I've broken something. Hello, check. Mic is fine, I guess. This wire gets stuck in my feet. Okay, so this, my dear friends, over here is the experimentally determined order. This is the case for ethyl amines, and this is the case for methyl amines. And this is something that you have to remember. They will ask questions on this, guaranteed. Every year they ask questions on this particular idea. So over here, as you can see, your 2 degree is more basic than 3 degree, more basic than 1 degree, more basic than ammonia. And in the second situation, 2 degree more than 1 degree, more than 3 degree, more than ammonia. Experimentally determined, because there are two factors influencing their basic strength. Okay. Kamali, you can think about it in an essential manner, yes, because hydrogen bonding and solvation are both essentially dipole-dipole interactions. Cool. So this is your experimentally determined order of basicity of amines. Very nice. I will write something. You already know what the product will be. What should happen over here, people? nitrogen should go and attack, chlorine should leave. Yes. So the product that we will get is RNH C double bond O. That's basically an amide, right? Just a fancy looking amide because there is an alkyl group on the nitrogen. So we can call this an N substituted amide. Yeah. We can call this an N substituted amide. So one way to make this reaction faster is by using a base over here. So what this base will do is that base will make it a stronger nucleophile. So the base makes amine a stronger nucleophile. So usually the base that is used over here is pyridine. So pyridine will capture a proton, N negative will be created that will attack faster to give you the N substituted amide. That's how this reaction works for acylation. Amine with acyl chloride gives you amide. Nice. Okay, people. So just 3-4 reactions remaining for amines. Just 3-4 reactions remaining for amines. It's okay. We'll do it. By 12, we should be done with amines. Then we'll see about biomolecules. All right. Carbylamine reaction. So this carbylamine reaction is also known as the carbylamine test. What we do here is that we test for primary amines. This test is done only by primary amines. So what happens here is, people, that if we take RNH2 and react it with dichlorocarbene, remember dichlorocarbene from Riemer-Tiemann reaction? Riemer-Tiemann reaction had this species, and this we know is an electrophile. This guy got added onto benzene as an electrophile. So what happens here is that this nitrogen can go and attack this carbon, and eventually you will get this type of species, RNH2 positive, CCl2 negative, and eventually you lose HCl molecules from this. Okay, you lose both of the HCl's from here. You lose both of the HCl's from here, and what you will get is RNC. What have we formed, my dear friends? We formed an isocyanide, also known as isonitrile. The weird thing about this compound is that this has a very bad smell. It has that rotten kind of smell. Bitter, rotten kind of smell it has. Isocyanide. Okay. So, how do we generate dichloromethane? Sorry, dichlorocarbene. This is called dichlorocarbene. How do we generate dichlorocarbene? We react chloroform with base. So, amine, chloroform and base will give us isonitrile and side products. Carbylamine test only given by 1 degree amine. If you have 1 degree amine, only then you will have isonitrile over here. Otherwise, this will not get formed. Cool. So this is your carbylamine test. Have a look at it, please. Hey, we know this already. Yeah, people? Those of you who've been watching from the beginning, you know this reaction. Diazotization, put water, turns into alcohol. Okay, so these diazonium cations, especially the aryl diazonium cations, are very versatile in nature. Okay, so what I mean by versatile is that this N2 positive Cl negative can be treated with a lot of different reagents. And this N2 will be replaced by the suitable reagent. N2 is replaced by the suitable reagent. So let me give you the different cases that we have. Okay. Have a look. These are the different cases of diazonium reactions. Look at the first case. So this Ar means benzene ring. Aryl diazonium cation, when it reacts with Cu2Cl2, copper is in its +1 oxidation state. Cu2Br2 +1 oxidation state, copper once again. CuCN +1 oxidation state, copper once again. So when we use copper +1 species with acid, it converts into chlorobenzene for Cu2Cl2, bromobenzene for Cu2Br2, cyanobenzene for CuCN, and you get nitrogen on the site. When we use these type of copper +1 species, my dear friends, these reactions are known as the Sandmeyer type reactions. These specific cases are known as the Sandmeyer type reactions. Now the next thing that we have over here, when the the aryl diazonium cation reacts with copper in HCl, copper in HBr, see the difference? Over here we basically use copper powder. Over here we are using copper powder. Copper was in +1 oxidation state over here. Over here it's in its 0 oxidation state. So in copper powder usage, with HCl will get benzene chloride, with bromine will get benzene bromide. These are known as my Gattermann reactions. Okay, so Sandmeyer reactions, Gattermann reactions. If I treat it with Ki, I'll get benzene with iodine. If I treat this species first with HbF4 and then heat it up, I will get fluoride. Basically fluoride providing reagent. So can you see the pattern over here, people? With chloride providing agents, I get chlorobenzene. With bromide providing reagents, I get bromobenzene. With cyanide providing reagents, cyanobenzene. Iodide, iodobenzene. Fluoride, fluorobenzene. Diazonium is exchanged by halogens or cyanides. Some more cases that we need to look at. I know this is a lot of information, but it's okay. Revision class, board examination in 3 days. So we'll do it. Yugant, over here AgCN will not give you a good yield. You can try doing that, but it won't give you a good yield. Alright, so H3PO2, dehydrating agent. Ethanol, these act as dehydrating agents. So these are two cases of reduction. Benzene diazonium cation with H3PO2, benzene diazonium cation with ethanol. What do we get at the end? We get benzene. Just have a look. Very simple reactions. Now, if we treat it with water, of course, we get phenol. Everyone knows this. We've seen this reaction 3 times, written differently. This is slightly different. So we put HbF4 to try to get the fluoride, but in the process, if I introduce NO2, In the process, if I introduce NO2, I will get nitrobenzene. Please take 2 minutes to observe these reactions. Yugant, I'll try to do biomolecules, but in case you guys are tired, whoever is tired, okay, you can leave and watch this class later also. That is absolutely fine. I'm glad you guys have sat in the live session for so long, but in case you guys are tired, you can watch this later as a recording also. I do not mind at all. Gokul, yeah, I will complete it today. Don't worry. Game Slayer is asking, are you not tired? I am tired. Of course, I'm tired, but it's okay, man. Can't have comfort every day in life. So last 2 days I was totally free. I had no class, Friday, Saturday. I was sleeping at home, doing nothing. And then yesterday I got a message that, Pahul sir, you need to take classes on Master Tamil. I'm like, sure. So I came today on Sunday. Otherwise, Sundays are supposed to be free. But then something or the other happened and they told me I should take classes here. I was like, okay, cool, let's do it. Gokul, awesome, man. Chalo, very nice. So these are your diazonium type reactions, very similar type of reactions over here. So, my dear friends, what will happen? Something very fancy will happen, and I'll show you some interesting images also. What will happen if I react this species with phenol? Carefully we'll think. Do you realize that this can act as an electrophile? Some positively charged species can act as electrophile, no? So what can happen here is that one of these bonds, if it moves here and essentially, sorry, I did the opposite. Yeah. So what will happen if this guy moves here and this bond moves over here? Can you see benzene attacks an electrophile? Electrophilic aromatic substitution. So after this electrophilic aromatic substitution, we will get this type of a species. This, my dear friends, is a colored species. And this is used as dye. D-Y-E, not D-I-E. Do you know what dyes are? Dyes are substances that are used to color clothes. So this weird cushion that I have over here, this is dyed with yellow color. Okay, this is dyed with yellow color. So this particular compound, it's a commercial name. Okay, so the commercial name for this compound is called solvent yellow 7. That's the name of this compound, solvent yellow. But in NCERT, they say that the color of this compound is orange. Okay, so NCERT says that this compound is orange, but actually it is yellow. NCERT is weird, so you write orange colored compound only. But I'll try to show you the color. This is what the compound looks like. So it's an orangish yellow color, by the way. It's an orangish yellow color. somewhere in the border. So it's called a solvent yellow 7. It's a common azo dye. Starts from diazonium salt, so we call it azo dye. So in the NCERT, it mentions orange, so we will call it orange. NCERT calls it orange, so we will call it an orange dye. Okay, so let me show you how this stuff is mentioned in your NCERT book. Hold on. I need to open up the NCERT first for amines chapter. There we go. Para-hydroxyazobenzene. So if you have a reaction with phenol, orange dye. If you have a reaction with aniline, yellow dye. This is what's given in the NCERT. So we will treat this as the truth for the board exams. Nitila Darshini Senthil Kumar, they will not ask that commercial name in the examination, so you don't need to worry about it. This is the kind of pattern that you can expect in the board exam. Nice. So this is also done. Now people, one reaction more please. One reaction. Roshni, so one was a compound which reacted with aniline, one was with phenol. We did the phenol case on the slides. And if you use aniline instead of phenol, the dye that you get is the other yellow colored dye. Chalo. So now people, let us look at the reaction with aryl sulfonyl chloride. My dear friends, this is a test for 1 degree versus 2 degree versus 3 degree amines. Okay. And this is known as the Hinsberg test. This reaction is known as the Hinsberg test. Okay. So people, let us try to understand how this works. So if I start with, let's say, a 1 degree amine, RNH2 reacts with, what is this aryl sulfonyl chloride? I'll tell you. So this is what it looks like. Benzene, this is your aryl group, S double bond O, Cl. Okay. So people, what's going to happen over here? Same thing again. Nucleophilic attack, chlorine leaves. You remove one HCl from here. And the species that you get out of this will look something like this. R, N, H, S double bond O, whatever this jazz is. Okay. Can you see this is what will be formed? Now, if I do the same reaction with a 2 degree amine, what will that look like? You have R2NH plus pH, sulfonyl chloride. Once again, you remove the HCl from here and the species you will get is RNR, sulfur, double bond O, pH. Can you notice the difference between these two species? Can you notice the difference between these two species? The difference is that the species on the left has an acidic hydrogen. So what happens is that this entire thing is soluble in NaOH. And this guy is not soluble in base. This is soluble in aqueous NaOH or aqueous KOH. That is not soluble in base. So if I do this reaction with 1 degree, I will get a compound that is soluble in base. If I do the reaction with 2 degree, I will get a compound that is not soluble in base. 3 degree amine gives me no reaction. 3 different types of reaction with 3 different types of amine, Hinsberg test. This reaction is generally done inside an ether solvent. So, this case, you form this species, then you put aqueous KOH, this goes away with aqueous KOH. This case, you put aqueous KOH, nothing happens. So, this remains in the ether solvent. Over here, no reaction only. You can't. So, essentially what's going to happen is you remove the H positive and you put N negative, K positive, like we did with Gabriel phthalimide. So, that's the reaction with the alkali. Anushka is asking, is this a recorded video? Yes, this is a recorded video. I recorded this session in the year 2075. So 2075 is when I recorded this video, and then I worked out a lot of quantum mechanics, and then I disproved Einstein's theory of relativity, proved that time travel to the past is possible, and through this video 50 years back. So yeah, it's a recorded video, sure. Sanjay, we did the important ones for board examinations. Shanmugamani, with this class, if you pay all the attention that you can, in board examinations, you can get it easily like 85% marks. 15% marks I'm leaving to you. Anushka, yeah, I will take rest. Alright, people, amines chapter is over. Good stuff. Amines chapter is over. Thank you so much for waiting till now. Let's do a couple of reactions of amines, then we'll move on towards biomolecules. Let's do this. And Abhishek is asking any tips for board examination chemistry. NCERT practice. Practice from previous year board papers itself. Okay. Evolbrum is asking, is it fine not to sleep for 3 days? No, it's not fine at all. Please don't kill yourself. That's not fine at all. Yugant, session PDF will be uploaded in the description box tomorrow. Alright, let's do this. Arrange the following compounds in increasing order of their basic strength in aqueous solution. Done. We've got methylamines over here. So what was the order for methylamines? Where is the order for methylamines? My brain is slowing down for sure. Wow. Hey man, that was a very nice page. Green and highlight also I did. This one. For methylamines, what's the order? 2 degree, more than 1 degree, more than 3 degree. And they will definitely ask this in your board examination. So please remember this. Okay. What is Hinsberg reagent? Benzene, sulfonyl chloride. What is the role of pyridine in the acylation reaction? Pyridine acts as base, takes proton from amide, sorry, not amide, amine, turns it into strong nucleophile. Yeah, so this is the jazz that we studied a little while back in the Hinsberg test. No, not in the Hinsberg test. Sorry, Hinsberg test was the previous one. Sorry, people, my brain is a little slower now, but here we go. Pyridine. So it abstracts the proton turning it into a stronger nucleophile so that it can attack the acyl chloride faster. Yeah. Yes, PDF will be shared after the class is over tomorrow. I mean, class will be over in some time, but PDF will be shared tomorrow. Okay. All right. Let's solve more questions. CH3CONH2 on reaction with NaOH and Br2 in alcoholic medium gives. What is this reaction, people? This reaction is your Hofmann's bromamide degradation. Yes. So we will form simply a primary amine. This CO from the middle will be lost with sodium carbonate. Very good. Okay. Can you try this question? After this question, we'll move to biomolecules. Okay. All are board previous year questions, by the way. So, diazonium cation with CuCN. A will be phenyl cyanide or cyanobenzene. Then if I quench this with water, the cyanide will get converted to C double bond O single bond OH. And when this is treated with ammonia in the presence of heat, C double bond O NH2. Yeah. Sorry. My system is a little weak after speaking for such a long time, but it's okay. So NO2 FeHCl, what will this be? This will be aniline. Reduction of nitro compounds to create amines. Then diazotization. So this is your diazonium cation, N2 positive, Cl negative, and ethanol. Which reaction is this? This is the reaction for reduction of the diazonium cation. So option C over here would be benzene. Let me show you this reaction. This reaction is over here. Great. So that was from your diazonium type reactions. There are some conversions also if you want to do this. Yeah. Nitrobenzene to aniline, we did this already. Used FeHCl or SnHCl, done. Ethane amide to methane amine. Ethane amide to methane amine. Once again, what do we have over here? Hofmann's bromamide degradation. What are the reagents for Hofmann's bromamide degradation? Br2 in the presence of NaOH and heat. Ethane nitrile to ethane amine. So we have CH3, C triple bond N converted to CH3, CH2, NH2. How do we reduce this particular species, people? Put LiLH4. Or you can do hydrogenation, or you can do that sodium amalgam thing in the presence of ethanol. So many different things. Dibalh will convert this to aldehyde. I want to convert to amine. So to amine, I will use stronger reducing agents. All right. So people, amines chapter is over. Good job. People who are worrying that it is too much. It's just a revision class, man. These things are supposed to be studied over a span of a year. We're in a revision class. And if you haven't studied for 1 year, then one day you can manage 6-7 hours. I'm sure. So, good stuff, people. Very nice. Now, the final chapter of organic chemistry is biomolecules. And what I often say about biomolecules is that this is a bonus chapter for us. It's a bonus chapter because there are two reasons. Number one, it's not a very high weighted chapter. Okay, 1 or 2 questions might come from it. That 1 or 2 question might be anywhere. It might be a 2-mark question, might be a 3-mark question, might be a 5-mark question also. But it is a bonus chapter because that question can be from anywhere in the NCERT. Okay. So first of all, what I will do is show you what the biomolecules NCERT looks like, because most of the things will be asked from this particular book itself directly. So you have some ideas about sugars initially, carbohydrates. Some specific reactions of glucose are given. Okay, we'll have a look at those reactions. Some cyclic structures of glucose are given. We'll draw this. Some other important carbohydrates are mentioned over here with certain types of linkages and stuff. We'll understand that. Then we have the segment of amino acids. Amino acids are the building blocks for proteins. Okay. And after proteins and their complications, we come to some ideas about vitamins and stuff. And then we have the composition of DNA and RNA, nucleic acids. Yeah? DNA is deoxyribonucleic acid and RNA is ribose nucleic acid. So these are the main segments of biomolecules from the NCERT. So majority of this chapter has to be done by self-study. Good morning, everyone. So for this, your main effort will of course be self-study. But some side effort Pahul sir will do with you. I am Pahul sir, by the way, in case you don't know. Yeah. So some ideas we will discuss together, and remaining ideas you can study from the NCERT. So the first idea from biomolecules is about glucose. Okay. Glucose is a 6-carbon molecule, and please draw with me the way I'm drawing. On top we'll put CHO, on the bottom we'll put CH2OH. Over here we'll do OH, H, OH, OH. Wherever we've put OH, put hydrogen on the left side. Where we have hydrogen, put OH on the right hand side. Okay, so glucose is basically a sugar or a carbohydrate, which is essentially a polyhydroxy. One second, please. Which is essentially a polyhydroxy aldehyde. Yeah. So this is what we have over here. Glucose, it is a sugar. It is a polyhydroxy aldehyde. Nice. Now, my dear friends, since it is a 6-carbon species, yeah, 1, 2, 3, 4, 5, and 6, it is also known as an aldohexose. Aldo stands for aldehydes, hex stands for 6, O's stands for sugar, aldohexose. Okay. Now, people, what happens when alcohol reacts with aldehyde? When alcohol adds on to aldehyde, we have hemiacetal formation. So let us do hemiacetal formation over here with this particular movement. this oxygen forms a bond with this particular carbon, and the OH group, let's say we keep it on the left hand side for now, hydrogen we keep on the right hand side. Yeah, so this was aldehyde, this carbon is now the hemiacetal, OR OH. Remember hemiacetal has OH and OR on it, so OH OR. Remaining carbons are the same. Right. Now people, do you realize that the original straight chain structure of glucose has 1, 2, 3 and 4 optically active carbons? This guy has 4 chiral carbons over here. My dear friends, this particular form of glucose which occurs naturally, this form is known as D plus glucose. Plus stands for dextrorotatory. This rotates plane polarized light in the clockwise direction. This capital D is not equal to this plus sign. That capital D is different. That capital D means, listen carefully, I'm doing this in a fast manner. That capital D means that the last stereo center has OH on the right. This capital D means last stereo center has OH group on the right side. Last optically active carbon, OH on the right hand side, capital D. Plus means when you throw it in polarimeter, plane polarized light is rotated in the clockwise direction. This is one of the hemiacetal forms. But notice in the hemiacetal form, this is also a chiral carbon now. This is also a chiral carbon now. My dear friends, I will make another form. Realize both forms are different. I'll make it, then you will understand. People, can you spot the difference between these two compounds? Can you spot the difference between these two compounds that I've drawn for you? This and this. Can you see the orientation, the configuration of this top carbon is different? Kamali, yes. Dextro is plus, levo is minus. So very nice, you observe the difference. The difference is in these two carbons. So my dear friends, these two hemiacetals that we formed are known as the anomers of glucose. What are anomers? Yeah. What are anomers? Let me show that to you from the NCERT directly. Where is biomolecule? Yeah. So, if you search for, where is search? Yeah, if you search for anomer, the two cyclic hemiacetal forms of glucose differ only in configuration of the hydroxyl group at C1. Can you see these are the two structures that we drew? Yeah. So one has OH on the left side, we call it beta. One has OH on the right side, we call it alpha. And these three structures, people, are in equilibrium with each other. If you take only this structure, you throw it in water, it will break, form this, it will also form this. These three structures in water are in equilibrium with each other. So isolating one of these structures is pointless, because as soon as you use glucose, put it in water, equilibrium of all three structures exists. Alright, so the two cyclic hemiacetal forms of glucose differ on configuration at C1, called the anomeric carbon. Such isomers are called anomers. What's the fancy thing about anomers? Anomers are in equilibrium with each other. Okay, anomers are in equilibrium with each other. Now, do these look like good structures? That's not how we are used to drawing cyclic structures, right? We should draw cyclic structures in a slightly different fashion. Let's draw cyclic structures like this. Okay. Sashwin, yes, absolutely correct. Anomers are actually diastereomers of each other. Stereoisomers, but not mirror images. Yes. But anomers differ in configuration on one carbon and are interconvertible to each other. That's what anomers are. So now let's make these structures. These are called the Haworth projections. You will read all of that in the NCERT. People, take this structure that you have. Whatever is on the right hand side, you put those at the bottom. See what I'm doing. You divide this structure into two halves, okay? Whatever is on the right, you put it at the bottom. Let's number the carbons for your help. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5. I will draw carbon 6. On carbon 1, OH on the left side. So on carbon 1, I will put OH towards the top. Observe. Carbon 2, OH on the right. Right side means put it at the bottom. Carbon 3, OH at the left. Carbon 4, OH at the right. Carbon 5, CH2OH. You always make it over here. So this CH2OH at the top basically refers to this D configuration only. Similarly, over here, what's going to happen? Numbering the carbons once again. 1, 2, 3, 4, 5. This is the sixth carbon. So, on carbon 1, you have the OH group on the right, OH. Carbon 2 also on the right. Carbon 3 at the left side. Carbon 4 right side. Carbon 5, CH2OH at the top. So, this is your sixth carbon. Same over here. Fine. Sanjay, yeah, they sometimes do. Sometimes they do. So they will not ask you the exact polysaccharide diagram, but they will ask you what type of bond is there in this polysaccharide, what type of bond is there in cellulose, let's say. Okay. So one of these forms is called the alpha form, the other form is called the beta form. Let's see the NCERT ones to refer to these structures, as you can see. Yeah. This case where OH is on the left, which means the OH is on the top, is known as the beta form. The other case is known as the alpha form. And since these two structures look like pyran, okay, this compound is called pyran. These structures are also known as pyranose structures. Okay, that is why these are also known as pyranose structures. Perfect. So this was a little bit of idea about glucose and its cyclic structure and how it works. So you have to read about it more from the NCERT, obviously. Have to read from the NCERT, obviously. People, I hope you realize that glucose can reduce Tollens reagent because it is an aldehyde. So it can reduce Tollens reagent. It can also reduce Felling's reagent. Also it can reduce Benedict reagent. Okay. So glucose can reduce Tollens reagent. My dear friends, how can we say that this cyclic form will reduce the Tollens reagent? Let us take one cyclic form of glucose. Can I say the cyclic form will reduce Tollens reagent? Cyclic form will reduce Tollens reagent if it breaks apart into aldehyde. Yes, if it breaks apart into aldehyde, then you will have the reaction. How do we recognize? How do we recognize if this can break apart into the aldehyde? We have to spot the hemiacetal carbon, right? Hemiacetal carbon. What is the characteristic of a hemiacetal carbon? A hemiacetal carbon has a cyclic oxygen and an OH group. Yes, if you have the cyclic oxygen and the OH group both, then this can break apart into the aldehyde. When you break this, it will turn into aldehyde. So have a look at it. Hemiacetal carbons looks like this. Oxygen of cycle, OH group. Cyclic oxygen, OH group. So if you can spot a hemiacetal carbon reducing sugar, if you can spot a hemiacetal carbon, it will be called a reducing sugar. So let me ask you, look at maltose. Maltose is a sugar that gets formed when you have glucose and glucose joining at carbon 1 and 4 via an ether type linkage. Basically, ether linkage is formed. Oxygen bonded to these carbons. A better way to draw this, just a second. A better way to draw this one would be this way. That's better. Okay. So what I want you guys to do now is I want you to try and recognize if this is a reducing sugar or not. Is this a reducing sugar? Can you tell me? Yeah, people. What we need to recognize for reducing sugar is hemiacetal carbon. Look at that carbon on the right side. Cyclic oxygen and OH group. This is your hemiacetal carbon. And therefore, this is a reducing sugar. Maltose is a reducing sugar. So keep it in your mind. Maltose is a reducing sugar. Look at this case. Lactose. Lactose is found in milk. Okay, lactose is found in milk. So you have beta D galactose and beta D glucose combined together via this ether linkage. One from the top side, one from the other side. Ether linkage. So people, can you see if this is a reducing sugar or not? Hemiacetal carbon once again. Cyclic oxygen, OH group. Nice. This is also a reducing sugar. Brilliant. Acha. Let's look at sucrose. Yeah. Sucrose is the most common form of table sugar. The sugar that we eat, that is sucrose. Okay. Can you find any hemiacetal carbon over here? Can you find any hemiacetal carbon? Yeah. I can't find any hemiacetal carbon. This carbon, cyclic oxygen, no OH group. CH2OH, I need OH. No hemiacetal. Over here also, oxygen, OH was there, but now you have turned it into ether. No use. It used to be OH, but now it is ether. No use. This one also no use. This one also no use. There is no hemiacetal carbon. Sucrose, my dear friends, is a non-reducing sugar. Okay, and sucrose is made from the combination of glucose and fructose. And what we have in the middle is an ether linkage. Now this ether linkage looks very simple, but do you realize we are doing the chapter of biomolecules? Biology and chemistry, biologists and chemists, these people hate each other for some reason. Yeah. Biologists and chemists, for some reason, they hate each other. So what biologists do is they try to complicate simple ideas of chemistry. So instead of calling this an ether linkage, they call it a glycosidic linkage. Just to sound fancy. What is ether? No. Glycosidic link. Just to sound sophisticated. So, if the glycosidic linkage is on the same side, this is known as an alpha glycosidic linkage, same side. But if the glycosidic linkage is in the opposite side, I will show you another image which will help you visualize better. On the opposite side, this is known as a beta glycosidic linkage. Bharadwaj, no comments, bro. So amylose. Amylose is glucose, 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 glucose. It's a huge chain of glucose joined with alpha glycosidic linkages. Read this on your own from the NCERT also. Okay. So amylose is lots of glucose molecules joined by alpha linkages. Okay. Amylopectin. This is an amylose chain. This is an amylose chain. But two amylose chains are linked with branching. This becomes amylopectin. Observe the structures later from your notebook, please. From your textbook. Cellulose. Glucose, 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 but joined with beta linkages. This is a different way to represent the beta link. One oxygen on the top, one oxygen pointing towards the bottom. Yeah. So, cellulose is once again a polymer of glucose. So, these are some important ideas about sugars. These are some important ideas about reducing sugar, non-reducing sugar, anomer, anomeric carbon, what is cellulose, what is sucrose, maltose, lactose, and you study this NCERT after my explanation, you will understand it much better. There are some chemical reactions given over here. You can study them on your own, you will understand them. See, aldehyde group, hydroxylamine gives C double bond O, N single bond OH. The same derivative that we were making. CHO, HCN adds, gives the cyanohydrin. So these reactions of glucose, you read them on your own tomorrow or whenever you get the time before 27th. You will be able to understand these reactions very easily. Okay. When you reduce glucose, you get normal N-hexane. When you treat it with bromine water is a mild oxidizing agent, the CHO gets converted to COOH, gluconic acid. If you reacted with acetic anhydride, all the alcohols turn into esters. If you reacted with stronger oxidizing agent, you get COOH on top and bottom also, saccharic acid. So read about these properties. carefully after the class. Now, people, let's think about amino acids. Amino acids. What are amino acids? Make a V shape, C double bond O, single bond OH, NH2. Put any random group over here. Okay. So such amino acids are called alpha amino acids. Why alpha amino acids? Because if this is the primary functional group, this is the alpha carbon. And on the alpha carbon, we have the NH2 group. Okay. So alpha amino acids. Right. So depending on these different groups, you will have different amino acids. So for example, if you have only hydrogens over there, C double bond O, single bond OH, NH2, this species is called glycine. Okay. If I take a CH3 over here, one of them is already a hydrogen, of course, C double bond O, single bond OH, NH2. This species is called alanine. Aniline is different, alanine is different. Okay. So this is your alanine, and then you have etc. amino acids. So all the different amino acid groups, this G that I've written over here, are mentioned in the NCERT. These are the groups. Okay. These are the groups. So if that group is hydrogen, glycine. If that is CH3, alanine. If that is this isopropyl group, valine, leucine, isoleucine, etc. If you do not remember them, it's okay. If they ask you a memory-based question on these, leave it. Because in 2 days, how will you remember so much? If you already remember these, that's fine. But if you're panicking and trying to remember all of these in 3 days, it's sort of impossible. So if you don't remember these names and the structures, it's okay. Leave that question. Don't worry. Okay. Fine. So these are the 20 different naturally occurring amino acids. 20 different naturally occurring amino acids. Now, among these acids, the ones marked with the star are known as essential amino acids. What are essential amino acids? Essential amino acids, our body cannot make them on their own. Our body can not make them. So, it is essential for us that we take them from our diet. Need these from our diet. So, histidine is an essential amino acid. Threonine, methionine, phenylalanine, tryptophan, valine, leucine, isoleucine, arginine, lysine. These are essential amino acids. Your body doesn't synthesize them, so you have to take them from food. So milk is a form of protein where you get all these amino acids. Non-vegetarian protein generally has all these amino acids. Vegetarian sources of protein lack in certain essential amino acids. So, yeah, whatever. Coolio. So these are amino acids. And my dear friends, now I will show you a chemical reaction and you will say, sir, we already know this. What if one amino acid comes close to another amino acid? Just have a look. And then there is a loss of water molecule from here. Acid plus amine gives you amide. So simply make an amide bond over here. isn't it? Simply make an amide bond over here. But biologists, chemists don't like each other. So instead of calling this an amide bond, they call it a peptide bond. Peptides. So when we combine two amino acids together, we've created a dipeptide. If we put 3 amino acids, tripeptide, 4 amino acids, tetrapeptide, 5 amino acids, pentapeptide, so many amino acids together, polypeptide. What are proteins? Polypeptides. Okay? What are proteins? Proteins are nothing but polypeptides. Okay? So, some fancier looking images of all amino acids you will find in the PDF. Okay? And just to show you an idea, look at this. These are types of board questions. Let me show you, just with the knowledge that we've studied till now, we can solve a good number of board questions. Define the following related to carbohydrates. Anomers. Draw the two forms of glucose. Point to those carbons. Say that these two carbons are different in configuration but are interconvertible. These are called anomers. Glycosidic linkage, just a fancy ether linkage between two carbohydrates. What is the difference between peptide link and glycosidic link? This is amide, this is ether. Nucleoside, nucleotide, we'll see. This comes from DNA, RNA. Look at this. Which of the following carbohydrates gives only glucose on hydrolysis? Maltose gives only glucose. Sucrose gives glucose and fructose. Lactose gives galactose plus glucose. And galactose itself is a monosaccharide. Monosaccharide means smallest unit of sugar. Can't break it into smaller units. Maltose is the correct answer over here. These are the few cases which I had to show you for previous year board exam. Nice. Folio. So, just a little more information about amino acids, then finally we'll do DNA, RNA. Just 15 more minutes. 9 hours revision class. It's organic chemistry, it takes time. So people, when lots of amino acids will join together, it will look something like this. Lots of amino acids joined together. Can you see we've created a thread of amino acids? We've created a thread of amino acids. Creating a thread of amino acids is called primary structure of protein. Okay? Now, if this thread starts to do this, if it becomes a long thread, it will start to make a coil. If it starts to make a coil, this coil is known as the secondary structure of protein. Looks weird right now, but yeah. Instead of making coil, if I do this, I'm making this sheet sort of thing. Yeah? Can you see if I have many threads, I can make a sheet over here. That is also secondary structure. So, you could have, from these threads, you could have these coils. These are known as alpha helix. And you could have these type of sheets from these threads. These are known as beta pleated sheets. And these two are essentially your secondary structure of protein. So the first one is primary structure, then you have secondary structure. If you take secondary structure and complicated even more, 3-degree structure, tertiary structure. If you take multiple tertiary structures, combine them together, quaternary structure. Let me show that to you in the NCERT. It's very simple to understand now that you know what an amide bond is. Just a moment, please. Look at this image. Primary thread, secondary structure, complicated even further, tertiary structure, multiple tertiary structures sitting together. Can you see this is one coil, this is another coil, quaternary structure. And these secondary, quaternary, these structures are stabilized by some hydrogen bonding interactions. Okay, so alpha helix, beta pleated sheet, fine. They are stabilized by intermolecular hydrogen bonds. Roshniya does. See, primary structure, secondary coil, tertiary complicated coil, and quaternary lots of coils sitting together. And now, if I have this beautiful quaternary structure, if I put acid into it, or if I heat it up, this structure breaks and comes to the primary structure. What did I say? If I have any protein with a quaternary structure, complicated protein, if I put acid into it, or if I heat it up, breaks and comes back to the primary structure. Hydrogen bonds are broken. So when you come back to the primary structure, that is called denaturation. During denaturation, secondary and tertiary structures are destroyed, primary structure remains. The coagulation of egg white on boiling is a common example. Egg boiling, we know, turns from liquid to that mushy solid. So that intricate structure breaks. Another example is curdling of milk. So when you turn milk into curd by putting some old curd into it, putting in a warm place. Denaturation by bacteria. Nice. So these are some examples of denaturation. So enzymes you will read on your own. Enzymes are nothing but fancy looking catalysts. Vitamins also you can read on your own. Enzymes and vitamins you read on your own. Some basic ideas behind what are these vitamins, what are their uses. Those things are given. And then finally, let's come to nucleic acid. Last thing for today's session. Last thing for today's session. My dear friends, can you see these are two reducing sugars? These two structures, whatever they look like, are essentially reducing sugars, right? These are simple monosaccharides, smallest units of sugars, and both of them are reducing in nature. So this one is known as ribose and this one is known as deoxyribose. Ribose sugar, deoxyribose sugar. How are they different? Look at this second carbon. Just have a look at the second carbon. Can you see the difference between these two? Ribose sugar, deoxyribose sugar. Right? So, my dear friends, the ribose sugar is the building block for RNA, and deoxyribose on the other hand is a building block for DNA. Ribose nucleic sugar, deoxyribose nucleic sugar. Okay, ribose nucleic acid and that is deoxyribose nucleic acid. So my dear friends, what we want to do on these sugars, okay, what we want to do on this sugar, just have a look at this diagram. What I want to do is I want to remove this OH and put a base over here. And what I want to do to this OH is I want to create an ester over here. So we want to put base here. I'll show you the bases. And I want to do an esterification over here on this particular oxygen. Okay. Now, these, my dear friends, are the 5 bases. These are the 5 bases that we have: adenine, guanine, cytosine, thymine, and uracil. Uracil is only in RNA, not in DNA, and in DNA you have only thymine, you don't have uracil. So only in DNA. So what we will do is, we'll remove this OH group and put that base over there. How will we put that base over there? Something like this. I'll show you another image of how this base is bonded. Now on the other side, this is the basic sugar unit. Listen carefully. Basic sugar unit. We've put the base over here. On the basic sugar, if we have a base, this is called a nucleoside. How do you remember this? One side you put base, nucleoside. You put base on one side, nucleoside. Okay. But now on the other hand, if I have put the base, okay, fine. But over here I have created a phosphoester. This is not your typical carboxylic acid ester. No, this is your phosphorus ester. Phosphoester. So when you have base and phosphoester both, this is called a nucleotide. Understood? Base sugar, base, nucleoside, basic sugar, base and phosphoester, nucleotide. And now these phosphoesters, if I've made ester on one side, I can make ester on other side also. If I've made ester on one side, I can make the ester on the other side also. So my dear friends, one sugar, look at this. Another sugar, look at this. So just have a look at this particular idea. Base we've put on the 3 carbon. On this 5th carbon, I have a phosphoester. Another 3 carbon is making another phosphoester with it. So I'm sorry, this is the carbon 1. Base is put on the carbon 1. 3, 4, 5. So carbon 5 and another carbon 3 create this double-sided ester known as phosphodiester linkage. Alright. Phosphodiester linkage. So with multiple phosphodiester linkages, you can keep combining these nucleotides with each other. And lots of nucleotides will make your nucleic acid. Something like this. Can you see? One sugar has a base on one side, phosphoester, another sugar, base, phosphoester, another sugar, phosphoester, another sugar. It keeps going. So this makes one side of DNA. Yeah, this makes one side of DNA. Now this one side of DNA is hydrogen bonded to another side of DNA. We've studied that in our childhood days. Yeah. So one side of DNA bonded to another side of DNA with hydrogen bonds. So there are 2 hydrogen bonds between thymine and adenine, and there are 3 hydrogen bonds between guanine and cytosine. G will always bond with C with 3 hydrogen bonds. T will always bond with A with 2 hydrogen bonds. Okay? So this is how your DNA is formed, the little colorful structure that is here. So my dear friends, now that I have given you so much Data. All I've done is I've fed you data. After this data, if you read the NCERT, you will be able to understand each and every word of it. Phosphodiester linkage, sugar base phosphate link goes on. This is your double helix structure, right? So now all you need to do in order to make your biomolecules even stronger is you need to read the NCERT. Pretty much. And with that, my dear friends, we shall call it a new day. Technically speaking, the class is over. All right. Cool. Kamali, so the thing is, the pentaacetate can be formed from your hemiacetal, right? From your hemiacetal also you can form the pentaacetate. So that hemiacetal form cannot react with the hydroxylamine because that C double bond O is in the ring now. Gokul, cool, bro. See you. What else, people? Thank you so much for staying till the end. For those of you who stayed till the end or those of you who watched the majority of the lecture, I'm glad you did. Thank you so much for joining in. If you enjoyed, you know exactly what to do. Like button, subscribe. You can leave a comment if you are watching this as a recording. Perfect. Sanjay Singh, any way to memorize vitamins? In the last few days, I don't think you should be cramming up too much information. If you can remember some of those ideas, fine. Otherwise, don't worry too much about it. Joshit, yo man, what's up? And once again, thank you so much for your appreciation as well, people. I feel really good when you guys give me back the energy that I've invested in you. Good stuff. Kamali, we'll discuss that tomorrow in the coordination chemistry part. So tomorrow at 1 p.m. I have kept the session for inorganic chemistry marathon. 2 chapters only, so that will not take so much time. Maximum 4 hours it will be. So coordination compounds will revise. We will not be doing basic theory all the time. We'll revise and we'll also revise D and F block. More focus tomorrow we'll put on questions because inorganic chemistry is best learnt via questions. So read question, revise theory, read question, revise theory. Okay. Bhardwaj, yes, the plan is for physical chemistry session on Wednesday at 1 p.m. So that's also just 3 chapters. That will also not take a lot of time. Cool. Sanjay, yo man, thank you so much, bro. Yes, Sanjay, tomorrow we will do a live session at 1 p.m. So for that, I need to go home and sleep. I will upload the session PDF. So session PDF will be updated tomorrow. In the morning, they will upload the session PDF. Cool. Perfect. All right, people. Thank you so much for joining in. I will take your leave. I hope you enjoyed this one. See you tomorrow for inorganic chemistry. Bye-bye. Take care. Good night. If you have any doubts, you can leave a comment. I will come back to you. Take care.